Hi, Hemant. Gabrielle already came and checked out her presentation.
Yes, Jen, go ahead. What did you say?
Yeah. No, I was just saying that Gabriela also came and checked out her presentation.
Oh, good, good, good.
Right,
Okay.
right.
She hasn't joined yet, has she?
She has already joined. She's just on mute right now. She said she'll join us at 1:30.
Oh, yes, I see her. Yes,
Right.
I see her.
Hi, back again.
Hi, Gabrielle.
Hi.
Good morning.
Good morning. Good morning.
We have about 7-8 minutes. Okay.
Yes, good. So I'll switch off my video again.
Yeah, even I will. Hi, Sonia. Can you make me co-host just in case required?
Yeah, sure.
Oh, yeah. I think I'm co-host already.
You are, no?
Yes, yes.
Yeah, great. Eman, do you want to check your screen share or it's okay?
We can get started now.
Good afternoon, everyone. It's an honorable moment for our college and for us to have your prestigious presence in today's event. We're truly thankful to all of you for staying through all these 3 days of the ACM India 2022 workshop series. Here we are on the final day of the workshop, which is the ACM India's annual event 2022.
To formally invite all of us, we have Dr. Hemant Pandey, the Executive Director of ACM India Council. Dr. Pandey is also the Executive and Technology positions at Siemens Corporate Research, TRDDC, Persistent Systems, EZEST, and KPIT Technologies. He holds a PhD and Master's in Computer Science from Rutgers University, USA, and Bachelor's from IIT Bombay. We're extremely happy to have you here, sir. Now I request you to address the audience, please.
Thank you. Thank you very much. And on behalf of ACM India and our host institution, PSG Tech, welcome all of you to the ACM India Annual Event 2022. Today marks the culmination of 4-day events. Let's have that nice slide about those 4 days now. So today marks the culmination of 4-day events, which bring out multiple facets of computing initiatives by the members and volunteers of ACM India. Day one, as you can see, day one on Wednesday is our special focus on gender diversity, when we bring out the contributions of women in computing research.
Jayant, I think Hemant is having some connectivity.
Yeah, Hemant seems to be frozen, right? I was wondering whether it is my end or whether.
No, it's Hemant.
Right.
It's an opportunity.
Yeah, right.
Jayant, can you hear me? Can you see?
Yeah, yeah. Now we could hear you. You're frozen for about 10 seconds in the middle.
I see.
Right,
Okay.
right.
All right. Yeah, I thought so. So, as I was saying, and finally today at the annual event, it's an opportunity to interact with some of the best minds in computing from the world. Let's have that slide for today's schedule. It's also an occasion to celebrate some outstanding contributions and achievements from India. We are continuing our tradition of inviting the recent Turing Award recipient to spend time with us and some eminent award-winning leaders for keynote lectures. And we'll conclude with the award function, where we felicitate the India's recipient of ACM level honors as well as ACM India honors. But first, let's find out how ACM at India level and at global level is continuing its mission to advance computing as a science and profession. And to tell us about that, about the India initiatives part, let me invite Professor Jayant Haritsa. Jayant is, as you all know, he's president of ACM India Council. Let's have Jayant's introduction slide. Great. Okay. He's professor at the Department of CDS and CSA at the Indian Institute of Sciences, Bangalore. As you can see, if there is an award in computing, he deservedly has that award. That's the recognition of the contribution that he has been making. With excellent academic credentials and his involvement in professional activities such as ACM India, I think it's a pleasure to have him, pleasure to welcome him. Jayant, all yours.
Thanks, Hemant. Shall I start sharing my screen?
Yes.
Yes, right. So is this visible? Is the slide visible, Hemant?
Yes.
Okay, so thank you, Hemant, for the warm introduction. And on behalf of ACM India, a warm welcome to all the participants in this annual event, and especially our distinguished guests from headquarters, led by Professor Gabriela Cortsis, President of ACM. While we had thought that last year's online mode was an aberration, unfortunately, this year too, we have been forced to have it in the same mode due to the third COVID wave. However, the good news is that despite the pandemic, ACM India has made significant strides over the past year, and I'm pleased to present a summary report on our activities. Although computing may appear to be a recent discipline, ACM was founded way back in 1947, coincidentally, exactly a month after India's independence. And ACM is currently celebrating its 75th anniversary, as is India. Since then, ACM has developed to be the largest educational and scientific computing society in the world, boasting of over 100,000 members globally. ACM India was launched 12 years ago in January 2010 as a regional council on the lines of ACM Europe and ACM China to give focus to the activities in India. And what is amazing is that despite its relatively short existence, ACM India has grown by leaps and bounds to become one of the largest regional communities. In fact, our latest count is over 12,000 members, constituting more than 10% of the worldwide membership. We also have a very healthy and roughly equal mix of professional and student members in our community. Further, our members are organized into an impressive number of SIG, professional, student, and ACMW chapters spread all over the country. Our annual membership fees are extremely low, just about the cost of a large pizza. So I strongly encourage those of you in the audience today who are not members to please join us at the earliest. The council is the elected governing body of ACM India and has a 2-year term. The current council, which includes 13 elected members, the ones marked in green, took office in the summer of 2020. And from the list here, you can see that they represent the major academic institutions and industrial research labs in the country. The past president and the ACMW chair are also ex officio members of the council. Finally, to manage ACM India's activities on a continuous basis, we have an executive director and a chief operating officer who are seasoned industry veterans and ensure that our programs are implemented in a professional and timely manner. This summer, we will be transitioning to a new council, and while some of the current members will be continuing as part of their 4-year tenure, an election process for electing 8 new members has been initiated and will be held in May. I request all the professional members of ACM India to actively participate in these elections and ensure that a truly representative council is elected to office. Here is a picture of our recent council meeting, which was held just last week. And as you can see, they all look reasonably happy, so the work must be going on pretty well. When our council took office in 2020, we felt that the scale of ACM India activities had reached a stage where it would materially benefit from a streamlined organizational framework that evolved from the earlier largely volunteer-driven phase. So a dozen focus subcommittees were set up, covering the gamut from awards to external engagements that you see listed on the slide. Most of the committees are chaired by council members, and a designated member of the executive committee serves as the liaison to each subcommittee. This structure has worked out very well for us and ensured focused progress on all our multifarious dimensions. In the rest of this presentation, I'll walk you through the highlights of the various initiatives, both ongoing and new, that have been taken up over the past year. I'm particularly glad to report that there has been enthusiastic involvement from our members and volunteers as both contributors and participants in all of these programs. To start off, on a regular basis, we host popular webinars by experts on topics related to industry and education. Recently, Live interaction discussions have been added to this mix to give the audience a rich blend of perspectives on a state of the art area. For instance, an upcoming event is on current trends in computer vision. We also support an eminent speaker program on the lines of ACM's Distinguished Speaker Program, where leading Indian experts visit chapters that would like to benefit from their knowledge and experience. We have a large pool of experts, and 5 more have joined over the past year. But of course, due to the pandemic, all visits are online at the current time. A brand new program of industry boot camps, which are 3-day intensive upskilling events for professionals, has been made operational, and 2 offerings, one on blockchain technologies and the other on digital experiences, were successfully conducted over the past year. Mini Graphs is our most recent initiative where subject experts produce accessible but in-depth surveys on current technologies. The first issue on the highly contemporary topic of privacy of personal information was released, appropriately enough, on Mahatma Gandhi's birthday last year. The upcoming issues include topics such as hybrid cloud, high performance computing for AI, and verification of software systems. The mini graphs have also been invited for inclusion in the well-known ACM Q series. Moving to the research front, ACM India runs a plethora of programs that further the cause of computing across all segments of the research fraternity. ARCS, which stands for Academic Research and Careers for Students, is the rebranded avatar of the long-running IRIS Symposium. Its objective is to provide an opportunity for our research students to showcase high-quality work published in top international fora to a conclave of researchers and potential employers. Further, recently graduated researchers share their PhD experiences and the professional life thereafter. In tandem, we also have distinguished senior researchers present their celebrated work to serve as role models for the student audience. The PhD clinic, on the other hand, facilitates research students, especially those from developing institutions, to obtain inputs and advice on a sustained and one-on-one basis from expert mentors in academia and industry. This program has caught the popular imagination, with over 100 students enrolled in the program being guided by 30+ mentors. The linkages set up by the clinic are augmented with a program called Anveshan Setu, which is the Hindi phrase for research bridge, that supports month-long in-person visits of these students to the mentor's institution. In collaboration with our sister organization, IARCS, which is the Indian Society for Computing Research, we have provided for several years student travel grants to premier international computer science conferences. But in the past year, the support has been primarily in the form of registration fees due to conferences going online. Finally, ACM India is a prime mover behind most of the top Indian conferences, including COTS COMAD in data science and ISEC in software engineering. And these have been conducted in collaboration with their respective SIGs. Further, we recently hosted a very large data engineering conference with our new institutional partner, Huawei. Turning our attention to the pedagogical front, ACM India is involved in a spectrum of activities that range from school education all the way to professional upskilling. For instance, several schools for senior undergrads are hosted in the summer and winter breaks. Each of these schools runs for a couple of weeks and covers a contemporary topic, leveraging expertise from both researchers and practitioners. Some of the recent areas that have been covered include shape modeling, natural language processing, and quantum computing. We have also had exclusive women-only schools on IoT systems and cybersecurity. In association with I6CSE, we held Compute, our flagship education conference last November, with a special focus on creative research in computing education. CS Pathshala and Pathshala is the Hindi word for school, is a long-standing grassroots effort to inculcate computational thinking in school children, especially in underserved areas. Our volunteers have interacted directly with thousands of students in multiple states and several different languages, and hosted programs at hundreds of academic institutions. The impact of the work is indicated by the fact that the annual CTIS conference, that is Computational Thinking in Schools conference, attracted more than 1,100 participants. During this year, we also helped midwife 2 faculty-oriented programs and got them off the ground. The first is a teaching partnership program where subject experts jointly teach courses with local college teachers in the classroom. And the other, CS Edu, is a certificate program where leading experts communicate the best pedagogical practices to aspirational faculty in core computer science areas. While ACM India, not surprisingly, has traditionally had a dominant academic flavor, we have now tried to actively pursue a better balance by bringing in a strong industry presence across the board in all of our programs. Google, Icertis, Persistent, and TCS have been our long-standing and highly valued platinum partners, while Cisco is a silver partner. We are delighted to report that this year, IBM and Huawei have joined as gold partners, while Facebook has come in at the silver level. Apart from the monetary support, we are also leveraging the technical strengths of our partners. As previously mentioned, we had a very large data engineering symposium with Huawei, and now a quarterly webinar series has just begun with TCS Research. Despite the pandemic and the consequent industry downturn, the good news is that thanks to strategically focused efforts, we have still managed to obtain a healthy funding of over 10 million Indian rupees, roughly equivalent to 135,000 US dollars. We share a symbiotic relationship with ACMW, as Hemant already mentioned, with the common objective of empowering women in all spheres of computing. ACMW conducted a variety of programs over the year, including programming hackathons, women-only schools, and a workshop that happened earlier this week. They also organized AICWIC, which is a platform for women in technology to showcase their innovation and ideas. Finally, the grad cohort workshop, a program which is inspired from its US counterpart, unfortunately could not be held last year, but we will be making amends by organizing it in IIT Jodhpur later this summer. A new scheme that has been implemented is the option of environmentally friendly mementos for those who have provided service to ACM India. In particular, we have signed up with 14tree.org, which was initiated by a group of computer scientists to have trees planted in their names. The reason for the number 14 is that this is the estimated number of trees required to compensate for each human's carbon dioxide output over their lifetimes. Currently, the trees are being planted in the Pune area, and hopefully we can all visit there someday in person after the pandemic. We have received very positive response with most of our conference speakers choosing this mode, and it will soon be extended to our other programs as well. A picture of the first set of saplings that have just been planted last month is shown on the slide. We have excellent news with respect to recognition. For starters, 4 of our members have been appointed to international ACM positions. Mayur to the Bytecast Committee, Hemangi to the Diversity Council, Hemant to the Practitioner Board, and Yogesh to the Distinguished Speaker Program Committee. Also, Manish Gupta of our council was featured both in the People of ACM interview and in the Tech Talk series. Secondly, we have had exceptional success in the higher grade nominations. As many as 7 distinguished member and 2 fellow nominations have gone through, and their names are listed here. We are particularly delighted that 2 of our own council members, Supratik and PK, feature in the distinguished member list. The committee of fellows that we set up last year played an active role in identifying and mentoring these successful nominations, and I would like to place on record our gratitude for their support. Just to put their efforts into perspective, in earlier times, we had roughly one successful higher grade nomination each year. Whereas just this year, we have had close to 10 successes, representing an order of magnitude improvement. You may recall that last year we set up 3 new professional awards: Outstanding Educator, Outstanding Woman Contributor, and Early Career Researcher. And this year's recipients of these awards are listed here. We have also increased the number of student chapter awards to reflect achievements on a variety of dimensions, and the prize-winning chapters are broadly spread across the country. Finally, our flagship doctoral dissertation awards have also been announced, and the recipients made presentations on their thesis work in the ARC Symposium yesterday. Our hearty congratulations to all the awardees. These recognitions will be formally presented in the award ceremony, which will be held in a few hours from now. So overall, we have certainly made visible progress over the past year, but plenty of work still remains. And here are some of the areas that we plan to focus on in the remaining months of our tenure. Most of our membership continues to be from developing institutions and smaller towns, with our footprint being worrisomely weak in the premier schools and in metro cities. And we absolutely need to change this lopsided profile. We are also working on setting up data collection initiatives on a variety of student and institutional aspects to help guide our future programs. On the flip side, we have started working on crafting position papers to influence government and educational policy on issues such as cybersecurity and digital currencies. Finally, you may recall that a ACM special section on the India region was published in November 2019. The second edition of this issue is currently being formulated and will appear in print by the end of the year. Due to paucity of time, I have only covered some of the highlights here, but I hope you found this brief overview of ACM India and its programs to be informative. I now hand it back to Hemant for introducing the address by the ACM president. Thank you.
Thank you, Jayant. So as Jayant said, this is just a non-exhaustive account of what all we have been doing at India level. And now it's my great pleasure to again welcome Professor Gabrielle Kotsis, who's president of ACM. But her involvement and her engagement with ACM goes back a long way. She is a distinguished member of ACM, and in fact, she's founding member of ACM Europe Council. She's professor at the Johannes Kepler Universität, Linz, Austria, and PhD from University of Vienna. As you can see, her PhD dissertation was honored with the prestigious Heinz Zemanek Award. But even before that, her master's thesis also, I believe, received the Austrian Computer Society Award scholarship. So we are very pleased to have you, Gabrielle. We know that you were very keen to attend in person. And of course, we were keen to do this in person. I know you love India. I believe you spent a month in IIT Madras as a researcher. And we all were looking forward to you being here, but hopefully that opportunity will arise someday. So welcome to this session again, to this event, and over to you to talk to us about ACM in general.
Thank you very much for this nice introduction. And yes, indeed, I spent 1 month of a sabbatical in India while doing my habilitation. And I truly would love to come back soon to enjoy the beauty of the country and the richness of the culture. I have to admit, I especially fell in love with the South Indian cuisine, which is truly amazing. You can do so many great vegetarian dishes, and I took home a heavy cooking book from India, and sometimes I'm preparing Indian dishes on my own. So I really like to come back again. Maybe you can insist that on the 23 ACM India annual event, the past president must attend. That would be nice.
We will.
So for my address today, I would like to start with congratulating really ACM India for all the achievements and success that you have been able to accomplish in these past years. I think it has been especially challenging because of the pandemic situation. But even without the pandemic, I do know, as you heard from my own experience, how important it is on the one hand to motivate the members of an academic, scientific, also professional community to really contribute. And I think the officers of ACM India are doing a great job here. It seems that all your 12,000 members are very active and contributing to this success. As you can see from the slide, and Jayant also has mentioned this, 2022 is a special year for ACM. We are reaching a major milestone, and our logo already reflects this. ACM turns 75 years old this year. So ACM, the Association for Computing Machinery, thus was established in 1947 by a small group of researchers that were interested in computing machinery. And in the 75 years since then, ACM has grown to more than 100,000 members worldwide in 190 different countries. In terms of our global impact, we serve more than our member community. We serve nearly 4 million researchers, practitioners, educators, and students through our technical and educational resources. ACM today is the world's oldest and largest computing society, and the field of computing has grown from that interest by a few people in 1947 to being a part of virtually every aspect of our lives today. ACM's activities remain true to the original vision. As it is written in the founding, and I'm quoting here, the association is an international scientific and educational organization dedicated to advancing the art, science, engineering, and application of information technology, serving both professional and public interests by fostering the open interchange of information and by promoting the highest professional and ethical standards. Throughout 2022, ACM will be celebrating the growth of ACM as well as the growth of computing. We will be highlighting ACM's role in facilitating technical excellence, fostering communications and collaborations, and supporting professional growth in computing. Please follow our ACM social media posts on Twitter and Facebook throughout the year to learn about these growths in our profession.
Gabriel? Okay. Yeah.
Over
Now
the
we're seeing
years,
the second slide.
no.
Yes.
Over the years, ACM has developed a set of core values that guide the services, products, and activities of the organization. These core values are technical excellence, education and technical advancement, ethical computing and technology for positive impact, diversity, equity, and inclusion. And you can see that these core values are directly reflected in ACM's strategic goals that we defined when I became president for the coming period 21 to actually a little bit longer, 25. I'm not going to read all of them. You can find this information on the website. I would like to just mention some highlights. I think the most important goal would be to make the ACM Digital Library fully open access, to increase again the visibility of the research results, and to open our results as a community also to a wider audience. I think that's a very important goal. And I also would like to emphasize the last impact. We are living in really challenging worlds. Technology can do a lot of benefit to humankind, but there's also a lot of risk and potential for harm and misbehavior, both within the society, but also by means of the impact that our technology makes. So therefore, promoting ethical computing to make a positive impact across the global computing community is another important strategic goal. I will be in my talk addressing some of these in more detail. To let me begin, I would like to tell you something about the ACM community. As you heard, the heart is our 100,000 global members. But there are many other people around the world that use ACM products and services and participate in our activities. As you can see, there are hundreds of speakers and award recipients each year. In addition, we have 10,000 volunteers each year who drive ACM activities. And by largest group in the communities, those who use the ACM resources, for example, the readers of our digital library, not all of our readers, of course, are members of ACM, the listeners to our Byte podcasts, the viewers of ACM talks, but maybe even also now, right now, the viewers that watch this stream of the ACM India event. I will go into detail about some of these activities now. So let me start by talking a little bit about what ACM actually do, and I would like to distinguish here services for practitioners and researchers. The computing profession is very diverse, which means that also we as a computing society have to provide a variety of products and services. And you see here on the slide just a more or less random selection of some of our activities. For example, SIGGRAPH conference. The SIGGRAPH conference in 22 is one of the major ACM conferences for both researchers and professionals working in the field of visual art. And as I've said in the beginning, our target audience here is not only the computing scientists and professionals, but also a link to artistic people, to the creative industry. And ACM is not only sponsoring this conference, but nearly 200 conferences all over the world on related topics. You can see on the upper right a photo of our Crossroads magazine, XRDS, which is the ACM publication related to our educational efforts. You can see on the bottom left a screen of one of the recent tech talks on Kubernetes systems about automating aspects of software deployment. Tech talks are ACM's offer dedicated mainly to practitioners, which are mainly software engineers, but others who develop and apply technology. And last but not least, you see on the bottom right a cover from our communications of the ACM magazine, which is the flagship magazine of ACM. And this was a special issue, that's why I picked this picture on the research work done in India. And hopefully many of you will recognize this special issue. And I would like to mention that also for CACM, there will be some significant changes in the coming years. Because of a regular change in terms, there will be a new editor-in-chief appointed starting from next year. And I can already tell you some of the plans are to, in addition to the printed magazine, move more also to online material so that we can inform you even quicker about work that has been published and that is of relevance for the community. Let me mention a few more services that we have. So for the practitioners, we do have, of course, communications of the ACM with several interesting articles dedicated specifically to keep practitioners up to date on what is happening in the profession. Then we have ACM's Q magazine, which was created specifically for practitioners, and it provides the latest information about software engineering and gives practitioners practical information useful for their jobs, or hopefully useful for their jobs. Q is a free and online magazine, and on the slide you can find the URL where you can retrieve all the information from Q. Tech Talks are a fabulous webinar series addressing professional needs. While it was started for practitioners, many researchers and educators also find these talks extremely valuable. Again, these talks are open to everyone, and you can see the web address for these talks where you find out about upcoming talks. You can also see 3 archives of the previous talks. All the webinars are recorded and archived, so you can watch them at any time. In addition to those materials that are open, we have several materials that are dedicated to members only, including training resources or online books. And for both members and non-members, there is the new Bytecast podcast. You can find these podcasts at the address again given here on the slide, or wherever you usually get your podcasts if you subscribe our channel. The podcast series is hosted by Rashmi Mohan, who many of you will remember from her years serving on the ACM India Council. What does ACM do for educators? Educators are another important target group, of course, that need to be served well. And we have a large number of curricular offerings, and you can see just a few on this slide here. Again, these are free and available at the URLs shown on the slide. And again, for members, there's additional material, training resources, online books, etc. Specifically for student members, we have designed the magazine that I've already mentioned, Crossroads, which I truly love, and that has a lot of great content written specifically for students. So if you're a student, I truly encourage you to go and check out the interesting materials in Crossroads. And for student members, there's also career news, which comes out in regular emails. So if you're a member, then you will receive this information directly into your mailbox. Last but not least, what does ACM do for researchers? Well, all of you, I'm sure, know our conference and workshop series that give you the opportunity to actively participate, to share your research ideas, but also to benefit from the research work as others. There are travel grants to conferences and workshops. There are publications, journals, and conference proceedings. And last but not least, there's the digital library that is a major activity for ACM. So I would like to spend a little bit more about the digital library. In the past, the digital library was mainly a repository for printed papers. So there would be the printed versions of the proceedings, and in the digital library, there would be the online counterparts. Over the years, and this is still an ongoing process, the digital library is transforming more into an active resource that help you do your research. Some of the ACM publications don't appear in print anymore, so you will only find them online in the digital library. But apart from being a repository, it's also a new way of publishing. And I would like to mention a few highlights here. First of all, one of the major things authors really want is to get their papers published as quickly as possible. We are working in a field that requires our results to be disseminated quickly because things are changing so much, and papers that have been written 20 years ago probably are not that relevant anymore today, apart from a few seminal papers. So it is always frustrating when you hear of large publication pipelines and lags that delay the publication of our work by a year or more after it has been accepted. To address this need, we have recently introduced the Just Accepted for journal articles. If you go to the digital library, you can see this as a new tab. It is marked with the red circle on the slide. And with the Just Accepted articles, they will be published online within the days of their acceptance, ahead of the printed version appearing in the various journals. They still go through some copy editing, get a DOE, and then they are immediately published online. And you can see here how that looks in the digital library. Another important thing, in my opinion, is that the digital library is not only a repository for global publications, but also allows authors to create their authors' profiles. So this is an enhanced functionality that we're going to build up. You can now edit your own profile. As you can see here, if you're logged into the digital library with your access, then you can claim your publications. You can even add publications that are not correctly linked to your profile. And if you have access to the digital library, just log in, click on the upper right that you see circled here in your screen, and then you can get started with updating your author profile. So you can add a picture, you can add some information about you. Of course, this doesn't mean to replace your personal individual homepage, but for publications, this will be a valuable source in the future. And we are planning also to include more features about statistics of access and all those things. And as I said before, in the past, it was mainly papers, but now we are also changing to other types of material, like, for example, software, data sets, speaker videos, poster presentations. All these new types of content that we are working with will also be in the future more an important part of the digital library. I think I should come to an end because we are reaching the end of our session, and I see Hemant already joining again. Just a few words. We also try to give back to the profession, like, for example, with the ACM Code of Ethics and Professional Conduct that many other societies and institutions are adopting. We do have our awards program, the speakers program, the Diversity, Equity and Inclusion Council, which is a very important activity, and also policy-related statement and position papers that might help the community to bring forward their arguments. Last but not least, I would like to conclude with again mentioning the celebration of the 75 years of ACM. There will be a celebration event in June, on June 10, and the day before our official annual ACM Awards banquet. We truly hope that we will be able to have this event in person. And I personally hope this very well, because my term as a president will end by end of June. And because of the pandemic, hopefully this ACM celebration will be the first event that I can attend in person as an ACM president. So far, I only have been attending virtual meetings. Unfortunately, and for sure, this will also be the last event that I will be attending in person as an ACM president. But of course, I will join the community in future meetings in several other roles. So thank you very much for your listening to me, and I hope it was a little bit inspiring, and I'm truly looking forward to the remaining talks of the end of the day. Thank you very much, and congratulations again for not only setting up this great event, but for all your activities during the past years.
Thank you very much. Yes, and I think every time I look at it, every time we all look at it, it's always inspiring, motivating for us to contribute more and more to this professional society called Association of Computing Machinery. So thank you again, Jayant, Gabriel. Gabriel, I know that this is early morning for you, but I hope whichever sessions that you can attend, you will be able to continue doing that. And of course, we'd love to welcome you again for the awards session, which happens in the evening India time. So we'll see you that time again. We do have a couple of minutes. So if there is anybody who has a question or something, they could ask. Otherwise, I think we have 3 minutes before we have the next keynote talk by Dr. Manik Verma. So anything else, Jayant, you want to say, or Gabriel?
No, just wanted to thank Gabriela again for being such an inspiring resource for us and for supporting us in our activities for the past 2 years officially. And I'm sure she'll continue unofficially after this as well. And we still owe her a visit to Madras, or Chennai, as it's now called. Right.
Yes.
So, right.
And of course, having heard about the activities of ACM, whether globally or in India, I don't think this session will be complete until we invite people, those who are not members of ACM, to become members. Whether you're a student, whether you're a professional, just go to the ACM site or ACM India site, india.acm.org, and you can't miss the membership tab. So I invite all of you to become members and to come forward, contribute. So I think
Yes. May I add just a small sentence to that? Because you heard in my talk, I have been mentioning that many of the services that ACM is offering is actually free for everyone.
Absolutely.
So I'm frequently asked, why should I join ACM if all what I could get is for free? And my answer is always, because it's not only getting, it's giving. If you're a part of ACM, then you can be part of the community and you can actively bring in. And I think you are all excellent role models for that. For me, at least, it was very rewarding to be part of the society and to be active and to contribute and not only to consume. So this is always my answer when people ask, why should I join? Because you want to be part of it and you want to act.
Absolutely. Couldn't agree more with you. The joy of giving is always more than joy of receiving and getting something. Absolutely. Thank you very much. And back to the organizers now.
Very thank you to Dr. Pandey, Professor Jain, and Professor Gabriel. We now have a keynote lecture for which I now call upon Professor Jain to introduce the first keynote speaker of the day, Dr. Manik Verma, to talk on the topic, a Turing test for recommendation. You can now proceed.
Okay. Yeah. So am I audible? Yeah.
Yes.
Yeah. Right. Good afternoon to all the Indian participants, and good whatever to everybody in the world. Welcome to the first keynote lecture of the ACM India Annual Event 2022. We are starting on a high note with a presentation by Professor Manik Verma, one of the most visible stars in the Indian machine learning firmament. Manik received his undergraduate degree in physics from St. Stephen's in Delhi, and then went on a Rhodes Scholarship to Oxford, where he obtained a PhD in engineering in 2004. He then returned to India, joining the Microsoft research team, where he has risen to the senior position of partner researcher. Manik is also an adjunct professor at IIT Delhi. Manik is recognized as the founder of extreme machine learning, a thriving field which has had very significant industrial impact. It has also led to premier scientific recognition through the Shanti Swarup Bhatnagar Prize in 2019, as well as fellowships of the Indian Academy of Engineering and the Indian Academy of Sciences. In today's lecture, Manik will propose a grand challenge for the research community in the form of a Turing test for recommendation, and we fondly hope that our audience will be catalyzed to take the lead in solving this intriguing problem. During the talk, you are welcome to enter your questions on the Q&A or chat channels, and these will be handled online by Manik's close collaborators. And then there will also be a live Q&A session directly with Manik at the end. So with that brief introduction, welcome and over to you, Manik.
Thank you so much, Jayant, not only for that very generous introduction, but for also inviting me here to speak today. Am I audible and is my screen visible?
Yes, we can see this perfectly well. Yeah, thanks.
Okay, great. And again, thank you so much for introducing Purushottam and Deepak. So my colleagues, Purushottam Kar, Professor Kar from IIT Kanpur and Deepak Saini, they will be responding to all your questions and clarifications on the chat. And of course, once the talk finishes, I'll be delighted to take your questions later on. Okay, so let's get started. I'm Manik Varma from Microsoft Research India. And I'll be in my talk today, I would like to propose a Turing test for recommendation, which I hope can become a grand challenge for the community in some sense, right? And my hope is that it might inspire some of you to tackle some of the research challenges that the test gives rise to, and thereby not only advance science, but also benefit society, right? So, Jayant, I'm having some trouble, I think, over here. Is it okay if I switch off my video?
Yeah, that should be fine. We can hear you perfectly well, so that should be good enough.
Are the slides visible?
Yeah, we can see this, the first slide with the Turing test for recommendation and your name at the bottom.
Okay, great. So I'll just ask my daughter to turn the slide, the screen off. Just 1 second.
Yeah, you're on mute, Manik, still.
Can you unmute me better? And is the screen video off? Okay, and am I unmuted?
Yeah, we can hear you now, Manik.
Okay, great. Thank you so much, guys. As I said, I'm sorry, I'm blind and I sometimes have all of these issues. So thank you for your indulgence. Okay, great. So let's get started, right? So as I was saying, I would like to propose in my talk today a Turing test for recommendation. And hopefully this might become, let's say, a grand challenge for our community, right? And my hope is that this might inspire some of the students to tackle some of the problems that the test gives rise to, and thereby not only advance science, but to also benefit society. So the original Turing test was proposed in 1950, and there have been many variants over the years, including one by Feigenbaum in 2003, who thought of the Turing test as perhaps the grandest of all grand challenges in computing. So Feigenbaum conjectured whether a machine could ever imitate a human domain expert at conversation. So the test starts out with the interrogator choosing 3 topics from a pre-selected list on which certain mild and reasonable restrictions have been placed. The world's foremost domain experts on those topics are then identified and brought into a room one by one, where they're isolated from the interrogator, while the machine is kept in yet another isolated room. The interrogator then converses with both parties via a terminal and has to decide which party is the human domain expert and which party is the machine. Now, note that this is a purely subjective judgment call based on the interrogator's own training, experience, intelligence, and current mental and emotional state. And therefore, 2 interrogators could reach very different conclusions given exactly the same conversation. Therefore, this imitation game is repeated multiple times until statistically significant results are achieved. Now, the machine wins the Turing test only if it can fool the interrogator into thinking that it is the human more than 30% of the times. Now, note that while the interrogator's original judgment call might have been purely subjective, the fact that whether the machine won the Turing test or not is completely objective. In fact, we can make very precise statements. For example, we can say that 100 rounds were played and the machine won 31 rounds out of these 100, and therefore it barely managed to pass the Turing test. Now, our proposed version of the Turing test is very similar to the original, but just specialized for recommendation. So the test starts out with the interrogator once again choosing 3 topics from a pre-selected list on which certain mild restrictions have been placed. In particular, we require that information on these topics be either publicly available on the internet or can be found using publicly accessible technology by both the human domain expert as well as the machine. Next, the interrogator requests recommendation advice, such as what might be an ideal birthday gift for their partner. And then both the machine and the human domain expert are allowed to gather whatever personal details the interrogator is willing to reveal. Then the recommendations of both the machine and the human domain expert are anonymized and placed side by side in front of the interrogator, who once again has to make a subjective judgment call as to which recommendations are better. So for example, the interrogator might decide that the recommendations on the right-hand side are better because they are more delightful and surprising, or because they're more accurate, or because they are more useful and actionable, or whatever the interrogator prefers. If the interrogator is unsure, they can ask for an explanation, or they can try out both recommendations before deciding. Now, the machine wins the round only if the interrogator feels that its recommendations are better, and it loses the round if the interrogator continues to remain unsure or prefers the recommendations of the human domain experts. The machine wins the overall tournament only if it wins more than 30% of the rounds, as was the case in the original Turing test. Or if we feel that this bar is too low, then we can set it higher to 66%, 80%, or whatever we think is appropriate. Now, our proposed Turing test for recommendation has the following properties. First, it is very easy to state and can be and is completely objective. Second, it can be verified publicly because the test can be broadcast live on your favorite TV channel or whatever you like, wherever you like to watch Who Wants to Be a Millionaire or Kaun Banega Crorepati. And third, if we could actually solve this problem, then we could potentially benefit billions of people around the world by providing them expert level recommendation advice and making it accessible to them on their fingertips. Okay, so at this point of time, some people ask me, but hey, wait, Manik, why is this a grand challenge? Isn't recommendation a solved problem? In fact, hasn't recommendation been a dead topic of research ever since the Netflix challenge was won more than a decade ago? Haven't all the best recommendation algorithms already been developed and all the research challenges solved? And so my answer to all of them is an emphatic no, because the Netflix challenge was won at the scale of a few thousand movies and a few million people. Whereas if we are really serious about tackling the proposed Turing test for recommendation, then we will have to make perfectly personalized and highly accurate recommendations for the billions of people around the world who could potentially act as interrogators. And if we have to guarantee accuracy, we will have to index the entire world containing trillions of items, because an interrogator might request any piece of information that, or any item of information that is publicly available on the internet. At the same time, because these recommendations will need to be provided in a timely and accurate manner, we will have to reduce our computation, storage, and communication costs by orders of magnitude. But if we can do this, then I guarantee that even Netflix will improve, as will all the search and recommendation applications that you use daily. In fact, completely new recommendation scenarios will open up. For example, if you were looking to buy a pair of chunky headphones, let's say on the internet, then your web browser could recommend to you, why don't you try bone conductance earphones instead? Because they don't even touch your ears. And that's because you have back-to-back meetings every day, due to which your ears are already starting to hurt. Similarly, if you were responding to a request for proposals for providing machine parts in a foreign country, then your document editor could recommend the relevant local laws, the preferences of the evaluation committee, and also pull up all the relevant documents, or let's say the previous proposals that had been successful from your company. So if we can really build a system like this, then it might have a transformative impact on the world, because providing accurate, reliable, unbiased, and personalized information in a timely and accessible manner is perhaps one of the greatest challenges that our world is facing today. So in the next 5 slides, let me briefly highlight some of the novel research challenges that the test gives rise to, starting from training the machine learning model, going all the way up to performance evaluation. And then in the second part of my talk, I will discuss some of these research challenges and how they can potentially be solved using extreme classification. But due to lack of time, I won't be able to go into the details of the other solutions that are being explored in my group. So I've just listed them over here briefly, and I'd be very happy to talk to you about them later on offline. Okay, so the first research challenge that we will face is that there will now be billions of rare items for which very little training data is available. Now, accurately training on these billions of rare items is going to be very hard, but it can also be very rewarding, because these rare items can delight and surprise the user who might not even know that they existed. So all the complexity and richness of extremely large scale recommendation arises from the complexity, the computational and statistical challenges that arise due to these extremely long tail of rare items. Excuse me, can people go and mute? There's a lot of background noise coming in from someone. So thank you so much. Right. So I was saying that a lot of these challenges arise due to the statistical and computational challenges that are posed by this extremely long tail of rare items. And in the second part of my talk, I will discuss some of these research challenges and see how we can use extreme classification to train a machine learning model that is accurate, scalable, and personalized. But unfortunately, again, due to lack of time, I won't be able to go into the details and discuss research challenges around multi-equality, explainability, robustness, fairness, and so on. Okay. Now, the next research challenge will be that once the ML model has been trained, then we need to use it to encode the representations of the trillions of items that we need to recommend. Unfortunately, running a state-of-the-art deep learning encoder such as BERT trillions of times can take many months, even on the largest available GPU clusters. So our next research challenge is going to be to design, So what I wanted to say is that this is going to take many months, and on top of that, this computation will need to be repeated every time the items churn or the models change. Right? So our next research challenge is going to be to design state-of-the-art encoders whose inference costs are orders of magnitude lower on GPUs, as well as design new encoders that can be run on FPGAs and CPUs that are, and because we have millions of CPUs that are lying idle in the cloud data centers. And at the same time, the ML model also needs to then encode the representation of the interrogator in milliseconds. So another exciting research challenge is to design new encoders that are even cheaper at inference time. So they have inference costs that are, let's say, 10 times lower than that, so that these encoders can be run on the user's idle edge devices or appliances, so as to minimize latency and enhance privacy. And if we can do this, this might enable new scenarios so that interrogators can receive hyper-personalized recommendations based on their very sensitive data and signals that never leaves their trusted device. Now, because, sorry, so we will also have research challenges based on efficient storage and retrieval, because when the interrogator comes in, their representation needs to be computed and then matched to the stored item representations of these trillions of items in milliseconds. Now, unfortunately, storing the representations of these trillions of items can take petabytes of RAM. Therefore, our next research challenge is going to be to design approximate nearest neighbor search or ANS algorithms for representation matching in milliseconds that guarantee 95 to 99% recall while storing all of these item representations on solid state drives. Further research challenges include designing novel ANS algorithms that can dynamically insert and delete items to support item churn, as well as designing novel ANS algorithms for programmable drives so that they can move the compute to the data for even greater efficiency. Now, since every system that gets built can't possibly be evaluated by real life interrogators, our next research challenge will be to design performance metrics that can be evaluated on offline test data. Now, it is extremely hard to design good metrics that can reliably predict what the system will perform, how the system will perform when it goes live. And to compound the problem even further, we need to design multiple such metrics so as to cover the diverse facets of interrogator satisfaction and system costs. And even if you could design all of the right metrics, you might not have all the right data available at test time. So for example, you might not have any labeled data available in the Gondi language. So how would you ever know how your system would perform if it goes live and you get a Gondi speaking interrogator who wants items of information in Gondi recommended to them? And of course, our proposed Turing test for recommendation also raises many fundamental problems in theory. For example, as this graph shows, the amount of training data that we can gather per item grows only logarithmically. Okay? So therefore, can we design algorithms whose test error is provably minimized when we train these algorithms on data that is just logarithmic in, say, the number of items on average? Similarly, can we come up with a theoretical characterization of fairness and use it to prove that the algorithms that we developed are fair for both users as well as items? In addition, it's very important to develop privacy-preserving recommendation algorithms with provable guarantees so that interrogators feel safe and they are comfortable sharing their sensitive data that in order to receive hyper-personalized recommendations, and they have trust that this data will never be leaked. Okay, so there will also be many other challenges, but we won't be able to discuss them today. And at this point of time, many students ask me, well, how can we work on some of these research challenges at these extreme scales, given the fact that we have access to limited resources? So in my experience, if you can work at the scale of Wikipedia or larger, then you can actually contribute to the Turing test and make progress. So to demonstrate this, let me now switch to the second part of my talk, where I will discuss potential solutions to some of these research challenges based on extreme classification. And this is work that has been primarily done by my PhD students at IIT Delhi using limited resources. Though, of course, for the largest problems, I tend to collaborate with my colleagues at Microsoft. Okay. So extreme classification is a new research area that my group started in 2013 and which lies at the intersection of natural language processing, information retrieval, machine learning, and systems, and which has also opened a new paradigm for thinking about key applications in extremely large-scale search and recommendation. Now, I suspect that some of you might not have heard the term extreme classification before, so let me start by giving some context. In classification, the complexity of the learning task has grown from binary classification, where we learn to pick a single item from two labels, to multi-class classification, where we learn to pick an item from more than two labels, to multi-label classification, where we learn to pick the most relevant subset of these labels. At the same time, the complexity of the learning task has also grown in terms of the number of labels being considered. So we've moved on from working with two labels for binary classification to working with tens to hundreds and even thousands of labels for multi-class and multi-label learning. And if you looked at the state of the art in 2012, then the largest publicly available multi-label data set had about 5,000 labels, which is quite large, right? Because the size of the output space is 2 to the power 5,000, which is more than the number of atoms in the universe. So going beyond that was considered very hard. Then in WWW 2013, we published a paper which exploded the number of labels being considered in multi-label classification from 5,000 to 10 million. The motivating application was to build a classifier that could automatically predict the relevant subset of millions of search engine queries that were being asked on the Bing search engine and predict which one of those might lead to a click on an ad or a web page. So what we wanted to do was to build a tool for advertisers such as Geico, so that when they created an ad like this, they could use the tool to figure out which queries might lead to a click on their ad, and they could then bid on these queries. And then if the query got asked on Bing and their bid was high enough, then the ad might potentially get shown depending on its relevance to the query. So as you can well imagine from the context of the application, predicting queries from web pages is a really important problem from both a commercial as well as a research perspective. And so many sophisticated natural language processing, information retrieval, and machine learning techniques have been developed in the literature. However, we decided to avoid all of these approaches and simply formulated the problem by taking the top 10 million queries that were being asked on Bing and by treating each one of them as a separate label in a multi-label classifier. So we learned a multi-label random forest classifier called MLRF, which took the ad as input and extracted a bag of words representation based on the underlying HTML that underlies the ad, and then simply classified that bag of words representation into the relevant subset of top 10 million Bing queries. Now, this was a completely new and very different way of thinking about the problem. And as a result, MLRF gave 5% higher precision and 40% higher recall as compared to all of the state-of-the-art methods that were running in production in Bing at that point of time. Okay, so as I mentioned, MLRF was published in WWW 2013, and it started the area of extreme classification, which deals with multi-class and multi-label classification problems involving millions of queries, millions of labels and beyond. And since 2013, extreme classification has come to be a thriving area of research in both academia and industry, with papers being published routinely in top-tier conferences and many popular workshops being organized. And if you would like to conduct research in the area, then we maintain the extreme classification repository of publicly available code, data sets, metrics, and benchmark results, which make it very easy for new researchers to come in and get started. So you might want to check that out. The other thing that has happened since 2013 is that we have come to the realization that extreme classification generalizes far beyond being a simple tool for advertisers. In fact, one of the most interesting questions to have come out of our research is when or where in the world will you ever have 10 million labels to choose from? Or what are the applications of extreme classification? Well, if you think about it, 10 million is a really large number. Even if it were to take you just 1 second in order to read out a label, it would take you almost 4 months without eating or sleeping or resting in order to go through a list of 10 million labels and to go through a list of 10 million labels. And to put this into perspective in another way, when I was doing my PhD in computer vision in 2000, we were told that according to Biederman's counts, there were only 60,000 object categories in the world. And so most of your traditional computer vision problems won't make the cut. Similarly, if you were to pick up the largest, fattest Oxford English dictionary, it would only have about 500,000 labels. And so many traditional NLP problems will also not make the cut. Nevertheless, people have found very high impact applications of extreme classification in diverse areas, ranging from information retrieval to recommender systems, and even natural language processing and computer vision for that matter. So in our talk today, we will primarily be focusing on applications in search and recommendation. And it turns out that many of these applications can be reformulated as extreme classification tasks by simply treating each item to be ranked or recommended as a separate label in a multi-label classifier. So to see this, suppose we had a space of users X and a space of items Y, then all we would need to do is learn a multi-label classification function F, which is going to take a point in the space of users and map it to a set of points in the space of items, so that when a user comes in, we can simply apply the classification function F, see which labels get predicted, and then return the items corresponding to those labels to the user, either as a recommended bag or as a ranked search list, depending on the application. So as you can see, many problems in search and recommendation can be reformulated as extreme classification tasks. And because of this, throughout the rest of my talk, I'm going to use the terms label and item interchangeably. Now, to see why this reformulation can be such a powerful idea, let's return to our ads recommendation application. So here is an ad that Amazon had created for distilled water. And as you can see that they're selling a Tesco's brand of distilled water and a few other brands as well. But unfortunately, they bid on only a single query, which is distilled water 5 liters. Now, the way that online advertising works is that this ad can only get shown on the search engine when this query gets asked. And because of this, the ad had been languishing in our inventory for more than 6 months without being shown even once. So what we would like to do in order to fix this problem is that we can now predict the set of search engine queries that might lead to a click on this ad, and then insert these queries into Bing's inverted ad index, so that if the query gets asked, then the ad can get shown automatically, even though the advertiser might have forgotten to bid on the query explicitly. Now, as I mentioned earlier, this is not a new idea. We were not the first ones to think of it. And in fact, Bing has an entire ensemble of 50 top-notch algorithms that are doing just this, predicting queries from web pages. And by and large, they do a good job, except when you come to this very long tail of rare items when they start having problems with precision and recall. So we can address this limitation by reformulating this as an extreme classification problem, where the input to our classification function F is going to be the content of this ad, and our labels are going to be the top 10 million queries being asked on Bing. So when you look at the results, you see that the traditional approaches have problems with both precision and recall, as I mentioned. So the recall is poor because they were able to recommend only one query, and the precision is poor because this recommendation turned out to be completely incorrect. Whereas extreme classification has good precision, good recall because it makes lots of recommendations, and the precision is also good because these recommendations are all relevant. And because of this, this ad has been shown to many users who have now been able to buy this distilled water and buy this ad, click on this ad and buy the water. And you can see from here, right, all our recommendations are relevant because we predict queries such as distilled water, whereby distilled water delivery, distilled water Tesco's, distilled water Amazon, and so on. Okay, so let me now take just a moment to reflect on why the traditional approaches did not work well in this case, whereas extreme classification did. And the high level intuition is that a complex machine learning model trained on a humongous amount of data can often outperform a simple ML model. So the reason that the traditional approaches don't do well is because they try and reduce the complexity of the problem by reducing it to a simple binary classification task. So they learn a binary classification function H, which takes both the add and the query or phrase as input, and simply predicts whether the query is relevant to the add or not. So once this has been trained, the binary classifier is then applied to all the phrases that appear as text on the add, and then it simply predicts whether that phrase should be selected as a relevant query or not. Now, unfortunately, ads are pithy and have very little text on them. And so this is going to lead to issues with recall, because by construction, the binary classifier can only recommend those queries that actually exist as a phrase on the ad. So it will never be able to recommend the query buy distilled water simply because it didn't occur as a phrase on the ad itself. At the same time, these binary classifiers were traditionally designed to be simple and have a very small model size because they had to run in milliseconds over all the phrases on the ad. And this led to issues with precision because we expected them to model billions of queries and billions of ads, and they would obviously make mistakes, such as what happens in this case when it predicts that water 5 is a good example or is a good query. So on the other hand, in extreme classification, we actually embrace the complexity of the problem by testing each ad against all 10 million queries. So we learn a hierarchy over the space of queries so that all 10 million queries are at the root node, but then all the fruit related queries go left and all the battery related queries go right. And once you've gone right, the battery and the engine oil go left while all the distilled water queries go right. So that when an ad comes in, we can walk it down this tree in logarithmic time so that in a matter of milliseconds, it reaches the right leaf node containing all the distilled water queries, even those that did not occur as text on the ad. And so this will lead to good recall. Then we can apply a very powerful multi-label classifier to just that leaf node. And this will allow us to accurately predict the subset of those distilled water queries that are relevant to this particular ad. And that will give us high precision. Okay. So our extreme classification algorithm for hierarchical classification is called Parable. And Parable is a probabilistic model which generalizes the popular multi-class hierarchical softmax loss function to the multi-label setting. And this gives it three distinct advantages over MLRF. First, if we consider the benchmark extreme classification task of categorizing Wikipedia articles into their relevant subset of Wikipedia categories, then in 2013, MLRF had a classification accuracy of 19% on this task, whereas Parable had increased it to 68% by 2018. Furthermore, many papers had been published on extreme classification by 2018, and many algorithms had been developed, including this one called DISMEC, which simply throws away the learned label hierarchy and learns a separate classifier per label using brute force training on thousands of CPU cores. Despite this, DISMEC was only 2% more accurate than Parable, thereby indicating that perhaps Parable's learned hierarchy might be near optimal. The second advantage that Parable had was it could be thousands of times faster to train, orders of magnitude. So while MLRF and DISMEC took more than 7,000 hours for training on Wikipedia, Parable could be trained in under 7 hours used on a single core of a standard desktop. Parable's third advantage was that it reduced the model size from the terabytes that were needed by MLRF down to gigabytes. So all of this combined really democratized extreme classification, because now anyone in the world could train an extreme classifier at the scale of Wikipedia on their desktop without needing access to very huge and expensive clusters. Because of this, Parable and many other extreme classifiers have been deployed widely in the tech sector, where they are benefiting billions of people and have generated very significant amounts of revenue for many small and medium businesses throughout the world. To take just one example, here are some of the products where extreme classifiers have been shipped in Microsoft products with significant impact and awards. Okay, so Parable, MLRF, and DISMEC were all examples of classical extreme classification algorithms that were based on bag of words representations that were handcrafted. However, by 2018, deep learning was starting to revolutionize computer vision and NLP, and handcrafted representations were being completely replaced by deep embeddings. However, deep extreme classification was proving to be a much tougher nut to crack. And if you looked at the state of the art of deep extreme classification, including leading algorithms from CMU, then they could be 10% less accurate than Parable while being 10 times slower to train. So then in late 2017, 2018, we started two projects to address these limitations. And the first one was using pre-trained deep embeddings to recommend related queries on a search engine. So if you submit a query to a search engine, it will often recommend related queries that might serve your information needs better, or it might recommend related queries that you could have asked in addition to get more information on the topic. So for example, if you go to Bing and ask it about CAM procedure shoulder, it'll recommend, why don't you try asking me about Cam Newton shoulder surgery instead? So this is known as the related searches problem. And it is a classical problem in information retrieval, as well as being a fundamental problem in NLP, where it falls under the bucket of sequence to sequence problems. And all of this means that once again, there has been decades of research leading to the development of many sophisticated algorithms. But once again, these algorithms can have precisions with both, can have problems with both precision and recall, as you can see from the screen snapshot. So these traditional techniques can have poor precision recall because, as you can see, there was space for making 8 recommendations, but they made just 1 recommendation. And once again, precision is poor because this recommendation turned out to be completely incorrect. So the CAM that the user was asking about it stands for the Comprehensive Arthroscopic Management Procedure, which is a very specific type of shoulder surgery. Whereas the traditional approaches got confused and thought that the user was asking about the shoulder surgery of the American football quarterback Cam Newton. So if you look at the traditional approaches to related searches, many of the leading techniques are based on sessions data, where the last query in a user's session can be used as a recommendation for all the previous queries. Now, unfortunately, this can lead to poor recall, because if you have never seen a rare tail query in your sessions logs, then you won't be able to make many recommendations for it. At the same time, if the user changes their intent between the first and last query in their session, then you can also have problems with precision. And the same is true for leading techniques based on other methods, such as the query URL graph, right? So techniques that are based on random walks or graph neural networks will be beset by the same precision and recall issues. So we can address these limitations by once again reformulating extreme related searches as an extreme classification problem, where this time the input to the classification function F is going to be the user's query. And this time the labels are going to be the top 100 million queries that are currently being asked on Bing. So our algorithm for extreme classification based on pre-trained embeddings is called SLICE. And when a user's query comes in, it is passed through a pre-trained text encoder, such as BERT, which has fixed model parameters to generate a vector representation of the user's query. This vector representation is then classified into the top 100 million queries on Bing by slice learning one versus all classifiers, one per label, exactly as was done by Dismec. Now, a quick back of the envelope calculation tells us that that if Dismec took 7,000 hours for training on Wikipedia, it would take millions of hours for training on related searches. So Slice addresses this limitation by reducing the complexity from linear to logarithmic in the number of labels. Now, at first, I thought it was impossible to have sublinear training complexity because you have to learn a classifier per label, right? So the complexity has to be 100 million. But if you just shift your perspective and realize that the vast majority of items are completely irrelevant for a given user and can be eliminated without even consideration, then Slice can focus on just the order log 100 million items that are going to be relevant to that specific user. So for example, for the query camp procedure shoulder, all the queries that are related to travel or retail or entertainment or luxury, all of them can be discarded as they're not relevant and we don't even need to consider them. So Slice leverages a state-of-the-art approximate nearest neighbor search or ANS algorithm called DISCAN, which was built by Harsha, Ravi, and Gopal in our lab to discard these irrelevant items for a given user in log time. So the way DISCAN works is that when a user's embedding comes in, it starts out at the root node, and then it keeps traversing the graph by moving closer and closer to items that are embedded closer to the user. And once it can traverse the graph no further, it returns the list of items that are embedded closest to the user on the traversed path. Slice can then focus both its training and prediction just on these shortlisted items and thereby have logarithmic complexity. So just by a very simple shift in perspective, we can now use Slice to recommend these rare tail queries in logarithmic time. So if you look at the results, then you can see that Slice is better both in terms of precision and recall. So recall is once again good because Slice makes 8 recommendations for the query. And precision is good because all of these recommendations are relevant. In fact, Slice covers diverse facets of the user's query by recommending what are the alternative types of shoulder surgery, what is the cost of an arthroscopic shoulder surgery, how much time to take off work after a shoulder surgery, and what is the success rate, and so on. Slice's results also indicate that Slice's offline accuracy could be 8% higher as compared to the leading techniques based on sessions data, the query URL graph, and other approaches that have been denoted over here by M1 to M6. Furthermore, when Slice was deployed in production, the number of queries for which recommendations were being made went up by 50%. The number of recommendations went up by 33%. And the quality of these recommendations went up by 12% for queries in the very long tail. And this was a critical improvement because many people had been trying to use traditional techniques to get far fewer gains without much success. And because of Slice, millions of users were now able to successfully complete their task quickly and effectively. Okay, so let's finally cover our second project on deep extreme classification, where we are going to learn the embeddings jointly with the classifiers rather than using pre-trained embeddings as was done in Slice. Now, the scenario is going to be that we will have billions of users who are browsing trillions of web pages and asking billions of queries. And based on this search and browsing activity, we would like to recommend billions of items, so make personalized recommendations. And of course, all of this will need to be done within the ambit of GDPR and other regulation for protecting privacy and data. And personalized recommendations should only be shown to those users who want to receive them. And users should be able to opt out at any point of time and have their history deleted. Now, if we are going to make hyper-personalized recommendations, then we need to infer the user's intent in an extremely fine-grained manner. And there are multiple ways of doing so. For example, given the fact that the user is browsing a particular web page, their intent can be represented by the set of search engine queries that they might have asked in order to reach that web page, as can be seen over here by these Bing queries for the Book P&O Cruises page. Now, this sets up an extreme classification problem where the input to the classifier is going to be the visited web page, while the labels are going to be the top million or billion queries that are being asked on Bing, depending on how fine-grained we want the representation to be. So this leads to an explicit representation of the user's intent, which is interpretable. An alternative would have been to train the extreme classification function F to directly predict the set of recommended items and to use the learned embedding as an implicit representation of the user's intent. Now, there are many ways that we can use this inferred user intent in order to show personalized recommendations to the user. So to take just one example in the explicit setting, we can select the most relevant query predicted across all the web pages that have been visited by a user in their session, submit that selected query to Bing, and then show personalized recommendations based on that query to the user. As you can see over here, when we selected the query Book P&O Cruises from their first web page and then showing ads based on that. So we are showing deals for cruises based on this. Of course, there are many other ways to do this, and one doesn't always have to go through a search engine in order to make these personalized recommendations. Now, in order to deploy our solutions to many people across the world, we had to support millisecond level latencies as well as throughputs of more than 150,000 queries per second in order to make billions of predictions per day. And we needed to do this by using some CPUs that we had lying around spare rather than using dedicated FPGAs or GPUs. And we wanted to get these low latencies and high throughputs without any loss in accuracy. In fact, we wanted to get significantly higher accuracies as compared to all the state-of-the-art recommendation techniques based on deep learning that were out there. So state-of-the-art deep learning techniques for recommendations are based on Siamese networks, where we train a leading neural language representation or NLR text encoder using a contrastive loss function to embed users close by to the items they like and far away from the items they dislike. Recommendations can then be made by simply retrieving the items that are embedded closest to a user through an approximate nearest neighbor search algorithm such as DISCAN. Now, large recommendation models have been generating a lot of excitement and interest. They have become more and more accurate by becoming larger and larger. And there is a sense of anticipation in the community that one day we might be able to learn an NLR model so large that it can match human performance. At the same time, there is also growing concern that these NLR models have very, very high training and inference costs, right? And these are becoming prohibitive because their training and inference costs go linearly with the number of model parameters. For example, if we were to just restrict ourselves to the English language for a moment, then the Turing NLR V5XL model is one of the world's largest English language dense NLR models that has 1.5 billion parameters. Now, pre-training this Turing model can take up to 3 weeks on a cluster of 256 A100 GPUs. Now, you might potentially forgive this because this is a one-time cost, right? But fine-tuning this model on a slightly different version of our recommendation dataset can take yet another 3 weeks on 3 A100 GPUs. Perhaps even more importantly, using this Turing model to make even a single prediction can take 177 milliseconds, which is unacceptable given the fact that we have to make billions of predictions a day. So these very large NLR models are compressed and heavily distilled down to much smaller models, such as this 35 million parameter twin-BERT model, using state-of-the-art techniques so as to meet the latency and throughput requirements of our online real-world applications. Now, in terms of the accuracy of these fine-tuned recommendation models, you can see that it indeed increases from 35% to 45% as we use larger and larger Siamese NLR models, but then it plateaus out, and then heavy compression and distillation down to twin-BERT can lead to a significant loss in accuracy. So we can fix this problem by once again turning to extreme classification. Because extreme classification generalizes Siamese networks by learning an extra classifier per item in addition to the base Siamese NLR encoder. Thus, if we were training on 1 billion items that had been encoded in a 1,000-dimensional space using the Turing encoder, then our extreme classifiers would have 1 trillion extra parameters over and above the Turing model. So as a result, extreme classification can learn much larger models as compared to Siamese networks. And this can lead to significant accuracy gains by bridging the semantic gap between the user's text and the item's description. So, for example, the Siamese NLR encoder, the embeddings that it generates are constrained by the item's text, right? Whereas the extreme classifiers are unconstrained and are free parameters. So to see how this can be helpful, let's consider a pathological example where we have 3 very different items which have the same item text, which is Turkey. So one item represents the country that was formerly named Turkey. The second could represent the bird, and the third could be a representation for the food, right? And now the Siamese NLR encoder will generate exactly the same or identical label embedding for all 3 items, whereas their classifiers could be very different and could be tuned for the different users who want these items recommended to them. At the same time, extreme classification can be much more scalable because its training and inference costs grow only logarithmically with the number of labels rather than linearly. Therefore, we can get both accuracy as well as scalability by learning an extreme classification model using a small base Siamese NLR encoder such as distilled BERT, which gets us as close as possible to the 45% accuracy mark while being within all the throughput and latency constraints, and then shifting the bulk of the parameters into the huge classification layer that follows after the distilled BERT encoder. So when we learn an extreme classification model like that, we see that the classification accuracy jumps up from 45% to 60%, while the training time comes down from 3 weeks to just 1.5 days on 3 A100 GPUs, out of which 32 hours are spent in training the distilled BERT encoder, and only 3 hours are spent in training the extreme classifiers. And prediction time also comes down to just 4.5 milliseconds per test point on CPUs. No GPUs are required. Now, our extreme classification algorithm that generalizes Siamese networks is called Endgame, and it came out of the deep XML framework for deep extreme classification, which we've been developing for the last 4 years. So deep XML decomposes the extreme classification task into 4 simpler subtasks or modules, each of which has log time complexity while still being very accurate. So now we can develop many different algorithms from this deep XML framework by just plugging in various off-the-shelf components into the 4 deep XML modules in order to address the requirements of these various applications. So this makes deep XML very flexible and very powerful because we can now get state-of-the-art accuracies on diverse recommendation applications by making only minor modifications to the deep XML pipeline. And we don't need to start from scratch each time or go back to the drawing board for each application. So in module 1 of DeepXML, you can plug in the feature encoder that is going to be the most appropriate for your application and train it using Siamese contrastive learning or any other loss function of your choice. Now, in this talk, we've been focused on NLR encoders that are text-based, but you could easily have used visual transformers for images or any other encoder that you like. So module 1 corresponds to your basic Siamese network training. Then in module 2, you can plug in your favorite approximate nearest neighbor search algorithm to reduce the complexity from 100 million items to order log 100 million by eliminating the vast majority of items that are going to be irrelevant to each user, to a given user, and that don't even need to be considered. Then in module 3, you can plug in any leading transfer learning technique that will transfer the features from module 1 and fine-tune them for recommending these 100 million items, order log 100 million items that have been selected per user. Finally, in module 4, you can plug in the item classifiers that you like, slice or parable or whatever else, and have them be trained to predict these order log 100 million items based on the user's representation that was learned in module 3. So this gives us a framework that is very flexible and powerful, and that is not only highly scalable, but also very accurate, and which we have used to develop many algorithms, including Endgame. So when we deployed these DeepXML algorithms into production for making personalized recommendations, we saw that the click-through rate went up by 30%, and the number of excellent matches also went up by 21%, which is a very significant gain. Finally, on returning to Wikipedia, we see that the community has made a lot of progress on deep extreme classification since 2017. And now, thanks to DeepXML and Endgame, our accuracy has now crossed 85%, whereas the classification accuracies of these classical XC models and large NLR encoders is still hovering somewhere around 70%. Furthermore, depending on which algorithm in DeepXML you choose, our training time is just between 7 hours and 70 hours on a single V100 GPU, which should be accessible to most students. Okay, so I'd like to conclude by reiterating that extreme classification is a new research area that not only lets us tackle web scale classification problems, but which has also opened a new paradigm for tackling key applications in extremely large scale search and recommendation. Now, our group has developed many algorithms for tackling some of these applications, and their source code can be found on the Extreme Classification repository, and you can go and check them out and download them and play with them and give us feedback. And I hope that some of these algorithms will also take us a step closer towards solving this proposed Turing test for recommendation. And of course, none of this would have been possible without the immense contributions of my colleagues and collaborators, whom I would like to thank deeply. And also thank you very much for listening so patiently. That's all. Thank you.
Thank you, Manik. On behalf of the audience, it was a fascinating presentation on a really exciting topic. I didn't see any questions as yet on the Q&A or chat, but maybe those of you in the audience, who I'm sure you now have a lot of questions for Manik, and you could either unmute yourself if you're a panelist or put it up on the chat channel, and then we can convey those questions to Manik. So Anand, did you have a question? You have unmuted yourself. Any questions from the audience? Okay, just to get things going along, Manik, I was curious about one aspect that you said that you had these billions of labels, which meant that the labels were fairly close to each other, which then means that even a small amount of noise in the input will easily send you astray because of the proximity of the label semantics. So in that sense, is there really a notion of a correct recall or precision? Because essentially you're looking at clusters of labels that are fine-tuned versions of each other.
Thanks, Jan. That's a really great question. I think there are two separate questions over here, right? So I think one is like, what is a like, is there a notion of precision or recall or whatever, right? And that's really important because it turns out that the whole notion of what is a good prediction changes when you go from 1,000 classes to, let's say, 1 billion classes, right? And therefore, this whole offline performance evaluation, what is the right metric? There will be many labels that are missing, right? So for example, in supervised learning, the paradigm is that you can take a test point and have it manually labeled by some domain expert, and then you have ground truth, right? You have the gold standard for this. But nobody can take a data point and manually label it with the 1 billion items that you have, right? Simply not possible. So not only is it good precision or recall, but even the ground truth is not correct, right? And so even cross-validation and other things won't work. So that's a whole really interesting area of research, and there are papers that are coming on what is a good way of evaluating extreme classifiers. The other question that you mentioned of are there really 1 billion labels, right? Are they very close to each other, so there might be noise? So in fact, most of these extreme classification techniques today try and actually capture the correlation between these labels based on their text, so that two labels that are very close to each other in terms of their descriptions get mapped close by to each other. And so even if there's a little bit of noise, they'll get recommended, hopefully. But yes, it's still an important area of research, how to deal with noise, because when you go into the tail, you'll have very little training data. And so then even small amounts of noise can throw your classifiers off. So that's the whole name of the game. How can you overcome this noise and make good recommendations in the tail?
Yeah, there is one question on the Q&A. Maybe I'll just read that out to you. This is from Sridevi, UK. And the question from her is, how do you select the top 100 million labels per product? When you do, is there a separate classifier per label that is required?
Yes, so there are 3 or 4 different types of approaches in terms of extreme classification, right? So actually, I won't be able to see my screen over here. So you tell me when I get to that tree-based thing, right? I'm just going back on my slides. You tell me when to stop.
Which specific slide were you talking about?
Oh, this one, I think, right? So Sridevi, there are 3 or 4 ways, right? So one is you learn a tree over your space of 100 million products that you want to recommend, right? You learn a hierarchy over them. And when a user comes in, you just go down the hierarchy. You will end up in a leaf node that will, let's say, contain only 10 or 100 products. And then you can just choose from those 100 products. Here, you can learn a separate classifier for each product, or you can have any other multi-label classifier, right? So one whole branch of extreme classification is devoted to tree-based approaches, where you learn a tree over the space of items you're trying to recommend. The next branch is based on these embedding-based approaches, right? Hashing. So what you can do is, just as you can do dimensionality reduction on the input side, you can also do dimensionality reduction on the label side. You can compress that space, and instead of treating them as 100 or 1 billion independent products, you can say, they live in a space of low dimensional space, let's say of just 1,000 or 10,000 products. And every product is a linear combination of those 10,000 unique products or something, right? So that is the second approach, which is based on hashing or dimensionality reduction. And the third is based on, as I said, these one versus all classifiers, where you don't do any dimensionality reduction. You learn a full rank solution, and you say, I'm just going to have a separate classifier per label. Now I can't see where that is, unfortunately. Maybe over here, I'm not sure. Yeah, you guys will have to tell me. I can't see my screen. So
maybe it's this one. This is the query, the BERT and the one versus all classifiers. It's about slice.
That's right. Yeah. So over here, what you're doing is, for every label, you're going to learn a separate classifier. So this is going to be full rank, right? And these are the solutions that give us the best accuracy today. But now the name of the game is, how in the name of heaven are you going to learn a billion classifiers in, let's say, a few hours on your standard desktop or your GPUs that you have access to at your university, right? And so the entire focus is on quickly choosing these labels that you can discard that are irrelevant, and just focus on the order log classifiers that are relevant for any particular user, right? The labels corresponding to the classifiers corresponding to those labels. So those are the three main ways of tackling extreme classification.
Okay. Also, Manik, there's a interesting question from Varad Vishwarupe from UK. He asks, can extreme classification be used for tasks other than multi-label classification? For example, such as interpretable machine learning using probabilistic frameworks for explaining the decisions in large data sets.
Yeah, so explainability and interpretability is critical, right? Users will have much more trust in a recommendation system if they can explain why it is making certain recommendations to them. And I personally have not worked on this, but one of the people in our group, Amit Sharma, he works on these kinds of robustness, fairness, explainability, and things, and he's looking at these issues. And it's a very important research topic, right? So if you are interested in working on this, please come and collaborate with me at either IIT Delhi or Microsoft.
Okay. So that's an open invitation. And on that happy note, I think we will stop here. If any of you had questions, I'm sure that you could email them to either Manik or his collaborators, and they'd be happy to respond to them. So please join me again in thanking Manik for an exceptional talk, which has set this field really alive with a very intriguing kind of a framework. So thank you, Manik, for setting the annual event on fire.
Thank you, Jen. I'm
Thanks.
so glad you invited me. Thank you.
Sure. Okay, so we'll have a short break now before we move to the second talk by Srikant Srinivasan, which will be at 3:30. Back to the organizers.
We owe a very big thanks to Dr. Manik Verma for this informative talk. I'm sure now many of us are intrigued by this talk, and we hope this would help us in our future research. We'll get back after a short 15 minutes break. Thank you.
It's not a 15-minute break, I think. It's at 3:30 that the next talk would start, right?
Sorry, a 10 minutes break.
Right, okay, thanks.
Drgnaka drgnaka jam jam drgnaka drgnaka jam jam tatti drgnaka jam jam drgnaka jam jam takati drgnaka jam jam drgnaka jam jam tatti drgnaka jam jam drgnaka jam jam takati drgnaka jam jam drgnaka jam jam drgnata dingina ta tatti drgnata dingina ta dingina ஆயர் குலத்தினிலா நிறைவேற்றவன் ஆடியும் பாடியும் கூடி மகிழ்ந்தவன் ஆனந்தமானந்தமானந்தமானவன் ஆழி துயில்பவன் அவன் அடிப்பணிவோ தாமித தக்க திமி 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 தஜம் திமி திமி கிட்ட தக்க திமி தக்க தஜம் திமி திமி கிட்ட தக்க திமி தக்க ஜம் முகவண்ணன் கண்ணன் காளிங்க நர்தனம் ஆடியவன் கம்சனை வென்றே காத்து நின்றார் கலியுக வரதன் கோவிந்தன் அன்னைய சோதையின் எண்ணம் கவர்ந்திட வெண்ணை உண்ட சிறுமாயவனே உண்மை எண்ணி நிலம் நினைந்துருகும் அடியார் துயர் தீர்த்திடும் தூயவனே இன்னும் விரி கடலும் வியந்திடவே நிதம் வண்ணை உண்ட சிறு பாலகனே யசோதை மணமகள் மாதவனே குசேலர் துயரினை தீர்த்தவனே மாமுனிவர் புகழ் மாலவனே நாரணனே மதுசூதனனே நாமமுறை துணை நாளும் நினைந்திடும் ஸ்ரீமுரளீதர கவித்வமே ஸ்ரீமுரளீதர
Venkatesh, did you want to try out Srikanth Srinivasan's slides?
Yes.
Srikanth,
Srikanth, you want to share your slides?
Yeah.
Sure. Second. Do you see it?
We see an empty screen. Right now, there's
screen.
there's a blank screen.
Oh, oopsie. Okay, so let me try that again. Just a second. Maybe I shared the wrong thing.
Yeah,
How about
this
now?
time it worked.
Okay, great. Fantastic.
Right. That's right.
Okay.
I thought you were giving a guessing game to the audience as to what the title is. And therefore,
I could make the whole talk that way. Maybe. That'll be fun.
right.
What's the next letter I'm going to use? Yeah.
Yes, right. So anyway, thanks very much for accepting our invitation and delivering this lecture today. Really looking forward to it.
Okay, great. Thanks very much for inviting me. It's an honor. Yeah.
Right.
Should we start, the organizers? Yeah, I think I will start.
Oh, okay, we can start, sir. Algebra plays a prominent role in life and in mathematics. We have Professor Srikanth Srinivasan to talk about algebra and computational complexity. And the session chair for this event is Professor Venkatesh Raman, who's currently working at Institute of Mathematical Sciences, Chennai. He's an ACM India Council member since 2016 and now is the secretary of the same. He has supervised more than 12 PhD students and over a dozen of master's theses. We are proud to say that he has published over 150 papers in international conferences and journals. You can now take over, sir.
Thank you. Thank you for this generous introduction. As Jayant would say, we will continue with another young Turk from India. It's a pleasure to introduce Professor Srikanth Srinivasan, who made some recent headlines by submitting his paper on super polynomial lower bounds against algebraic circuits in the recent IEEE Foundations of Computer Science prestigious Fox 2021 conference that actually happened last week. This paper, jointly authored with Nutan Limaye and Sebastian Tavenas, make a fundamental advance by proving super polynomial lower bounds against algebraic circuits of arbitrary constant depth. Now, Srikanth's quest for proving lower bounds actually started during his PhD days at the Institute of Mathematical Sciences under the guidance of my colleague Arvind. His thesis, titled New Directions in Arithmetic and Boolean Circuit Complexity, submitted in 2011, actually won the first ACM India's Doctoral Dissertation Award honorable mention. As Supratik was mentioning yesterday, it was a close tie with the best thesis. And so for those of us who have seen him as a student, it is hardly surprising the larger strides he's making in research, and we are sure that the best is yet to come. So after his PhD, Srikanth spent a couple of years in the US as a postdoc, 1 year in IIS Princeton and another year at Rutgers Temax, before moving to IIT Bombay as a faculty in the maths department. Since 2020, he has been at Aarhus University in Denmark. And today he's going to be talking about algebra and computation, a topic close to his heart. Over to you, Srikanth.
Yes, thank you. I assume you can hear me?
Yes. Yeah.
Okay. So what do we do about video? Should we keep it on, or is it better to turn it off? Or?
You can keep it on.
Okay. Okay.
Unless there is some bandwidth issue or something. For now, I think you keep it on. Yeah.
Okay. Sounds great. Yes. Thanks very much, Venkatesh, for the very kind introduction, and thank you to the organizers of this wonderful event for inviting me to give a talk here. It's truly an honor to be speaking among these very distinguished speakers. So I'm going to talk today about algebra and computation. As Venkatesh mentioned, it's a topic dear to my heart. I did my PhD at the Institute for Mathematical Sciences in theoretical computer science, and I worked for 8 years in a math department. So you can imagine that I'm very interested in the way that mathematics in general interacts with computer science. And it's actually often surprising to me how useful this interaction is in both directions. I guess it's not so surprising that mathematics is useful in computer science. After all, a lot of mathematics was developed in order to make certain computational procedures more efficient, because computation itself has been around for much longer than computers. So in some sense, that's not so surprising, but what's somewhat surprising, at least to me, is how computer science continues to kind of supply new research directions, even in age-old mathematical subjects, which you think would have been studied to death by now. But computer science continues to come up with really fundamental and beautiful questions to look at, and in turn spurs more research in that direction. Okay, and so this is sort of the motivating theme for my talk. And in particular, I'm going to be looking at the interface between algebra, which is, of course, one of the classical areas of mathematics and the theory of computation. So algebra, as many of you might know, is the name algebra comes from the book of a famous Persian mathematician. And the same Persian mathematician also, his name also shows up in the word algorithm. So somehow both algebra and algorithm have their provenance in the same source, so to speak. So it's not surprising that algebra has a lot to do with computation, I guess. But there are many ways in which it interacts with computation today. So let me mention a few. Okay, so for one, algebra since time immemorial has been a source of important computational problems when it comes to solving polynomial equations or many things of this sort. People have been looking at algebraic computation problems for a long, long time. On a kind of a slightly different note, the use of algebraic techniques also shows up in unexpected ways in algorithm design. So very often we are so we are face to face with some sort of turn out to be useful in the design of a suitable algorithm or its analysis. Another example is complexity theory, which is sort of the topic of my own research. So complexity theory is about the topic of showing that certain computations are inherently difficult, that there are no efficient algorithms for certain kinds of computational problems. And again, here algebra seems to play an important role in characterizing what computation can do and what it can't. So it's a very different use of algebra. A fourth direction of its application that's really beautiful is the theory
Venkatesh, maybe Shrikant can turn off his video because there's some
of pseudo-randomness. So oftentimes to random bits. So Monte Carlo simulation video then.
Shrikant, we keep losing you.
Just a second. Yeah.
There. So maybe you can turn off your video and see.
Okay, I'll do that. All right. Yeah, please do let me know if there's any issue. Yeah, thanks very much. Interaction between algebra and the theory of computation. Well, when you're trying to run an algorithm that assumes that it has access to random bits, right? A source of randomness that it uses for certain kinds of computations, of access to these random bits. What you would like to do is produce bits that are not really random, but that look random from the algorithm's point of view. And this is a very intriguing area of theoretical computer science that we'll get to a little bit more later on in the talk. But this basic idea goes by the name of pseudo-randomness. And algebra somehow is a source of a lot of pseudo-randomness. And it's very interesting in that sense. A fifth and final application of algebra in the theory of computation, there are many others, but I've chosen to kind of highlight these five, is to the theory of information transmission. When you have two parties that are trying to communicate to each other over a channel which happens to introduce errors, then what they want to do is they want to encode their communications in a certain way so as to introduce a little bit of redundancy so that even in the presence of a certain amount of noise, their computations can be decoded at the other end. Yeah, and again, algebra is very useful in the design of these kind of redundant mechanisms for information transmission. Okay, so these are five very important applications of algebra in the theory of computation. And it turns out that in all these five applications, there is a certain kind of algebra that's extremely useful, and that's the algebra of polynomials. Okay, and so this is sort of the theme of my talk today. I'm going to tell you a little bit about how polynomials and their study from a computational point of view impacts many of these different areas. I may not touch upon information transmission, but I hope that I'll touch on all the other four. Okay, so I should say at the outset that I'm going to illustrate these interactions with three vignettes, which is sort of related to my own research. But this is really a vast amount of interaction that I'm talking about here. So I cannot really do justice to all these areas, but I hope that I'll be able to pique your interest a little bit. And if you're interested, and then you can look at more resources and feel free to ask me at any point of time if you need more resources to look at. Okay, great. So let's get started. So I should mention that my talk is divided roughly into three parts, corresponding to three research vignettes. But and each part will start with a slide that looks like this. So this is sort of a segue into the next part of the talk. And at any point of time, if you lose track of what's going on, then just hang around until you see the slide again, and then it's a kind of a reset. Okay, so let me start off with the first part of the talk, where I'm going to talk about this topic in theoretical computer science called algebraic complexity theory. And this is closely related to the area of research, to the paper that Venkatesh was talking about when he introduced me. This is a certain computational way of studying multivariate polynomials, and this has applications to certain important computational problems and complexity. Okay, so let's get started. All right, so just to start off at the very basics. So what are polynomials, right? So you've probably seen these kind of objects. You remember them from high school, from Cartesian geometry or something else. But a polynomial roughly is an algebraic object that looks like this. So you have a few variables, you multiply some of them together, maybe with some coefficients, and you add them together, and you get an object which we call a polynomial. Okay, so frequently when we study polynomials in high school, they're related to things like conic sections and other geometric objects. But we also study many other objects that are polynomials, but we don't think of them as polynomials. Okay, so let me give you another such object. So consider a 3x3 matrix and the determinant of that matrix. Okay, you might again recall this object maybe from high school physics or somewhere else. But this object is extremely useful if in computing other kinds of geometric properties, for instance, like volumes of three-dimensional objects and many other things. Okay, but typically we don't think of this as a polynomial, but it is in fact a polynomial in the entries of this little 3x3 matrix. So it looks like something like this. It doesn't really matter what it is, but the thing is it's a sum of products of things. Okay, so this is the determinant. That's another important polynomial. And there's a closely related polynomial called the permanent. So the permanent is a very similar polynomial. It's the same kind of terms, but instead of these minus signs here, you have the plus signs here. So then that is the same. Okay, so throughout this talk, we're going to be talking about polynomials of this kind. So we're going to be talking about polynomials which have many variables in them. So the first polynomial here has just two variables, x and y. The second one, the determinant, has 9 variables. Yes, it's easy to visualize geometrically, but nevertheless, they do have interesting geometric properties that we can leverage for various reasons. All right, so let's get to what we are going to study about these polynomials. Okay, so we are going to look at multivariate polynomials from a kind of computational point of view. So what does that mean? So given any polynomial p, we'll think of p as defining a computational problem. Put as some settings to the variables of this polynomial. For instance, for a 3x3 matrix, we might get 9 numbers corresponding to these 9 variables. And the desired output from our computational procedure should be the evaluation of this polynomial at z, etc., etc. Then I want to compute the determinant of this 3x3 matrix, and that's the underlying computational problem. Okay. So it turns out that many naturally occurring computational problems that we are interested in can be defined via polynomials in this way. Okay, so let me give you a few examples. So the determinant, so this is the 3x3 determinant, but in general, the n by n determinant, that's an extremely important computational problem. It shows up in all sorts of contexts, for instance, in solving linear equations, in optimizations of linear optimization problems, and so on. So it's an extremely fundamental computational problem. The n by n cousin of this permanent guy is also extremely important. So it shows up in all sorts of counting problems, for instance, counting matchings and graphs and other combinatorial objects, which maybe we'll talk a little bit more about later. And there are other problems that, again, that we don't think of as polynomial computation, but they are. For instance, the problem of multiplying matrices or computing the fast Fourier transform. These are all fundamental computational problems that we learn about in our basic algorithms courses. And they're all about evaluating certain polynomials with certain inputs. Okay, so many natural computation problems are captured by this general framework, right? And it's not just algebraic problems that come up in this framework. There are situations where you have a combinatorial problem that you're interested in solving, maybe finding a matching in a graph, and it turns out that polynomials of this algebraic problems of this algebraic nature can help you with those combinatorial algorithm problems in some non-trivial way. Okay, and we'll see maybe examples of this later on. Okay, so that's the general setup. So algebraic complexity theory is about the study of computational problems that are defined in this way. Okay, that's the basic setup. And more specifically, it studies a certain kind of algorithm for these kinds of problems. Okay, and these algorithms go by the name of algebraic circuits. So let me just tell you quickly what they are, because they're very simple objects. So there are 2 equivalent ways of defining them. So the first way of defining an algebraic circuit is as a program in some sort of assembly language. Okay, so imagine that you have a polynomial p that you would like to compute, that you would like to evaluate at some setting of these variables. So you can imagine that you write down this long line of assembly language code, if you will, for doing this evaluating this polynomial. And what does this assembly language code do? Well, every line of this code is an instruction which either computes a product of variables, a sum of variables, or sums of products of things that have already been computed before. Okay, so for instance, the first line of this is multiplying a couple of variables together. The second line adds a couple of variables, and the third line does the same. And then the fourth instruction kind of adds two previously computed values and so on. Okay, so this assembly language program, if you will, goes on for a while, and the last instruction that you write down, the last instruction of the program, it's supposed to compute this polynomial in the underlying variables. Okay, so this is the basic setup. This is what an algebraic circuit is. So it's a very simple kind of assembly language code for computing any polynomial that you'd like. All right, so that's an algebraic circuit. There's a completely equivalent way of looking at this in terms of graphs, which I like because I like pictures. So, and that's this picture here. So this is also an algebraic circuit. So again, this does the same thing. So you start with your variables here, and then you can multiply them together. Just like this, the first instruction here is multiplying x1 and x2. This vertex in this graph is multiplying x1 and x2. Just like the second instruction is adding x2 and x3, this vertex here is adding x2 and x3, and so on. So this picture on the right represents exactly the same kind of computation as the picture on the left. P is being computed. Okay, so these are kind of either of these two things, and studies for evaluating. This is the general setup. So I should stress here a small point, but it's an important one, is that this is a special kind of a computational procedure for evaluating polynomials. Okay, so given that you could choose to use transcendental functions or logarithmic functions or exponential functions or bit rate algebraic complexity theory, we only consider natural because polynomials themselves are defined using, okay. And it turns out that there are not too many scenarios where an algebraic problem. So it seems to us that this is a good model of computing.
Shrikant, sorry for butting in, but we are periodically losing you. Do you have an alternate internet connection that you could use? Because
yes, I do actually. Just give me a minute. I will just connect to an alternate internet connection. Sorry about that.
Sure.
Should I leave and go? Hi, I'm back. So are you able to hear me?
We can hear you.
Okay, so let me see if I can share my screen. Can you see my screen?
Yes, perfect. Yeah.
Okay, great. Yeah, I'm sorry for that. I hope there won't be any more problems, but yeah, let's see. Okay, so back to where I was. Okay, so the computational problems we are looking at are problems that come from evaluating polynomials at a given point, like the problem of evaluating a determinant. And the computational model that we study is that of an algebraic circuit, which can be visualized in one of these two ways, either as a list of instructions or as a graph like this. Okay, so that's the topic of study of algebraic complexity theory. Yes,
you were mentioning that this is a very special model, and that's when we lost you a little bit. So what is special about?
Yes. So let me just finish that point. So so I should stress here that an algebraic circuit is not the most general model of computation you could think of. If you look at a more general kind of program, it is not restricted to doing just these arithmetic operations such as additions and multiplications. You could imagine that a program uses transcendental functions such as exponentiation or logarithms or things of that nature in order to compute polynomials. So in some sense, this is a special model of computation. But on the plus side, every algorithm that we know of for these kinds of algebraic problems does look like this. So in some sense, we don't seem to lose much generality by restricting ourselves to this particular model. Okay, so that's the reason for doing this. All right, so now let me tell you a little bit about the kinds of questions we study in algebraic complexity theory. So you're given this polynomial that you'd like to compute. And the basic question is, for any such polynomial, does it have an efficient algebraic circuit? Okay, so that's the basic question. Does your favorite polynomial have an efficient algebraic circuit? And here efficiency refers to the number of operations that you use, which roughly corresponds to the number of lines of assembly language code. Okay, and what does efficient mean? Well, for simplicity, we use as efficient the notion that the size of this circuit, which is the number of operations, is polynomial in the number of variables. Okay, so that's kind of a rough analog of efficiency. You can go further than this and look at linear, quadratic, etc. But as roughly as a first approximation, this seems to be a pretty decent notion. Okay, so that's the basic question. And does your favorite polynomial have a polynomial-sized algebraic circuit? Okay, and for many interesting polynomials that we saw on the previous slide, the answer turns out to be yes. Okay, so matrix multiplication, you can multiply matrices efficiently, and that comes from the fact that they have efficient algebraic circuits. The problem of computing the determinant, the n by n determinant, that's a fundamental algorithmic question. Algorithms for this have been known actually from before the time of computers, and it turns out that they come also from algebraic circuits of a certain kind, which are efficient. So in both these cases, the answer turns out to be yes. Okay. But a related case, the case of the permanent. Okay, the permanent is the same as the determinant, but without the signs. So for this particular computation problem, the answer is not known. Okay, so as far as we know, there are no efficient algebraic circuits for this problem. And it's suspected for a certain reason that there are absolutely no algebraic circuits for this problem that are efficient. Okay, and essentially the study of complexity of problems of this kind, why is it that the permanent does not have efficient algebraic circuits while the determinant, which looks very similar to the permanent, does? And that's sort of the study of algebraic complexity theory. Okay, so just to define this basic problem, so let me just make a small definition. So we use for VP, VP is a class of problems or class of polynomials, all those polynomials of this form that have efficient algebraic circuits. So that's VP. And if you've seen a little bit of complexity theory, this is very analogous to the complexity class P, right? The class of problems that are solvable in polynomial time. So this is sort of the algebraic analog of that. Okay, so any polynomial that has an efficient algebraic circuit is in VP. Examples include matrix multiplication and the determinant. Okay, and similar to VP, there's also an algebraic analog of VNP, which is the other half of the equation. Which is a large class of algebraic problems that we ideally like to solve. Okay, so we have P and NP in classical complexity theory. P is the class of problems that we can solve. NP is a large class of problems we'd like to solve. And similar to that here, we have VP, which is the class of problems we can solve algebraically in this way. And VNP, which is a large class of algebraic problems that we'd like to solve. And the kind of the big motivating question for this area, which was actually discovered by Valiant, who started the study of these kinds of things, is whether these two classes are really the same. Okay, is it the case that every problem that we'd like to solve in this big class V and P, is it the case that every such computational problem has an efficient algorithmic procedure of this form? Okay, so this is kind of a very abstract question. The question is, does every problem in this very vast collection of problems have an efficient algorithm of this form? Okay, it's a very abstract question, but what Valiant discovered when he started the study of this kind of problem was that he realized that it could be actually boiled down to an extremely concrete problem. Okay, a very concrete problem, not such an abstract one. And the concrete problem that Valiant discovered that this is equivalent to is the problem of whether the permanent, this very specific polynomial, the permanent, does it have efficient circuits? Okay, And what Valiant noticed was that if the permanent has efficient circuits, then in fact, these two classes are equal. And if the permanent does not have efficient circuits, then in fact, these two classes are different. Okay, and it's really tied up to the complexity of this one problem. Okay, so in a line, algebraic complexity theory is about the study of this fundamental question, or equivalently, it's the question of whether the permanent has efficient circuits. Okay. All right, so this is the motivating question behind the area. And so let me just tell you a little bit about why we study these kinds of questions and how they relate to more, possibly more famous questions in complexity theory. Okay, so why VP versus VNP? All right. So as I mentioned already, the kinds of computational problems that we're looking at, problems like the determinant, matrix multiplication, the permanent, etc., is a very natural family of algorithmic problems that we'd like to study. Okay, they show up in all sorts of natural contexts in interesting ways. So we'd like to study the complexity of such problems. And in all these scenarios, the best known algorithms that we have come from algebraic circuits. Okay, so it's natural to look at, okay, what is the best algebraic circuit for a given problem of this form? So that's one reason to kind of study VP versus VNP. And another very interesting reason is that it is actually easier than the P versus NP question. Okay, so the P versus NP question is this famous question in complexity theory, one of the Clay Millennium math problems. And it's known, so it's suspected that P is not equal to NP, that not every problem in NP can be solved efficiently. And it's also known that if indeed P is not equal to NP, then VP is not equal to VNP. Okay, so the classical complexity analog of this question also implies the algebraic analog. So you can interpret this in a couple of ways, but the interesting way of interpreting it in our scenario is that the VP versus VNP question is sort of like an easier version of the P versus NP question. Because if you believe that P is not equal to NP, which almost everybody does, then indeed VP is not equal to VNP. Okay, and so this seems like an easier question that you'd like to solve on the way to P versus NP. Okay, so that's one of the main motivating goals behind this line of research. Okay, and finally, unlike the P versus NP question, where we have very, very few strategies to kind of attack this question. We strongly believe that P is not equal to NP, but we have no means of approaching this problem. It seems that we do have means of approaching the VP versus VNP question. Okay, and this is why a very concrete approach called depth reduction that I'll tell you about in the next slide. Okay, so this is another reason to study the VP versus VNP question. Okay, all right. So let me tell you a little bit about this approach towards the VP versus VNP question, and this is closely related to the result that we recently had that Venkatesh said a little bit about. Okay, so in order to do that, I need to define a special class of algebraic circuits that are called constant depth circuits, which I'll now do. Okay, so what we are trying to do is kind of trying to understand for a given polynomial what is the most efficient way of computing it via an algebraic circuit. Yeah, and the hard part of doing this is sort of to understand at which point of time that you have the most efficient computation for this given polynomial. So how do you prove that I cannot get a more efficient computation than a given computation? How do I show that this polynomial does not have a more efficient algebraic circuit than this? Okay, that's sort of the hard part of this, and the hard part of understanding questions like this in general. And this is the question of proving a lower bound. Okay, the question of showing that this polynomial does not have efficient circuits of some form. Okay, and let's try to kind of approach this general question by understanding very, very simple kinds of algebraic circuits and see where we get stuck. So let me start with this polynomial here. So it's a very simple polynomial. So what's an algebraic circuit for this polynomial? In other words, suppose I give you values for x and y, how would you evaluate this polynomial at x and y? Right. And now if you think about this question for a bit, you see that, oh, here's a polynomial. You've given me this as a list of products of variables and summing them together. This gives me a recipe for evaluating this polynomial, right? First, I'll look at x, I'll multiply it with itself, multiply it with 3, and I compute the second term, and I compute the third term, etc., etc. I add them all together, and that gives me a recipe for computing p at a given point. Okay, and this in particular is a special kind of algebraic circuit. Okay, so if you kind of draw it as an algebraic circuit, it looks something like this. Maybe it looks a little bit complicated, but it's really doing the same thing. So it's computing each of these terms individually, which are all products, and then adding them all together, and that's the algebraic circuit. Okay, you can do this in general for any given polynomial. Take your favorite polynomial, write it as a sum of products of things, and this gives you in particular an algebraic circuit for this kind of polynomial. Okay, so this kind of algebraic circuit actually has a name. It's called a sigma pi circuit. Okay, why sigma pi? Because the sum of products of things, so sigma pi circuit. And this kind of thing is very easy to understand, right? Because given any polynomial, of course, I can always write it down as a list of things like this. These are called monomials, so as a list of monomials and sum them together. So it's very easy to always come up with a sigma pi circuit for any given polynomial. It's also very easy to understand what the number of operations or the size of this circuit is, right? So because the number of operations here is just the number of terms of this form. So it's just the number of monomials in this polynomial. Okay, and roughly it's usually the exponential in the degree of this polynomial. Okay, so the simplest kinds of algebraic circuits you can come up with for any given polynomial is a sigma pi circuit. A sigma pi circuit is always easy to understand, and its size is very easy to analyze. Okay, so this is something that we understand. Now, starting from here, if you want to kind of just increase the complexity of the circuit a little bit in order to understand it further, you run into problems. Okay, and I want to describe to you the first class of circuit where you actually run into problems. Okay, and this class of circuits is very, very similar to this. So instead of writing a polynomial as just a sum of products of variables and other things, what you do is you write it as a sum of product of sums of variables and other things. Okay, so now these terms, instead of being variables, they are now linear polynomials or sums of things. Okay, and this kind of thing, again, for obvious reasons, this kind of expression is called a sigma pi sigma circuit, right? Because the sum of product of sums of things. Okay. And in general, a sum of product of sums of things can be much more efficient in terms of number of operations than a sigma pi circuit, right? So if you imagine that you just take your variables and divide them into sets of size 2, sum them together and take the product, right? So imagine that you have pairs of variables that you sum together and take their product. If I want to write this as a sum of monomials, then that will really blow up the size of this by a lot, because I have to look at every possible way of choosing one variable from here, one variable from here, one variable from here, and so on. Okay, so to write this as a sigma pi circuit would be highly inefficient. But here I'm writing it as a sigma pi sigma circuit very efficiently, just using n operations. Okay, so in general, a sigma pi sigma circuit can be extremely efficient. And you can get even more efficient if you start looking at higher analogs of this, like sigma pi, and so on. Okay, so these kinds of circuits are called constant depth circuits. Constant depth refers to the fact that you have only a constant number of these kinds of symbols defining the name of the circuit class. So sigma pi refers to depth 2, sigma pi sigma refers to depth 3, and so on. And in general, we look at circuits where you only have a constant number of these, and the constant is because it's independent of the number of variables of the underlying polynomial. Okay, so these are special kinds of computational objects. And just like we understood sigma pi circuits really nicely, the first question we can ask is, can we prove that some polynomial does not have efficient sigma pi sigma circuits? Okay, and the analogous question for sigma pi is extremely simple. Take any polynomial that has lots of monomials that does not have a sigma pi circuit that is efficient. Can you show something for sigma pi sigma circuits? Okay, and this question, despite being extremely simple, was actually open for 25 years. Okay, so this problem was actually stated back in a paper in 1995, but it was open for 25 years. And this is actually an amazing question, and it's a kind of example of things that I was talking about, where simple questions in computer science lead to extremely beautiful and combinatorially interesting questions in mathematics, because all this is about writing a polynomial in some sort of generalized sum of products of sums representation. But for some reason, mathematicians had never considered this problem. They found it, of course, very interesting, but they had a priori no tools to immediately deal with it. Okay. So this is the kind of question that was open for a long time, and it was only solved recently, which I'll tell you about. Okay. All right. So now, why was this question interesting, and why was it open for so long? It turns out that in the meanwhile, we did make some progress on understanding this question, and that's what I want to tell you about first. Okay. So the progress that we made was we couldn't prove that certain polynomials do not have efficient sigma pi sigma circuits, but we could show that if we could prove something like this, then we'd get a whole lot more. Okay, and this phenomenon, extremely interesting phenomenon, goes by the name of depth reduction. Right. So I should say that this line of research has, in general, algebraic complexity theory is a research area that kind of finds a lot of traction amongst the Indian theoretical computer science community. So we have a lot of very influential work in this area that comes from Indian theoretical computer science. And this particular strain of research is no exception to this. So this starts with some old work of Valiant and others from 1982, but there were more recent results by Manindra Agrawal and V. Vinay, and more recently by Neeraj Kayal, Ankit Gupta, Pritish Kamath, and Ramprasad Saptarishi, all of whom were in India. Okay, so let me tell you a little bit about the depth reduction. So what is depth reduction? So depth reduction is this idea that we can actually start with a general algebraic circuit, right? So this picture on the left represents a general algebraic circuit, which you can think of as an efficient algebraic circuit for your favorite problem. And you can kind of squish it down. You can kind of squish it down into a small depth. And small depth, think something like sigma pi sigma, sigma pi sigma pi, or something like that. A small depth, a short but slightly more, slightly broader circuit of some other form. Okay, so in this example, a sigma pi sigma circuit, which is somewhat efficient. So it's not as efficient as the guy you started with, but it's still somewhat efficient. Okay, so I'm sort of a half mathematician and half a theoretical computer scientist, so I cannot help but put some numbers to this just to make myself a little bit more clear. So suppose I start with an efficient circuit, which is a circuit of size polynomial in n. We end up with a somewhat efficient sigma pi sigma circuit. And the somewhat efficient is still not great. It seems to be some sort of exponential in the degree, but it's still much better than what we'd expect in a sigma pi circuit, which is truly exponential, whereas this is somewhere between polynomial and truly exponential. Okay, so you get some sort of improvement when you convert to a sigma pi sigma circuit. Okay, so this is this phenomenon of depth reduction, right? And the name is hopefully fairly self-explanatory because you're just reducing the depth at the expense of losing a little bit in the efficiency. Okay, so what is the reason for the interest in this result, and why am I telling you about it? Well, because you can look at this result in the contrapositive and you get something extremely interesting. Okay, and so what this means is that if you can show that your favorite polynomial, maybe something like the permanent, does not have even somewhat efficient, does not have sigma pi sigma circuits of the size, then in fact you also note that it does not have efficient computations of any kind of depth. Okay, so by just sort of understanding the power of this very, very simple kind of polynomial representation, sorry, let me just go back here. By understanding the power of this very simply stated polynomial, power of these kinds of polynomial representations, what we're able to do is derive consequences for much more general kinds of these kinds of algebraic circuits, these kind of assembly language code. Okay, and this is the kind of approach we have towards the VP versus VNP question that we are lacking in the P versus NP question, which is why this question seems so interesting to us. It seems very approachable. This problem can actually be defined to maybe an undergraduate in mathematics or theoretical computer science or general computer science, and the undergraduate would understand it and be able to appreciate it. But solving this problem kind of optimally would lead to this beautiful result that VP is not equal to VNP. All right, so that's all I had to say about depth reduction. So, this final vignette about depth reduction, I should say that it's somewhat unrealized because we didn't know how to we still don't know how to prove that there are no efficient sigma pi sigma circuits for your favorite polynomial. In fact, we do not even have a way to show that a polynomial P does not have efficient, which is polynomial sized sigma pi sigma circuits. This problem was open for 25 years. And this is exactly the problem that we solved recently. Okay, so take your polynomial P to be either the determinant or the permanent. What we showed was that this polynomial P does not have efficient sigma pi sigma circuits. So efficient again just means polynomial size. Okay, and this result does not stop here. It holds for sigma pi sigma pi, sigma pi sigma pi sigma, and so on. Okay, so we showed that these polynomials, which are very naturally occurring, do not have these simple kinds of constant depth representations. They are efficient. Okay, so that was kind of our first main result. This resolves a problem that we've been struggling with for a while, and does it in a, I guess, somewhat satisfactory way. And what we were able to do was do a little bit more. Actually, we were able to show that for some other polynomials, not exactly this one, but some variant, we were able to actually show that it does not have circuits of size n to the square root the degree. Okay. So the only reason I'm flashing this number here is that hopefully you remember from the previous slide that this is the kind of bound that showed up in the depth reduction arguments. Okay, and this weakly exponential bound is what we get for some other polynomial P. And it turns out that if you improve this by the depth reduction result, if you can just get rid of the square root and improve it to something a little bit better, maybe remove the square root entirely, then you'd actually show that VP is not equal to VNP. Okay, so we are almost, so from being essentially nowhere, we didn't have even polynomial sized lower bounds. Now we have super polynomial, and we are kind of pushing the boundary of VP versus VNP via this particular approach towards proving lower bounds for sigma pi sigma circuits. Okay, so that was sort of the main result that we proved. And I'm not going to tell you much about the proofs at all. So this is all I have. I'm going to devote to that. But let me just tell you a couple of things, because it turns out that the proofs are kind of counterintuitive, but it turned out to be incredibly simple. Yeah, so this was another thing that all of us found surprising, but we are very happy about, because obviously what we'd like to do is actually prove VP not equal to VNP. So we'd like to improve our results. So it was great that the proofs were very simple. So again, the statement of this problem is something you can describe to a kind of a senior undergraduate student, and the proofs are something that maybe a first-year graduate student can understand. They're quite simple and nice.
Srikanth, I have a question.
Yes. Yes.
For some other P, you said you have a lower bound of n power square root of degree P. That is also for sigma pi sigma circuit?
That's right. Yes, that's right. This bound is for sigma pi sigma. That's right. Absolutely.
Okay.
Yes. Thank you for that question. Yes, absolutely. We get a lower bound of n to the square root degree. And if we can improve this to anything better, then we get a separation between VP and VNP.
So I thought from the previous slide, you already have this separation from n power square root of degree P. No? Can you just flash the previous?
Yes, of course. Right. So the previous slide, this result says that any polynomial which has efficient algebraic circuits has a sigma pi sigma circuit of size, whatever this is, n to the square root degree. And now we show that there is a polynomial which requires sigma pi sigma circuits of this form. So this conversion in some sense cannot be improved, right, for this polynomial. But in order to show that it does not even have efficient algebraic circuits, then we'd have to improve this bound to something slightly better.
Ah, okay. Okay.
Anything better than this.
Okay.
Right.
Good.
Yes.
Yeah.
Thanks for that question. Yeah, it's a very good one. Okay, great. So this is the results, and the proofs turn out to be incredibly simple, and they also turn out to use many classical ideas in mathematics, kind of putting together ideas coming from different areas in interesting ways. These ideas include the classical Girard-Newton identities from like the 1600s or something. It's very classical. The partial derivative method, so which is actually kind of discovered by computer scientists, but also known to some mathematicians in the 1800s, and Diophantine approximation, which depending on how you count it, either goes back to the Greeks or maybe to the 1800s. So they're very, very interesting classical ideas of mathematics that show up in the proofs in very simple ways, and they're combined in maybe slightly surprising ways in order to yield this result. Okay, so that's all I had to say about this result of ours. And so now let me move on to the second one. So Venkatesh, can you tell me about how am I doing on time?
You have 15 minutes.
I have 15 minutes. Okay, great. So perfect. So I have enough time to do another research vignette, and maybe I'll skip the third and go on to summarize. Okay, so now let me tell you the second thing that I want to tell you about. And this is sort of a consequence of our previous result, but now to an algorithmic problem. Okay, and this algorithmic problem is called the polynomial identity testing problem. And it actually shows up in many different, in designing algorithms for all sorts of different interesting problems. Okay, so this is kind of an application of our previous result, our lower bound result, to algorithm design and some sense to pseudorandomness. All right, so let me tell you about how this problem goes. So I'll start with an example, which is actually a famous example in the theory of algorithms. It's called the bipartite perfect matching problem. Okay, it's a beautiful algorithmic problem. So what's this problem? You're given as input a bipartite graph, right? So you have a bipartite graph. So think of the vertices on the left as maybe 3 jobs, and think of the vertices on the right as maybe 3 machines. And you put an edge between a machine and a job if the machine is capable of doing the job, and you don't put in an edge if the machine is not capable of doing the job. Okay, so that's the bipartite graph. And a perfect matching in this graph is an assignment of jobs to machines so that every machine gets exactly 1 job. Okay, so for instance, this graph has 2 perfect matchings. You can assign job A1 to machine B1, A2 to B2, and so on, or you can do this thing. So you have the blue matching and the red matching. Okay, so these are the two perfect matches of the graph. And in general, the corresponding algorithmic question is as follows. So you're given as input this kind of configuration, a bipartite graph, and you have to decide, is there a way of assigning jobs to machines so that every machine gets exactly one job? Okay, does G have a perfect matching? So that's a bipartite perfect matching problem. So it's kind of a classical algorithmic question. In fact, the general perfect matching problem is what led to the definition of polynomial time as a notion of efficient. So it's a very classical algorithmic problem. Okay, and now let me describe to you an algebraic approach of solving this problem. Okay, so how do I do this using algebra? So notice the statement of the problem itself has no mention of algebra. So this is about graphs and matching, so nothing but algebra in there. But there's going to be a nice algebraic way of solving this problem. Okay, so what's the algebraic approach? Well, I take this graph G and I turn it into a matrix. Okay, so what's this matrix? Well, this is going to be a 3x3 matrix in this case because I have 3 vertices on the left and 3 vertices on the right. And every row of this matrix is going to correspond to a vertex on the left. So A1, A2, A3. So I have 3 rows, A1, A2, A3. And similarly, B1, B2, B3 corresponding to the vertices on the right. And now each entry of this matrix is going to be 0 if there is no edge between the corresponding vertices. So for instance, there's no edge between A1 and B3. So the corresponding entry in the matrix is 0. Or if there is an edge, so for instance, between A1 and B2, we have an edge. In that case, we put in a variable in this entry. Okay, so it's a 3x3 matrix. The entries are zeros or variables, distinct variables corresponding to different distinct entries. And the entries are 0 if and only if there's no edge. And if there is an edge, then you put in a variable. Okay, and now we look at the determinant of this matrix. Okay, so we constructed this 3x3 matrix and we look at the determinant of this matrix. Okay, so what does the determinant look like? Of course, we can write it as a polynomial, as a sum of terms, right? And it turns out, you probably remember this from having seen 3x3 determinants or other kinds of determinants at some point in time, but otherwise just take it on faith that it turns out that every potential term in this determinant, right, every possible term in this determinant corresponds to a potential matching in this graph, right? So there are lots of potential matchings in this graph, and every matching here kind of gives rise to a potential term in the determinant here. But now, if you don't have an edge corresponding to some pair of vertices, then the corresponding term here is 0, which means that the corresponding term in the determinant zeroes out. Okay, so what you're left with, if you evaluate the determinant, is exactly a sum of terms, and each term kind of corresponds to a matching in this graph G. Okay, so you have a blue matching, so you have a blue term, and you have a red matching and a red term, nothing else. Okay, so if this graph, for instance, had no matchings whatsoever, then there would be no terms in this polynomial and it would just be 0. But in this case, you have 2 terms because there are 2 matchings. Okay, so that's the algebra of this determinant. But now how does this lead to an algorithm? So now the general observation is that the determinant of an n plus n vertex graph, so the larger graph C1, the determinant is non-zero. So there are some terms in this polynomial if and only if the graph has a perfect matching. Okay, so the question of whether the graph is a perfect matching reduces to checking that this determinant is non-zero. Okay, so how do we check whether the determinant is non-zero, right? So it's a small point here that I have to make. In general, computing determinants, I told you some time ago, is doable efficiently, but that's only doable efficiently if the entries of the matrix are numbers, right? So if x is 1, y is 2, u is 100, whatever, then we know how to compute the determinant of this matrix. But now the entries of this matrix, they're not numbers, they are indeterminates, they're variables that can take any value. Okay, so what we have here is actually a symbolic determinant. It's not a determinant of a matrix of numbers, but it's a matrix with variables and other things. And the question is this symbolic determinant equal to 0? Yeah, and this is a kind of a different kind of problem, and that's the problem we need to solve if we want to check if this graph G has a perfect match. Okay, so how do we do that? Well, how do you evaluate a symbolic determinant, right? So there are 2 ways of doing this. One thing you can do is sort of just look at every possible term that can appear in this determinant and write it out and see if it's 0 or not. And that would be the analog of taking every possible matching that can appear in this graph and seeing if it actually exists in the graph or not. So that's going to take exponential time. So it's not a very efficient algorithm. But another thing you can do is use the fact that a determinant can be evaluated efficiently if the entries of the matrix are actually numbers. Okay, so what you can do is try to plug in numbers for x, y, u, v, r, and check if the determinant evaluates to 0 or not. And this has its own problems because it may be that the determinant is non-zero, like in this case, but when you substitute numbers in here, you get the 0 value. So for instance, if you make all the entries of this matrix 1, then you get 0 as the output, despite the fact that the determinant is non-zero. Okay, so this numerical substitution, you can be unlucky and you can get 0. Okay, so you probably see a little bit of how to fix this, and we'll get to that. But before I do that, let me define a more general problem that is of a similar nature. And this is called the polynomial identity testing problem. So what's the polynomial identity testing problem? In general, you're given a polynomial, but the polynomial is given some sort of encoded form. And the most general encoded form for us is an algebraic circuit. So this is the algebraic circuit. It computes some polynomial. And the question is the polynomial identically 0? Is this just a fancy way of writing the 0 polynomial? Right? Is it the case that when you kind of expand all the terms and write it out, everything cancels out and you actually get the 0 polynomial?
Shrikant, there is a question. Deepak has raised his hand. Deepak, did you mean to ask a question or? Deepak?
Yeah, Venkatesh, can you hear me?
Yes, go ahead.
Yeah, so Shrikant, on the previous slide, maybe I misunderstood that, but each monomial that you get from that determinant corresponds to one perfect matching, right?
Right, yeah, that's right.
I mean, isn't it possible that 2 can cancel out? Like maybe I had XVR and maybe I had VRX.
Right, that's a very good question. So this is why we make the indeterminates correspond to different entries distinct. So
that can't happen.
That cannot happen, exactly. Okay. Yeah. Thanks for the question. Yeah. Okay. Great, perfect. So so the polynomial identity testing problem is kind of a generalization of this problem of checking if a symbolic determinant is 0. So you're given a polynomial as a circuit and you want to check if it's 0 or not. And this is useful in a whole lot of contexts. So just like we saw the application to the perfect matching problem. So it turns out the perfect matching problem does have a different kind of algorithm that doesn't use these algebraic ideas. But there are many contexts, even variants of the perfect matching problem, where in fact this algebraic framework is the only way we know how to proceed. Okay. All right. So how would you go about solving this more general problem, right? The problem of checking if a symbolic determinant is 0, or more generally, an algebraic circuit is computing the 0 polynomial. And there's a very simple kind of a randomized strategy to do this. So what's the randomized strategy? How do you check if P is 0? Again, if you expand, you're going to end up taking exponential time because you're going to look at every possible monomial the circuit can generate, and that's an exponential number of monomials. So forget that. And numerical substitution has the potential of giving you 0 even when the polynomial that the circuit represents is a non-zero polynomial. So how do you get around this? Well, the idea is very simple. It's kind of geometric. The idea is to evaluate the polynomial not at a fixed point, but at a random point. Okay, so you don't evaluate the polynomial at maybe 1, 1, 1, 1, 1, but instead you evaluate it at a randomly chosen point. Yeah. And why is this guaranteed to work? Sort of very intuitive, right? It seems like if a polynomial is non-zero, so polynomial is indeed non-zero, then the set of points on which it vanishes, let's say in three-dimensional space, so take your favorite three-variable polynomial, maybe x squared plus y squared minus z or something. Take some three-variable polynomial. The set of points where this polynomial vanishes should define some sort of two-dimensional surface. Yeah, this is kind of a geometric idea. It finds a two-dimensional surface in three-dimensional space. So you would imagine that if you pick a random point in this three-dimensional space, you're very unlikely to encounter a point where this polynomial is 0. Okay, and indeed this can be made precise and has been by a series of works in various areas. And so now this gives you a very simple randomized strategy. Just choose a random point and evaluate the polynomial at that point. If it's 0, then declare the polynomial 0. And indeed, you will be right, because for a non-zero polynomial with high probability, you would have found a point where the polynomial was non-zero. Okay, so that's the basic idea behind this. And now let me come to the main question here. So you have this very natural algorithmic problem for which you have a randomized algorithm, which is extremely efficient. The question is, can we do this without randomness? Okay, so can we do this deterministically, which is to say an algorithm that is right all the time and does not use any sort of randomness? Okay, and this is actually, again, another long line of research in complexity theory that I will not be able to do justice to in this short time that I have remaining. But in general, it turns out that this question of whether you can remove the randomness from a randomized algorithm is fundamentally linked to questions like the P versus NP question, or even the VP versus VNP question that we spoke about earlier. Okay, and why is that? So at a very, very high level, so suppose you have a random algorithm. And what is a randomized algorithm? It takes as input something. So in our case, an algebraic circuit. it takes also some random bits as input, in which case, like our algebraic circuit, like our algorithm, it chooses a random point for evaluation, and it produces an output, which is right with high probability. Okay, so you have this algorithm, and what you would like to do is rid it of these messy random bits. So you'd like an algorithm that doesn't have any sort of recourse to random bits. Okay, and how do you go about doing that? Well, it turns out that it's very useful in this situation to use a hard computational task in some sense to get rid of these random bits. And how do you do that? Well, we do this actually in practice all the time, and this is the theoretical underpinnings of that. And it was discovered by kind of a sequence of works in complexity theory. So what you do is that you use this hard computational task in order to design what we call a pseudo-random generator. Okay, and what's a pseudo-random generator? A pseudo-random generator starts with a small number of random bits, right? So very few random bits here, and it produces as output a large number of bits, which not really random. They can't be, because there are very few random bits here, but they sort of look random to this algorithm A. Okay, so this algorithm A expects truly random bits, but it's able to make do with these random-like pseudo-random bits. Okay, and the reason it's able to make do with that is that the algorithm, the procedure that's used to produce these pseudo-random bits, is actually based on some sort of very hard computational task. Okay, somehow, because it's a hard computational task, the output of the task itself is very hard to predict, and that's sort of the reason for these bits looking random to this algorithm. Okay, that's kind of a very, very high level description of what's going on here. But it turns out that this kind of idea is extremely general and can be used in various scenarios. And in particular, they can be used to reduce the amount of randomness in the algorithm that we saw on the previous slide. Okay, so we use this idea in order to reduce the number of random bits the algorithm is using. And once the number of random bits is small enough, then we don't really need random bits at all anymore. Because what we can do is we can just simply say, oh, look at all possible values these random bits can take, run the algorithm on each of them, and sort of then decide what the algorithm is going to do. Okay, so once you use these pseudo-random generators to reduce the randomness enough, then you can eliminate it entirely. Okay, so that's the short pitch of this area, but the end result is that we can use the lower bounds that I told you about some time ago, and we can use this general machinery that was developed by a long line of people. In particular, the work we use is due to my ex-colleague Mrinal Kumar from IIT Bombay, and Chi-Ning Chu and Noam Solomon. So we use their work together with our lower bound in order to get a non-randomized polynomial identity testing algorithm for constant depth circuits. Okay, so if you're given a polynomial via this representation, which is a constant depth circuit, we can check if this polynomial is the zero polynomial or not in a non-randomized fashion. Unfortunately, an algorithm is not polynomial time, which is what we like. It only runs in sub-exponential time. Okay, so it's much better than just expanding out every monomial, but it's not a polynomial time algorithm, which you'd like to get. Okay, and I should say that it generalizes in some sense a long line of previous results, which did something for depths 3 and 4. In some cases, these algorithms are much better, but they're not as general. They don't work in as general a scenario as ours. Okay, so yeah, unfortunately, I don't have time to review all this beautiful literature, but there's a lot of lovely stuff in this area. Okay, and I should also say that there is potential for improving our algorithm. So we get a sub-exponential time algorithm, but if you improve our lower bound, if you don't just prove that something is inefficient, but if you prove that it's strongly inefficient or highly inefficient, then we actually improve our lower bounds. There's a potential for improving it all the way to close to polynomial time. Okay, so I think, Venkatesh, I'm probably just about out of time, right?
Yeah, I mean, you can take 5-10 minutes, but you could also devote that for questions.
Yeah, I think I'll do that. So I had one more research paper to present, but maybe I can skip that because I think the two things I spoke about are kind of a good, give you a good idea of what's going on. So let me just skip this little stuff. Okay, so just to summarize, right? So my summary finally is in fact this slide, which is to say that algebra is extremely versatile and useful in all sorts of scenarios in theoretical computer science, from the proving lower bounds to designing algorithms to defining algorithms to producing randomness from no randomness and so on. And so this is it's a beautiful area, and if you've not kind of seen some of these applications before, I encourage you to look into them. And yeah, feel free to reach out to me if you would like some sort of help in doing that. yeah, that's all I wanted to say. Thanks.
Thank you, Srikanth. Wow, this is a great summary of good applications of algebra. I see that Jayant has raised his hand. Jayant,
Srikanth, yeah, that was a great talk. I was just curious about what was the intuition that led you to take either the determinant or the permanent for proving those results? Was there some insight that you initially had that told you that this is the specific polynomial that would not get the efficient circuits?
Okay, so that's a fantastic question. So it turns out that this is not our insight at all. This is Valiant's insight. So Valiant, a famous thing about the P versus NP question is that SAT is sort of the prototypical NP complete problem. And if P is not equal to NP, then SAT does not have efficient algorithms. And so what Valiant discovered is that the permanent is the equivalent version of SAT in the algebraic world. So if anything does not have efficient circuits, then the permanent does it. So in fact, we don't do the determinant of the permanent at all. We actually work with some other polynomial. And that polynomial comes from, it's actually a fairly natural polynomial related to multiplying matrices. And it's in fact, we get these consequences for the determinant and permanent as a corollary of what we prove for some other polynomial, because these polynomials are sort of the hardest polynomials in their respective classes.
Okay, thanks.
Sure.
Okay, any other questions? Okay, while people are thinking, I have a couple of questions, maybe somewhat naive. So one question is, you said this algebraic circuit model is special. Are there attempts to show, at least for some problems, that this is actually as general as it can be?
That's a fantastic question. Can we show that the thing is as general as it can be? Well, yes. So let me think. Yeah, definitely by experience, in all situations where the problem is sort of algebraic in this way, the best thing we know is to use an algebraic circuit. There are yeah, so the only connections that I know of go in the other direction, that you can use an algebraic circuit to come up with a general kind of algorithm, which also has some technical subtleties there. But I can't think of any scenarios where actually it goes the other way. Yeah, can't think of anything right now. Yeah. It's a great question. And my suspicion is that though for most problems the answer is yes, I'm not sure that we have any techniques to prove something like this, because just the point is that analyzing general computation itself is so difficult that we don't have any techniques for doing that.
Right. Yeah, the other question is your lower bounds are unconditional, right? So does it make sense to use ETH or things like exponential time hypothesis to prove some lower bounds, and maybe they're conditional but maybe relatively easier to show? I mean, does it make sense?
Absolutely, it does make a whole lot of sense to do that. So I think there are many scenarios where we start with the exponential time hypothesis as some sort of, there is a kind of interesting intermingling of the two. So there are ideas from algebraic complexity, which in combination with the exponential time hypothesis can lead to general hardness results for other problems. So there have been things of this form. So where you assume that, assume some sort of exponential hardness for some problem, but now you use the ideas of algebraic circuit complexity in order to prove hardness for other problems. So these gadget reductions that you use sort of come from algebraic circuit complexity. So in that sense, that's an intermingling of the ideas of algebraic circuit complexity and more standard hardness reductions that come up. Yeah, so definitely that is doable.
Interesting. Okay, I don't see any more. I mean, I'll wait for a few seconds to see if anybody has any other question. Yeah, otherwise, thank you very much for this excellent talk, and congratulations for your Best Paper Award, and wishes for more. And on behalf of the ACM, again, we thank you very much for this great talk. Thank you.
Thanks very much. Thanks to everybody for attending, and thanks for this honor.
Okay, so over to the organizers. I think we have about half an hour break.
Thank you, Professor Srikanth and Professor Venkatesh Raman.
You can sit back, relax, and take a break for another half an hour and join us back for a keynote lecture, interview, chat, and the most awaited session, the award ceremony. We also have some pre-recorded cultural events for you to enjoy. Thank you.
Drgnaka drgnaka jam jam drgnaka drgnaka jam jam tatti drgnaka jam jam drgnaka jam jam takati drgnaka jam jam drgnaka jam jam tatti drgnaka jam jam drgnaka jam jam takati drgnaka jam jam drgnaka jam jam drgnaka dingina ta tatti drgnaka dingina ta dingina
ஆயர் குலத்தினிலா நிறைவேற்றவன் ஆடியும் பாடியும் கூடி மகிழ்ந்தவன் ஆனந்தமானந்தமானந்தமானவன் ஆழி துயில்பவன் அவன் அடிப்பணிவோ
தாமித தக திமி 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 தஜ்ஜம் திமி திமி கிட்ட தக திமி தக தஜ்ஜம் திமி திமி கிட்ட தக திமி தக ஜம் ஜம் திமி திமி கிட்ட தக திமி தக ஜம் ஜம் தாமித தக திமி 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 தஜ்ஜம் திமி திமி கிட்ட தக திமி தக தஜ்ஜம் திமி திமி கிட்ட தக திமி தக ஜம் ஜம் திமி திமி கிட்ட தக திமி தக ஜம் ஜம் தாமித திமி கிட்ட தக திமி தரி கிட்ட தஜம் 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 ததிங் கிட்ட தஜம் 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 ததிங் கிட்ட தஜம் 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 ததிங் கிட்ட
அமலமலர் முகவண்ணன் கண்ணன் காளிங்க நர்தனம் ஆடியவன் கம்சனை வென்றே காத்து நின்றார் கலியுக வரதன் கோவிந்தன் அன்னைய சோதையின் எண்ணம் கவர்ந்திட வெண்ணை உண்ட சிறுமாயவனே உண்மை எண்ணி நிலம் நினைந்துருகும் அடியா துயர் தீர்த்திடும் தூயவனே இன்னும் விரி கடலும் திகழ்ந்திடவே நிதம் மண்ணை உண்ட சிறு பாலகனே யசோதை மணமகள் மாதவனே குசேலர் துயரினை தீர்த்தவனே மாமுனிவர் புகழ் மாலவனே நாமமுறை துணை நாளும் நினைந்திடும் ஸ்ரீ முரளீதர கவித்வமே ஸ்ரீ முரளீதர
धीरेना धीरेना नितोम तनन धीरेना धीरेना नितोम तनन धीरेना धीरेना नितोम तनन धीरेना धीरेना उदन धीम तदन धीम तन धीरेना उदन धीम तदन धीम तन धीरेना धीम तनो धनो तनो धीरेना धीम तनो धनो tanana dhirena dhirena tom tanana dhirena udanadim tadirena udanadim tadirena direna udanadim tadirena direna dim tadirena direna dim tadirena direna dim tadirena direna dim tadirena direna tadim tadirena
Hello everyone, Rishi S. Mahadevan here of the Department of Applied Mathematics and Computational Sciences. I'm here to present a song for ACM Annual Event 2022 and ACM ARCS 2022 at PSG College of Technology. This song is composed by Gopalakna Bharati, legend of times. Song is based out of the Ragam Pehak, Talam Rupagam, and for convenience be converted to Adi Tishram sometimes. Please enjoy the composition. இரக்கம் வராமல் போனதென்ன காரணம் இரக்கம் வராமல் போனதென்ன காரணம் என் சுவாமிக்கு இரக்கம் வராமல் போனதென்ன காரணம் என் சுவாமிக்கு இரக்கம் வராமல் போனதென்ன காரணம் என் சுவாமிக்கு இரக்கம் வராமல் போனதென்ன காரணம் இரக்கம் வராமல் போனதென்ன காரணம் கருணை கடலென்று உன்னை கருணை கடலென்று உன்னை கருணை கடலென்று உன்னை காதில் கேட்க நோம்பே வந்தே கருணை கடலென்று உன்னை காதில் கேட்க நோம்பே வந்தே இரக்கம் வராமல் போனதென்ன காரணம் ஆலமருந்தே அண்ட உயிரே ஆதரித்ததுமது கீர்த்தி ஆலமருந்தே அண்டருயிரே ஆதரித்ததுமது கீர்த்தி பாலகிருஷ்ணன் பாடி தினமும் பாலகிருஷ்ணன் பாடி தினமும் பணிந்திடும் நடராஜமூர்த்தி பாலகிருஷ்ணன் பாடி தினமும் பணிந்திடும் நடராஜமூர்த்தி பழியத்தனை நான் செய்யணும் 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 பாலித்திடும் சிவ சிதம்பரம் பழியத்தனை நான் செய்யணும் பாலித்திடும் சிதம்பரம் என்னும் மொழி கற்றவர் வழிவேற்றுணை முப்பொழுதும்
Hi, Margaret.
Hi, good morning, good afternoon.
Yeah, good afternoon. Would you like to share your screen and check your audio video once?
Sure, let me turn my video on.
Yeah.
Yeah, and on behalf of ACM India, again, I sent you a message, Margaret. Thank you very much for joining us today. We're very much looking forward to your talk.
Oh, it's wonderful to be here. Thank you so much. So there we go. Is that good?
Yes, it looks good, Margaret.
Can I just leave this up here or should I take it away for now?
You can take it away for now because there will be an introduction slide for you.
Okay.
Yeah.
Yeah.
Welcome.
Yeah, we're just waiting for Hemangi Kapoor, who is our Vice President of ACM India and herself works in non-volatile memories, to join us. As you know, she would be the session chair.
Sounds good. So is there, how much of the event is in person versus virtual?
Most of the keynote lectures are all being done remotely from because the speakers are from abroad. But we had been hoping that some of our local sessions could be done in person. But at the end of December, we had a very virulent third wave of COVID because of the Omicron strain. And that put paid to all our plans of having it as a hybrid version. So it's completely online.
Okay. Okay.
Right.
That's a shame. That seems to be the
That's
theme of the past couple of years. And yeah.
Right. In fact, all the events of even the ACM headquarters have been done online for the past year. They're hoping that the June 10th, which will celebrate the 75th anniversary of ACM, could be done in person. But we are all keeping our fingers crossed that there isn't a fourth wave or a fifth wave that will cause us to go back and kind of hide within our offices or homes.
Yeah, we're planning an event for late May to celebrate the 30th anniversary of a group in the US. And it's been postponed multiple times. And so now it's a late May date with an outdoor setting so that we feel a little more resilient to whatever gets thrown this way.
Right. And if you wait a little longer, it won't be the 35th anniversary anymore. It will probably be something a little later. Right. Yeah.
Well, I guess, yeah, it's a computing event. So if instead of celebrating the 30th, we celebrate the 32nd, the 2 to the 5th, that would be okay.
Maybe Shekhar, can you just check with Hemangi and tell her that Margaret is already on board here? Yeah, so Margaret, one of the reasons that we are very keen on having a systems talk is that most of the students and the software industry usually work at the higher levels of the food chain here. And so their focus is primarily on using machine learning algorithms on large amounts of data, but they don't understand systems too well. So we are hoping that your talk would convince them that there are important and interesting issues to work on, even in these in the so-called plumbing areas of computer science.
I'll see what I can do in 45 minutes. But no, we see that in the States too, that there's so much excitement high up in the stack. And yet I think what I'm going to try to say is that a lot of what happens down low in technology is shaping what's happening up in the stack. So yeah.
Right. And any improvements at the bottom of the stack automatically percolate all the way to the top. I think that our students don't realize too well. It's much easier to just run TensorFlow on a large amount of data without looking at the underlying things. Hemangi is here with us. So Hemangi, we're just chatting with Margaret and requesting her to convince our students to work in systems. So,
good morning, good afternoon.
Good morning, Margaret.
Thanks so much, by the way, for the opportunity. I really appreciate it.
It's our pleasure to have you here. Right. We would have loved to have had you in person, but maybe we'll do that the next time around.
Yeah, the music that I was listening to that you had on 5 or 10 minutes ago reminded me of my trip to India a few years back. And yeah, it would be nice to be there.
Where did you visit in that trip?
It was kind of the classic foreigners vacation in India. Me and my sister went. And so Delhi, Agra, Udaipur.
Jaipur, right.
Jaipur,
the Northern
Varanasi.
Triangle.
Yeah.
Okay.
So there's a lot
next
more.
Time next time we need to bring you down south so that in fact this annual event was supposed to be held in Coimbatore, which is in the deep south. But again, as I said, we had been hoping it would be hybrid, but even those hopes did not materialize.
Yeah, I have several recent PhD students from Goa and Kerala, and so
Okay.
it would be nice to see more of the country.
Okay, so you would give your talk in Malayalam then, since your students are from Kerala, right?
I think the AI machine learning folks would have to work on that for me to be able to do that.
Yeah, over to you, Hemangi.
Good evening, everybody, and good morning, Margaret. So can the local organizers put the slide, please?
Yeah, we still have about 5 minutes, I think, to start.
Yes.
It's still right.
Okay.
But maybe you could tell Margaret about the systems work that you are doing in the meantime.
Hi, Margaret. Hemangi Kapoor here. Yes, and I have been working in architecture, mainly in non-volatile memories and bare leveling approaches in particular, at cache level and at the main memory level. And recently we've started designing accelerators for neural networks, but my main focus is on emerging non-volatile memory-based lifetime improvement. And we've graduated around 4 or 5 students in this topic, and very excited to hear. We have been trying to get architectural speakers since few years, but weren't successful. So very thankful to you that you could make it, and eager to listen to you.
I'm looking forward to it. I actually was in a big wrestling match. Are we live to other people, or is this the 20 of us?
We are live, yes.
Okay. Wrestling with the slides to figure out which parts to emphasize.
Okay. Yeah, please then. Please then take another 5 minutes to do this. We can start it. Another 4 minutes, we can begin. So you may please look at your slides.
We hope all of you are back after the break. With a fresh start, we now have a keynote lecture on seismic shifts, challenges, and opportunities in the post-IFA era of computer system design by Professor Margaret. And to chair this talk, we have Professor Hemangi K. Kapoor, Professor of CSE Department, IIT Guwahati. She is a part of ACM India Council and a part of the editorial board of Elsevier Journal of Systems Architecture. Ma'am is also a member of the executive committee of Smart India Hackathon 2019 under MHRD's Innovation Cell. We kindly request you to continue, ma'am.
Thank you so much, organizers. Can we have the bio of Margaret on the screen, please? Yes. So good evening to the Indian participants and a very good morning to Margaret. So we have a third talk of today's annual event with two exciting talks over, and I'm very much looking forward to this lecture of hers. So welcoming her, a quick introduction to Margaret. So Margaret is the H.T. Adams Professor of Computer Science at the Princeton University, where she has been a faculty since 1994. Martinosi's research interests are in computer architecture and mobile computing. Her work has included the widely used watch power modeling tool and the Princeton ZebraNet mobile sensor network project for the design of real-world deployment of zebra tracking collars. So this was deployed in the Kenya. Her research focuses right now in computer architecture and hardware-software interface for both classical and quantum computing systems. Martinosi is a member of the United States National Academy of Engineering and a fellow of IEEE and ACM. She is the recipient of 2021 ACM IEEE Eckert Mockley Award for her contributions to power-efficient computer architecture. Today, she is speaking about seismic shifts, challenges, and opportunities in the post-ISA era of computer system design. Welcome, Margaret, and over to you.
Thank you so much, and good afternoon, everyone, and good morning to others of you who are out there in other time zones. I'm going to share my screen.
Yes, it's visible.
Great. Okay, wonderful. It's wonderful to have the opportunity to talk with you today, both about a bit about my group's research work over the years and also about sort of our shared vision for the way forward across many layers of the computing stack. As a computer architect, we sit in sort of the middle of the stack, watching the application trends up above us, AI, machine learning, and so forth, and also reacting to the technology trends below us. And it's been quite an exciting time. You might be wondering what this picture is on my slide. This is a picture of a region in one of the Western American states, Utah, called Water Pocket Fold. And this region is about sedimentary layers of rock that were laid down over many years, and that seismic action has tilted sideways. And I use this as a metaphor for the way that our computing layers that we've gotten used to are now being tilted by application and technology trends that we're facing. So with that, here we go. Many of you have heard of Moore's Law, and it's been in the news a lot. It's for many of us, nothing new. What this graph shows is about 40 years of microprocessor trend data to show Moore's Law scaling as it has proceeded. So from 1970 to 2020, you can see that these orange triangles are on roughly a straight line. And with the logarithmic y-axis, that means that that's the exponential doubling that we've come to expect from transistor counts on chips. That's what Gordon Moore predicted over 50 years ago. But clearly, other aspects of these trends are already leveling off or changing. In particular, the number of cores on chip took a big bump up about 15 years ago, indicating that we're using new techniques to stay on top of the Moore's Law scaling. And so while we often talk about Moore's Law and the transistors doubling on chip, what we talk about much less often is what's happening under the covers, what is happening already in your cell phone, in your laptop, and in the data centers that are running the AI and machine learning applications that so many of us and our usages out in the world are depending on. In particular, this bump up in the number of cores on chip means that both we're changing the programming expectations to be more about parallel programming, even on individual mobile apps or individual software systems. And even more so, the number of cores on the chip, they can often be different. So it isn't just general purpose processors, but as you know, it's a wide range of accelerators. With that, we're changing not just the system way down low, far below where most software people see it, but we're changing it in a way that is actually changing the whole stack. That gets us to that seismic shift picture from the previous slide. The whole set of rocks have shifted, not just the bottommost ones. So Gordon Moore sketched out Moore's law in 1964. Something else happened in 1964. And that is that the term computer architecture, the name for my research field, was coined. You can see it. It's down here in the fine print in the footnote, which I've blown up here, of a paper by IBM, Amdahl, Blau, and Brooks, a classic paper on the IBM System 360. And the purpose of the System 360 architecture was to say, we want a layer where above that, the software can remain unchanged. And below that, we can have different implementations targeted at different price points in IBM's case, or sort of evolving over time, and yet still run the software unchanged. And it really highlighted the value of hardware-software abstraction. So both of these things happened nearly 60 years ago now. So where are we now? Oh, gosh, I knew I needed to update one more thing. 2022, we are here now. So where are we? This is the sort of block diagram for a chip that you might see in a cell phone. We see heterogeneity all over the place. First of all, we see heterogeneity in the large. There are literally thousands of different devices that we are programming to, thousands of distinct Android devices. If you add in the different laptops with different accelerator sets, the different data center implementations with their heterogeneity, and IoT, there's tremendous heterogeneity in what we're programming to in the large. If you look inside any one of those chips, you will also see heterogeneity. So this is a view inside one chip, and what we see are a set up in the upper left of general purpose cores, but we also see a wide range of graphics cores, accelerators, and so forth. Programming to this is very different than programming to the vision that Amdahl, Blau, and Brooks had in that 1964 paper. And yet we still need to figure out how to navigate a way forward that includes some of that abstraction. And that's where I view this not just as a thing for the transistor folks to think about, not just as a thing for the architects to think about, but this is really causing that seismic shift up and down the stack. It's a thing for the AI and machine learning community to think about, the programming language and compiler people to think about, and so forth. So there's heterogeneity in terms of the different numbers of instruction set architectures, or ISAs, on a chip, as well as the accelerators. There's heterogeneity in terms of the memory architecture here. Himanji, for example, looks at non-volatile memories. They shape how we program these systems. There's heterogeneity in the data, and there's also heterogeneity in something called memory consistency models, which are the rules by which different parts of the system communicate and agree on event ordering. So the seismic shift that I mentioned is basically the following. Instruction set architectures are still useful. A great example is the x86 instruction set architecture, which has its roots from the 1970s. You know, many of you probably weren't born when x86 was born, and yet we still run systems every day that are based on x86. So over time, it has proven the value of these sort of long-term durable instruction layers. They are still useful, but they are less relevant as particular abstraction layers. So for example, if you look at the Apple sequence of processors that they've designed for their phones and other devices, Apple A8, which I think is now nearly 10 years old, from that point forward to the present, over half of the chip area is devoted to accelerators that have no instruction set architecture. So we walked away from abstraction in that case. If you look at NVIDIA GPUs, they have an instruction set architecture. They choose to hide it underneath other layers like CUDA. So people are programming to CUDA rather than to the actual chip instruction set architecture. And so we're seeing that while we have recognized the value of these abstractions, we're also walking away from them in different ways. And the question as we go forward, there's many questions, but the ones that I'll sort of take on in this talk are listed here. How are we going to program these kinds of systems going forward so that we retain some of the portability benefits that we had 50 years ago when ISAs were new? How do we verify them? Because if chips are changing as fast as they currently are, how do we have any sense that they're working correctly? And how do we know that software, which also has to change quickly for portability reasons, is also correct? And then I'll talk a little bit about what technologies might come next, because we are sort of reaching real challenges in semiconductor scaling and Moore's law, and that's going to affect not just the bottom, not just how the chips are fabricated, but again, this whole stack. I'm going to talk today about what I would call post-instruction set architecture hardware design, and then I'll talk about its implications up the stack from there. So back to this picture, systems on chip, which are the pieces of hardware that are inside our phones, our laptops, and our data centers, are comprised of many CPUs, yes, GPUs, graphics processors, and accelerators from many different vendors. And so some of the questions have to do with how to verify that a given block, say this one, is doing what it's specified to do, and how to actually specify it in a way that will be sort of endurable across different system evolutions. So I would argue that more so than in 1964, when the first instruction set architecture was put forward, we need more formal interface specifications. So x86 was put forward as a set of vocabulary for the hardware that was about things like add, subtract, multiply, but it didn't even specify the format for those additions or divisions and so forth. We need to get back to a world in which we better specify those things formally so that we can verify them more carefully. And I will motivate that and give some examples as we go forward. So one of the, if folks could mute, that would be helpful. I hear a little bit of background noise. Thank you. So one of the ways in which my group took this on was by, again, viewing this as a full stack approach from the low-level hardware up to high-level languages. And I'll give some examples briefly in this talk. So we started with a very sort of basic question and very much focused in our own part of the stack, the architecture layer itself. And we came up with a tool called PipeCheck. The basic question that PipeCheck sought to answer was, if you give me a description of a particular microarchitecture, a particular implementation of a pipeline, how can I check whether it actually abides by what are called the event ordering or memory consistency requirements that the architecture has asked it to? That seemed like such a basic question. We should have answered it by now. And yet we hadn't. So we took that on to begin with. And then as we went forward, we built out a full stack set of tools that go from the Verilog, the low-level hardware, up to the programming languages to check this at different levels, to be able to verify at different levels that these levels were actually upholding certain event ordering constraints that the architecture said they should. And basically, this is revamping our view of architecture to take on the new challenges of these kinds of modern parallel systems. After a while, so our basic approach looks like the following. In modern parallel systems, like the pictures I've shown on the previous slides, there's an awful lot of different parallel blocks. They're doing things concurrently. And a fundamental question is, are those concurrent events happening in a correct order? So what we did across all these tools was we built a set of axiomatic specifications from which we could generate what are called happens before graphs. Happens before graphs are in some ways complicated, in other ways as simple as the name indicates. They're about checking whether things happen before each other in the correct order. And in particular, for a given system, we would have a set of rules about that system that would say, for example, that A should happen before B. We would have another rule that might say that B should happen before C. And if we have another rule that says that C should happen before A, we have a cycle. One of the key ideas of a happens before graph is to say that if we take the conjunction of those rules, the transitive closure of those rules, put them together, we're saying that A happens before B, which happens before C, which transitively says that A happens before itself. Clearly, that's impossible. So we've actually been able to use the sort of collection of these rules to reason about what event orderings are either possible or not possible in a given implementation. And from that, we can highlight for designers or for programmers possible bugs in the system or possible security flaws in the system by highlighting things that are observable that might happen that they didn't intend, that they didn't want. So this is the basic approach, and I'll go into a little more detail on the slides that follow. But I also wanted to note that from the right-hand side, which is really about checking for correctness, we went to other things, including checking for security flaws. So if you identify certain orderings that the designer didn't intend, but that might happen, these can often be exhibited as security vulnerabilities that the bad guys can take advantage of, such as Inspector and Meltdown, the much publicized bugs of a few years ago. So we'll talk about some research results that we have related both to correctness errors that we have found in real systems and also to security errors that we have found in real systems. So I want to take another trip in the Wayback Machine. I've talked about 1964 a little bit. Let's talk about 1979. In 1979, Leslie Lamport, who subsequently went on to win the Turing Award for this work, articulated a notion of event ordering that has come to be called sequential consistency. And sequential consistency says that if you have a system in which there's a set of concurrent events, sequential consistency gives system designers a rule for how those events should occur, what order those events should occur in. And in particular, sequential consistency has two big rules to follow. Rule number one, the memory operations of each processor should appear in program order. And rule number two, the memory operations of all processors together were executed in some global sequential order that they all agree on. So here's a program on the left with two threads, one in black and one in orange. Rule number one says that the X equals 1 event has to happen before the R1 equals Y event. So within a thread, they have to appear in program order. Rule number two says that all the processors have to agree on the order. And so here are the 6 legal interleavings of these 4 events for sequential consistency. This looks, sort of reasonable. You can either have the X equal 1 event followed by the Y equal 1 event, followed by the R1 equal Y event, followed by the R2 equals X event, and so on. So that's one of these. That's this ordering. But you can have other orderings depending on how they play out over time on these parallel machines. This is great. And if it were 1979, we'd be pretty happy with that. The issue is that modern processors are built in ways for which this is too limited. And so we have taken on different and more elaborate execution orders. In particular, the modern Intel processors have a slightly more complicated execution order. This is just a piece of the rule book for the Intel Total Store Order, or TSO, execution order. And I'm not going to ask you to read this rule book. I'm not going to ask you to understand each word that's here. What I want you to remember is this thing that I'm talking about, this event ordering that I'm talking about. It seems pretty obscure. Like I thought she was going to talk about architecture, and now all of a sudden she's talking about these funny little consistency models. The key idea here is that these memory consistency models form the specification of what value will be returned when your program does a load. So I don't care whether you are way up high doing artificial intelligence or way down low. We all need to know what value will be returned when our program does a load. And it's important to specify and verify that. And an awful lot of people, when they get to this point, they say, oh my gosh, isn't this done yet? How can this still be open research? And yet the ability to check that our modern systems are actually executing in legal orders is both largely an unsolved problem, or it's an incompletely solved problem, and also sort of fundamental to so many things that we do, from sort of trustworthy AI to security systems and so forth. So what did we do about it? I want to show you a little bit about the it happens before graphs that we first developed in that initial implementation, and then where we took them. This is going to look a little obscure, but hopefully I'll sort of take you through it slowly and bring it back to this notion of why it matters. Hopefully some of you might remember from an architecture class a set of pipeline stages: fetch, decode, execute, write back, and so forth. And so what our microarchitectural happens before graphs do is they take that sort of organizational view of a pipeline, and they start sort of using that to reason about which things might happen in parallel between different instructions and which things might happen concurrently. And in particular, if I go back a couple of slides, Lamport was thinking about these instructions as sort of individual granules that were indivisible. But actually that X equals 1 instruction, or that R1 equals Y instruction, we know now that on modern processors, they're being executed in a pipeline that has different stages. They look more like these pipeline diagrams. And so one aspect of what we wanted to do was to build happens before graphs at this lower level, at this microarchitectural level. And so what we have here are a bunch of arrows you can see, all of which are different aspects of the rules on how this system is supposed to execute in order. So for example, we would like fetch to happen before decode. We would like for decode to happen before execute. That seems like just normal correct operation. This column A, B, C, and D correspond to the different instructions in this little program or litmus test that we're going to check system behaviors on. So each column is an instruction that's actually flowing through its execution, and the arrows correspond to how the system will actually impose ordering, not at the level of instructions as a whole chunk, but at the level of individual pipeline stages. So once we do that, we can actually build tools on top of that to come up with different ways to specify what should happen in a system and then check it. And so in a real system today, we're going to have multiple of these pipelines. We're going to have a cache coherence protocol. We're going to have some accelerators. We're going to have sort of an awful lot going on. But across all of that, what our approach allows us to do is to create a set of rules, a set of axioms for the ordering of the events in that complicated system. And while the syntax might be a little obscure, hopefully some of this will ring true to everyone out there. For example, this rule here says that things should happen in program order. I should fetch instruction 1 before I fetch instruction 2, and I'm going to call that program order. And I'm going to add an edge to the happens before graph that articulates our desire to have instruction 1 happen before instruction 2. That seems pretty basic, that we have to sort of draw a graph to show program order. But given the complexity of modern systems and given the potential for really bad vulnerabilities like Spectre and Meltdown, this is the level at which we want to specify and verify things. You could also, in some processors, have an expectation that execute happens in order. But as you might know, some processors are called in-order processors, and some processors are called out-of-order processors. And so while many processors will have this expectation that instructions are fetched in order, Only some processors will have this axiom that the execution stage is in order. So different designers can write out different rules that express the nature of their design. And at the microarchitecture level, this allows us to consider all possible executions. Now, as computer scientists, probably pretty quickly, the minute you hear words like exhaustive consideration of all possible executions, you get worried, right? Because that's an exponential, and it sounds like it's going to take forever. Fortunately, I'm an architect, but fortunately, those of you out there who are from the formal methods community, the satisfiability solvers community, the satisfiability modulo theory community, SMT solvers, have done incredible work over the past 25 years to make these kinds of logic explorations much faster. And so we use SMT solvers to come up with very efficient ways to explore all possible happens before graphs for a given microarchitectural specification. And this is the key to our idea. We want to be able to specify things formally, and we want to be able to do it early enough that it happens well before the chip is designed. We want to be exploring these possibilities when the chip is just a block diagram on paper, so that we can catch bugs much earlier, and so that we can also project those specifications up towards programmers more efficiently as well. So I talked a little bit about that microarchitectural layer, but actually this same approach can do many other things. I don't expect you to zoom in and see what's going on in this figure here, but this is a happens before graph that we generated automatically and we checked automatically. This particular happens before graph has a much more complicated pipeline. You see things like fetch and decode, but you also see an awful lot that has to do with actually the operating system translations from virtual to physical memory, the potential for translation look-aside buffer error misses, the potential for pages to not be in memory and to have to go out to disk. And so all those kinds of potentially concurrent, potentially interleaved events are expressed for a piece of code that you can still see the columns. These columns are still instructions just like before, but now some of the instructions are user level. Those are the ones in black. Some of the instructions are related to underlying hardware events, like page table walking. And some of the instructions are kernel level instructions as we bring in new pages. That's what the red and the blue signify in this top thing. So again, nobody would want to check this by hand. Our approach uses SMT solvers to check this automatically. And in particular, it all goes back to that early slide about looking for cycles. What we look for are cycles through this graph. You can see that one that's highlighted in bold edges here, that's a cycle that the SMT solver found in our tool that basically indicates there is a very intricate interleaving of events that might be problematic, that might cause an error in a design. And the fact that we can find this early and efficiently lets us find errors sooner. So I'm going to pause here and I'm going to up level. I'm a computer architect. I talked a little bit about instruction set architecture. What I'm talking about now is what are new specifications that we can use that will give us the value of abstraction. And so I'm arguing that one of these specification layers we should be using are some of these axiomatic approaches that let us actually formally check from one layer to the next that the right things are happening. So why do this? Here's a real example from 5 years ago. We used these tools, the very tools that I'm talking about, to describe the RISC-V instruction sets memory ordering rules. And then we looked at a range of legal RISC-V designs. So RISC-V is an open source instruction set that's now getting sort of wide usage worldwide. At the time, its specification was still in draft mode. And what our work learned is that there were cases where something that was legal in the C language could not be correctly compiled to any or to some RISC-V CPUs because of errors in the draft specification. So this is where this work went from, oh my gosh, it's just little microarchitectural pipeline tweaks to, wow, this is now a full layer thing where we are checking languages and their specifications against hardware and their specifications. So this is where that seismic shift across the full stack becomes real. So we found these issues in 2017. RISC-V, the open source community, formed a memory model working group to address these issues. And by 2018, a new improved RISC-V memory model was ratified, and it's formally verifiable. There are formal models available for it. So it's a real success story in getting from errors to not just sort of getting rid of those errors, bug fixes, but also to this new approach that is hinging around formal specifications that can be verified at different levels of the system design. Okay, so that was correctness. I want to talk a little bit about getting from correctness to security. And this is an example of a smart student sees something in their work that the smart professor hasn't even thought of. And so I give tremendous credit to Caroline Triple and Dan Lustig, my former students, now PhD researchers elsewhere, for sort of identifying this opportunity and moving forward on it and finding something really impactful. So I'll get back to happens before graphs, but before I do that, I want to say, what would you like as a security researcher? If I were a security researcher, what I would like is I would like to be able to say, here's the system I'm worried about. Here's a potential attack. Tell me whether this system is vulnerable to that style of attack. Wouldn't that be nice? Because a lot of what security folks do a lot of the time is stare at a system and try to reason about whether it's vulnerable to attack. Or they're in a big room with a bunch of smart people and they're arguing about whether it's vulnerable to attack. Or it's just a race, right? Good guys and bad guys, each trying to figure out whether there's an attack vulnerability that's possible on a system. And if the bad guys figure it out first, we're not very happy about it. So this is what we would like. And what we actually have, you know, in many cases is something that is not nearly as synthesis driven, not nearly as automatic, but it is instead just based on people sitting and thinking about it. We wanted to take this flow and make it real. So what we did is we developed a tool to do exactly this 1, 2, 3 step based on those happens before graphs, those microarchitectural happens before graphs from previous sections. And bottom line up front, we automatically synthesized Spectre and Meltdown, as well as 2 new distinct exploits and many variants. And we notified folks and so forth. So how did we do that? The key idea here is, here's that set of axioms from before, same as I showed about 5, 10 slides ago, rules for the order in which things occur in the microarchitecture. And if you think about what Spectre and Meltdown were, they were cases of vulnerabilities where a particular ordering was possible and could be exploited for a security problem. So what we did is we said, this set of rules will be our way of denoting which orderings are possible. And we will use something called a mu-HB pattern to denote a sort of simplified or abstracted version of a particular exploit. So for example, I'm not going to go into detail about some of the terminology here, but believe it or not, this little red graph of 3 different nodes is a stylized description of one of the key elements of the Spectre security exploit from several years ago. Basically, the fact that loads can be taken from something called a store buffer in certain situations. So we take the microarchitectural rules we take these patterns for potential exploits and we enumerate all the possible UHB graphs, same as before, that include this pattern. So basically, we're enumerating all the ways that a particular program could run that would cause this pattern to appear. And so what did we find? We found, and as I said, so the result of this is that not only did we sort of show formally how Spectre and Meltdown were being created, but we also were able to identify new vulnerabilities. So the ability to exhaustively enumerate allowed us to find what we called Spectre Prime and Meltdown Prime before others did, before the quote unquote bad guys did. And so this was a big deal, both in terms of being able to find those particular vulnerabilities, but also being able to show a methodology that lets you explore these things more exhaustively and more automatically than the sitting in a room and hoping that the good guys beat the bad guys kind of a model. So overall, where are we with this? In terms of correctness, we have used our tools to find bugs in a widely used research simulator, a paper about cache coherence, some InDesign real commercial processors, and a bug in an IBM compiler that was quickly fixed. And we appreciate the fact that IBM lets us mention that this was a bug, and we appreciate how quickly they fixed it. We also sort of note that the entire RISC-V ISA's specification on memory consistency models was reworked due to our work. We found flaws in proofs in a paper because the proofs had certain lemmas that were not actually always true. Our tools were able to exhaustively demonstrate that they were not always true. And so those proofs got corrected. And in standards discussions, the C11 memory model is being refined due to findings of our work. Basically, when we found that the C11 memory model couldn't be supported by the previous RISC-V specification, that led to quick changes in the RISC-V specification, but it also led to consideration of whether maybe the C11 memory model was asking for things that were too hard to implement. Okay, so what are the takeaways? What are the overall philosophy things that anyone can take from this? First of all, it's about moving from ad hoc analysis to formal automated techniques, because that's a real brain saver, right? In terms of both getting designs correct and also reasoning about computer security, which is going to become more and more and more important. So that's number one, where things can be formal and automated, let's do it. Number two is to say, it needs to be done early in the design process. We can't wait for Verilog to exist and then start verifying. We need to verify earlier, where we can actually flag these kinds of hardware software errors long before all the hardware exists, because it's too expensive if the design is already finalized. We also need it to be efficient. We want it to be an hour or less for our tools. And I think that might surprise people, because you've heard me say exhaustive, you've heard me say exponential. These tools run in less than an hour because of the high level and axiomatic approach that we're often bringing to bear, and because of all that SMT solver work that other folks have done over the past 25 years. So that means you can press a button, go out to lunch or dinner, and when you come back, you may have found bugs in your system or security vulnerabilities that are going to save an awful lot of time and effort down the road. So the key insight is the degree to which event ordering becomes central to a lot of these different problems. Started out thinking about it as correctness, shifted to thinking about it as security exploits. Another thing is the degree to which this is not just a hardware thing, this is a full stack seismic shift that we're talking about. So with that, I'm going to move into another gear. And in particular, I'm going to acknowledge now that everything I've talked about up till now has been basically saying Moore's law is ending. It's causing us to design systems in a certain way. But everything I've been talking about has largely been around systems that are still based on the good old CMOS semiconductor transistors that we've been using for a while now. But we know that we're going to need more technology options very soon. And so there's a real question of what technologies come next And I'm not going to design the low-level technology. That's not where I work. But I do think it's really interesting and important for the rest of us up the stack to be thinking about, as those new technologies sort of emerge, what are they going to do to the rest of the stack? How can we program for them? How can we make use of them? And there are a lot of new technologies that are emerging right now. DNA storage, non-volatile memories, and quantum. I've happened to sort of get into quantum computing as my sort of exploration in this space, not because it's the only answer to what technologies come next, but because it happens to be something where it was interesting to me. I had some colleagues to work with. So I'm going to talk a bit about quantum, not as the only answer, but as an interesting possibility, and talk about what it does to computer architecture. So quantum computing, we're not sure whether it's on a Moore's law or not. But what we can see is some of the following. So quantum computing is getting close to 40 years old now. It was originally proposed by Feynman and others in the 1980s as a way to solve very large physics simulations. By 1990s, we were starting to actually build single quantum bits, the equivalent of a transistor, a single transistor. And from 1990s to the present, we've gotten a bit better at building those quantum bits, but there's an awful lot still to be done. So what does this graph shows? This graph shows 1995 to roughly the present. On the y-axis is a count of the number of qubits. You can think about this like a transistor count, but remember that quantum bits or qubits are far more powerful than individual transistors, because an individual transistor has a 0 or 1 state that it can express. Quantum bits, qubits, can express a superposition of states. And so the state space grows exponentially with the number of qubits. So as we get better at building qubits, we do get much more computing power. A 100 qubit machine, if it worked with sufficient reliability, would be more powerful than any supercomputer we have on Earth. So, but here we are, 1995 is where the first quantum algorithms were proposed and published. And in particular, you may have heard of Shor's factoring algorithm. Shor's algorithm, proposed in this mid-1990s, proposed a way to do factoring of large numbers on a quantum computer that seems to allow for exponential speed up compared to classical systems. What is really key about Shor's algorithm is that this problem of factoring large numbers is central to many of our current crypto systems. And if someone in their basement had a quantum computer that could factor those large numbers in a tractable amount of time, they could break crypto systems, because crypto systems are built on the design premise that that factoring will be intractable. So that proposition that I just described has carried quantum computing for the past 30 years in many ways, because it's given us a reason to care about the applications to implementation space for quantum computers. But here's the thing, Shor's algorithm for the kinds of crypto systems that we currently use would require thousands or millions of qubits. And we are currently building roughly 100 qubit machines. So there's a big gap between what Shor's factoring algorithm needs to be, quote, interesting, practical, or useful, and what we can build. The yellow line on here shows, roughly speaking, how our capabilities are improving on building qubits. We're getting better. And one of the things that I show here is the yellow line sort of tilting upwards or downwards. We don't actually know what trajectory we're on, much like Gordon Moore didn't particularly know fully that we would keep doubling transistor counts every 18 months. But we can project that we are getting better at building quantum computers, and so this yellow line might tilt upwards. Even so, there's a considerable gap between what applications need and what current quantum systems can build. And it's in that gap that a lot of interesting work lies for system designers, for architects, for programming languages people. Because in essence, quantum computing programming, design, and architecture tools can shrink the gap between the blue and the yellow. And that will actually move the feasibility point, the usefulness point of quantum years sooner, either by lowering the blue here, reducing the number of qubits that an algorithm needs, or by raising the yellow, improving the effectiveness of hardware qubits. And one acronym that gets used a lot for where we are now in quantum is NISQ, for Noisy Intermediate Scale Quantum. So these are quantum systems that we can build sort of in dozens of qubits, but each qubit has a high error rate. And so it's noisy. Each operation has a high probability of getting the wrong answer. So imagine if you were writing programs for something that A, was very constrained, and B, each operation had a high probability of getting the wrong answer. That's a pretty challenging landscape to navigate, and yet an interesting one because of the potential that it might offer. So I want to give one example of how architects like me look at our opportunity to contribute to this space, to contribute to connecting from applications to implementations in this quantum area. And in particular, this is a study we did a couple of years ago, considering the design choices to be made in different implementations of these noisy intermediate scale quantum, or NISQ machines. And we put on our architecture hats. We said, what are the gate sets that these quantum systems could use? Now, gate sets is a word that I haven't used in this talk up till now, but guess what? Gate set is basically instruction set. It's what is the vocabulary of operations that this machine knows how to use. A second relevant question is called the connectivity. So how do different qubits in the machine get connected to each other so that they can be interactive with each other? If you had all-to-all connectivity of the qubits, it would be much easier to design and run quantum programs. But many quantum systems, for a range of technical reasons, can't have all-to-all connectivity. So how much does it constrain things to have less than all-to-all connectivity? And the last thing is the noise properties of the qubits. I already mentioned, imagine a world where the memory forgets itself every once in a while, and every add, every subtract, every operation gets the answer wrong with some probability. That's where we are with NISQ. And so we have to consider how to build useful systems in the face of these kinds of constraints. What we did was we did real system runs across 7 existing NISQ systems from 3 different vendors. We did this study in 2019. If you did it today, there would be more vendors that you could use, and more of them would be publicly available as cloud-connected platforms. And so that's a pretty interesting opportunity, and one that I would encourage many folks in the audience to consider your role as computer scientists in sort of exploring them. IBM is a very well-known cloud-connected quantum platform in the IBM Quantum Experience. You can go onto it today. You can register, you can get an account, you can run on a 5-qubit machine today. It's pretty amazing. There are other systems available as well, Amazon and so forth. So, so this is out there. What we chose to do was to sort of target 7 different implementations, but with a single compiler. And I won't have time to go into detail about our compiler, but it's a single compiler so that we could have fair and accurate comparisons and not sort of have our conclusions be shifted by, one vendor's compiler is better at this operation and another vendor's compiler is better at another operation. So we used a single tool flow. And then we pulled in insights about what we learned from this process. I'm not going to have time to go into a lot of detail, but we took a set of teeny tiny programs. You can see the names of them here and the number of qubits they need here and the number of gate operations that they need here. And we ran them through this single compiler that we had, and we ran them on the real system implementations that are listed here. This is an older study. The world has changed. But the sort of philosophy of this study about sort of taking common optimizations and running them across different systems, that remains. One of the things that I show here is the connectivity of the qubits in the system. So this is, the top one is a 5-qubit machine, and you can see how the different qubits can interact with each other through these directed arrows. I mentioned that we'd love all-to-all connectivity. For the most part, these machines didn't have it. The one that had all-to-all connectivity was a trapped ion technology machine from the University of Maryland in the US. This kind of technology is now at the heart of IonQ, a company that's gone public recently. But you can see you get all-to-all connectivity, but you get relatively few qubits. And that's one of the design constraints that our later work sort of dug in on. Putting it all together, you get a graph like this. For folks in sort of the computer systems, computer architecture world, we see a lot of bar graphs. And you might say, well, what's the big deal? This was actually the first time that this kind of comparative bar graph was done for quantum systems and to span vendors and to span technologies. The y-axis is a little funny. It's not speed. The y-axis is success rate. If you run a program 1,000 times, what fraction of those runs get the right answer? That might be a little bit surprising to folks who are used to more reliable systems, but that's where we are in quantum. What you can see within each one of these clusters is one of those benchmarks that I mentioned. Some of them, you can see X's for. Those are cases where this is an 8-qubit benchmark, and some of our systems didn't have 8 qubits. They simply cannot run it. We've done subsequent research on cutting large benchmarks to run on smaller quantum machines. I'll talk about that some other time. So what you can see is that there's an issue of success rate. There's an issue of just capacity that shows up in some of these graphs. But it is interesting to see how different trends emerge. So for example, the UMD trapped ion machine, which is this rightmost bar, works extremely well in terms of the success rate for the benchmarks that it's big enough for. But there are many benchmarks that it wasn't big enough for. Other machines work quite well across more benchmarks because of having made the choice to be larger, say 16 qubits, even though the error rates and the connectivity might not be as high, might not be as good. And so these are the kinds of design trade-offs that we as computer architects and computer systems folks can bring to this space. So popping back up and in closing, I want to make an analogy. I wasn't alive in 1950. Many of you probably weren't alive in 1950 either. But if you go back to what classical computing looked like in 1950, it looked like a little bit like the thing on the left. Algorithms way up high, implementations way down low. In particular, in 1950, Alan Turing was already thinking about, can machines think? It's sort of mind-blowing to imagine that he was sitting down thinking about artificial intelligence at a time when we had barely built electronic computers at all. They were not built out of transistors in 1950. We had designed a transistor, we hadn't yet implemented a computer out of it. So computers in 1950 were built out of vacuum tubes and relay circuits. So one lesson learned is when you're thinking about what technology will win, you have to think forward and be open to new technologies. So right now in the quantum space, we have some different front runner technologies for quantum systems, but it's not clear which of those will win or whether something else will win, similar to how transistors ended up winning out over here. The other thing that we can sort of make an analogy to is that in 1950, we didn't have high-level programming languages yet. We didn't have a notion of architecture yet. That came in 1964. There was so much we didn't have in the middle here that we developed over the decades that followed. And so the really interesting thing for me as a computer scientist working in the quantum space is how will we fill in that box for quantum? We're starting to get a notion of a to-do list. And I won't go through like each of these to-do items in detail, but this is kind of the checkbox of things we have to figure out to make quantum real. But what we don't know yet is it going to organize into layers like this or something else? And in particular, we're sort of familiar with this classical layering. But I started the talk with that picture of the rock layers being turned sideways. And we're seeing that in a lot of our different post-ISA tool flows. For example, TensorFlow and TPUs is an example of going pretty much from a high-level API or language straight down to circuits rather than stopping with some of these intermediate abstraction layers. Quantum could very well be quite similar, that we might go straight from high-level programming languages down to quantum implementations. So I bring in the quantum partly because I find it so fascinating, but also because it actually aligns with what is also starting to trend on the classical side, that we're seeing this seismic shift in computer systems design that's permeating through all these layers on the left and increasingly creating these columns on the right. So what does that mean? It could mean that we change how we teach our classes. It could mean that we change how we organize our conferences. It could mean a lot of different things, and it will probably mean it both for quantum and for classical. So with that, I want to thank my students, my co-authors, and many funding sources that led to the work you see here. And I'm happy to take questions in any time that remains, but before I do that, I want to do a hard pause and I want to bring up one more slide because I'm currently, I'm a professor at Princeton, but I'm on leave from Princeton to serve at the America's Basic Science Research Funding Agency, which is called the National Science Foundation. And I'm really thrilled that just this past week, we released a partnership approach publicly between US researchers and researchers from India that allows for new opportunities where the folks from India get funding on their side, the folks on the US get funding on their side, and there's opportunities to collaborate. And so what I'm going to show you is what your US colleagues and collaborators are now seeing. It's a set of opportunities to support supplemental funding requests on the US side to conduct US-India collaborative research. A lot of what is here is for the USPIs to think about as they think about how they might get this supplemental funding. But I would encourage you to think about whether you have colleagues in the US with whom you might want to join forces on some of these collaborations. You can see some of the relevant dates coming up. I did 99% of this talk with my Princeton hat on, but I did want to get the word out about this new opportunity. And I would encourage you to reach out to US academic researchers with whom you collaborate to see if this might be of use. There are certain topic areas that are highlighted, so be aware of the different kind of constrictions on it, but this is out there and we would love to see it get a great response. And with that, thanks very much. And if time permits, I'm happy to take a question or two.
Thanks, Margaret. Yeah, there are a couple of questions in the chat box. The first question is related to, I see, Meenakshi is asking, what is the average number of the happens before graphs that you have encountered in the real models, and how large are the cycles in the bad examples?
So that's a great question. So we use SMT solvers to do this. And in many cases, the SMT solvers can rule out entire chunks of the space early using logical methods. So what would be exponential in the number of orderings becomes less than exponential in terms of how the SMT solver actually deals with them. And that's where you get, as I said, runtimes in seconds or minutes, not hours, not days. How large are the cycles in the bad examples? The cycles are sort of often less than 10 steps, 10 or 20 steps. And when we added in the operating system behavior in that most complicated graph, it's a little bit more. But the key is not that the cycles are long, but that it's an intricate set of steps that would be hard to reason about as a human. And so the automation helps a lot in terms of navigating this.
Yeah, thanks. The next question is
Yeah,
from...
thank you.
Hi. I think maybe the panel attendees also can ask, because there are only a few questions instead of I reading out. So Arka Prava, would you wish to ask it live to Margaret? Okay, I don't know whether he has access to asking. Okay, so the question is, Arka Prava has nicely appreciated your talk, and he says that you pointed out earlier in the talk about that memory becomes heterogeneous. So for example, persistent memory. So how do the checkers you mentioned are applicable to or are extendable to the memory persistency models?
Yes, that's a great question. Everything about the approach is extendable to persistency models rather than consistency models. Because again, with persistency models, there's a notion of event ordering. I need to know who's reading when. I also need to know who's committing when, right? And that affects things. So everything about it is extensible. I would love to see it extended. We actually at one point were talking to persistency folks about doing that extension. But in a world where to-do lists are longer than hours in the day, we never got around to it. So I would hope that someone else would take that up because I think it's a really interesting opportunity.
Thank you, Margaret.
Thanks. A question related to Spectre. You said that if the load sources from the store buffer, it causes an error. But if it's from the same thread, we should be permitting it, or how do you check the cycle across the threads doing this loading earlier than the memory from the buffers?
Right, that's a great question. And one of the things that I didn't have time to get into in this talk is that we have constructs in our happens before graphs for tracking whether we're reading an old or a new value. And it's called values in cache lifetime, VICLs. And so with these constructs that actually can keep track of essentially the lifetime of data in different storage units, whether it's the TLB, the cache, and so forth, we can use those to know whether it was an appropriate value that was being read or a not appropriate value. And that's pretty central to the security thing. It's pretty central to the correctness thing too, because a lot of what we're doing in consistency models is, did we read the right value? And so that notion of had something been rewritten before I pulled this value out of this storage element is pretty key to a lot of what we do. And so this notion of a VICL construct that helps us track the lifetimes helps us deal with a lot of those, both in the correctness side of our work and in the security side of our work.
Oh, okay. And how about the prefetch buffers? The cache prefetching happens and then we read from there. So do they also matter in your happens before graph?
So the neat thing about the happens before graph is that these kinds of constructs work across a lot of different places where values might be stored. So we started out looking just at caches, then we added in things like TLBs. Clearly, the values you're storing in TLBs are actually metadata, not data, right? I mean, it's things like, what's the page mapping rather than what's the data itself? And yet it's still important to track the ordering of those values. So for example, some of the things that we can check is not just, did we get the correct data in the right order as a sort of end goal, but we can also check common operating system bug would be, I bring a page in, I write to that page, so now it's dirty. And when that page gets evicted, I better write it back to memory before I mark it as invalid, right? That's like, we learned that in operating system class, that when you evict a dirty page, you have to write it back. One of the things that we can check is whether that occurs. And that's a mixture of both the data we're manipulating and also the metadata about the valid bits and the dirty bits. And all of that can be included in the constructs that we express. The designer needs to write these rules. And I'm not going to say that's always easy. So we're also looking at ways to help making the writing of the rules a little bit easier. Because one of the questions that you could be asking right now that you haven't asked is, how do we know that the rules we've written are correct? And so we have ways of doing that more efficiently and checking some of that as well.
Okay, the next couple of questions are related to quantum computing. So Ashish Panwar wants to ask that, is there a correlation between the number of qubits and the success rate in the quantum architectures? And if yes, then should we focus on improving the reliability before increasing the number of qubits?
That's a great question. And actually, some of my colleagues who are a little bit lower down in the quantum computing technology stack have these pretty amazing 3D graphs where they can show different ways that we could proceed in quantum, right? So we could proceed in quantum by just increasing qubit count without considering the noise level or the connectivity, or we could push hard on making small numbers of qubits higher fidelity, lowering the noise, or we could push hard on connectivity. And as an architect, I love spaces like that, right? Because we're all about trade-offs, right? We're all about deciding in this three-dimensional space, where should we navigate? One interesting sort of way forward on this is a lot of early quantum work focused a lot on qubit counts. And, you know, this machine has this many qubits and that machine has more qubits. And what we're seeing increasingly, IBM, for example, has advocated for a metric called quantum volume, which is about the capability of a machine, including both attributes of its qubit count and its fidelity. And you can think about this as their way to try to come up with a metric that is more about overall success and less just about qubit counts. And so then within a notion of quantum volume, yes, that does help you decide how much to emphasize improving reliability before emphasizing adding more qubits.
Yeah, thanks. Jen wishes to ask that the design complexity increases due to exposing low-level parameters. So do you see a blurring between physical and logical qubits in the future to reduce this complexity?
The first sentence of this question is great because, you know, architecture, as I started out with, architecture is really about drawing an abstraction layer and saying, you shouldn't need to see what's down there. When you write your classical program, when you write your machine learning kernel, you don't need to understand how a transistor works, right? And yet in quantum, we're asking people to kind of deal with and understand that whole stack. That's not a great place for us to be 20 years from now, but it's the place we kind of need to be right now, because if we don't understand enough of the stack right now, we won't get to usefulness in any sort of reasonable time frame. And so we're compromising on abstraction right now in order to improve the success of the overall stack. And one of my students, Teague Tomesh, led the writing of a paper that is in IEEE Micro now called Quantum Co-Design. It really takes on this issue of what benefits do you get by pushing information up and down the stack? And then when can we maybe hope for less complex information flowing up and down the stack? So right now, the quantum computers we have right now don't have logical qubits per se. There's essentially no error-corrected quantum computer out there. We're just getting into the beginnings of error correction working at all. And so we don't really have logical qubits yet. But once we do, that will be a great abstraction layer to say, ignore the physical qubits and only think about logical error-corrected qubits. When we get there, that'll be wonderful. We're not quite there yet. We might be getting close to a point where we can choose. Some parts of our algorithm, we might choose logical error-corrected qubits. In other parts of our algorithm, we might choose uncorrected qubits because they take less resources, right? An uncorrected qubit takes sort of 1/10 to 1/100th the resources of a corrected qubit. And so we need to know how to balance that too.
Thanks. Yeah, so we'll take a very quick last question. Rashri wishes to ask that how do you foresee the future of energy efficient heterogeneous systems and GPUs in particular? And is it being looked at in the quantum space as well?
So on the classical side, I think, you know, heterogeneity and parallelism have been our key levers on energy efficiency, because where we can build an accelerator to do something, there's huge energy benefits in building it as an accelerator rather than as sort of instructions that we sequence through with all the fetch, decode, execute kinds of overhead. So specialization has been key on the classical side, and we're sort of dealing with the complexity issues that specialization has brought about, but it's been a big win for energy efficiency. On the quantum side, we're kind of in a different place on energy efficiency. because on the quantum side, everything that I described is happening inside a cooling system that's bringing things down to almost absolute zero. And let's be honest, the energy of that cooling system is huge. So the issues of quantum and energy are first, how much compute can we do inside that cryogenic system without heating it up? And second of all, if we can take something that was intractable or that would take sort of days, months, years to run, and we can make it run in seconds, there's likely to be an energy savings there. But frankly, for now, quantum is mostly about taking intractable things and seeing if we can make them tractable, as opposed to thinking hard about sort of the ongoing energy costs of doing so. A nice question for the future.
Yeah, thanks. Thank you, Margaret. And I really appreciate a very interesting talk. You have taken us through the 1950s all the way to 2022. And I'm sure the audience and their students must have definitely been encouraged to work in architecture. Looking at it's at times we only imagine, is this possible? But you have shown by your work that yes, it is possible, and that has motivated the students very much. So thank you so much. And yeah.
Thank you.
Thank you, Margaret.
It was a wonderful chance to meet with you today, and I hope to see you in person sometime soon.
In the near future.
Take care.
Thank you, Professor. We surely have gained knowledge after listening to this talk.
Now there is this unique interview and we now have a 5 minutes break. Thank you.
In the meanwhile, I want to take this opportunity to welcome Professor Eho. Hello, Al.
Good morning, Helen.
Thank you.
Or good afternoon.
Yes, good morning to you.
Yes. It's actually closer to evening. So welcome, Professor Eho.
Yes.
I had sent you the initial earlier emails about requesting you to join us for this event, and we're really thankful to you for having been kind enough to do so.
So we have a few minutes, and I'm sure Sriram will join shortly. But the way we are planning, sir, is that, of course, I'll introduce you, both you and Sriram. And then we will play the recorded video. I think that's going to be for about 50 minutes. And then there will be a 10-15 minute live Q&A session, which Sriram will host. That's the plan. So I'll go on mute and call Sriram in the meanwhile. Okay.
So, Professor Eho, did you have a chance to visit India earlier? Yeah.
I just spoke to Sriram. He's joining in a minute. Professor Eho, I want to make sure that you can hear us.
I can hear you fine, and I can see you fine.
Excellent. And yes, we can hear you. We can see you as well. Let's see. I see something.
Professor Eho, I had asked you earlier, did you have a chance to visit India sometime in the past?
Yes. I don't remember the exact year, but it was about 8 or 10 years ago. I visited Sriram. I gave a talk at IIT Delhi, visited the IIS in Bangalore, and I discovered that Bangalore was a parking lot at that time. I couldn't believe the traffic.
It still is.
I don't know whether that's changed or not.
Now, thanks to the pandemic, most people are working from home. So the
Yes.
parking lot is inside the house.
Okay, I think we can get started. So if you can bring up the slide with introduction to Professor Eho, that would be nice.
Yes, sir, sure, sir.
Yes.
So now there's this.
Sriram, welcome. Sriram has joined as well.
Hello, Sriram.
Sriram, we can't hear you. You might be on mute.
Yes.
Yeah, is it better now?
Yes,
Yeah,
now we can hear you.
Yeah, okay.
Okay. Yeah, let's bring up the slide and then we'll get started.
Good evening, everybody. Now there's this unique interview and fireside chat session by the two of the most eminent speakers, Dr. Sriram Rajmani, who's the host of this interview, and Professor Alfred Aho, talking for us. I now humbly call upon Dr. Hemant to introduce and invite Professor Alfred Aho and Dr. Sriram Rajmani.
Thank you. So again, I'm Hemant Pandey. I'm Executive Director of ACM India. And I can spend so much time introducing Professor Eho, but it's probably not necessary. So I won't read out things from here because what you will get from the 50 minutes of conversation that Sriram and Professor Eho are going to have, it's probably more inspirational and informational, educational than anything that I say. But suffices to say that I don't think there is anyone who has studied compilers, let's say programming languages, and has not read the Dragon book or the design and analysis of computer algorithms book or used awk as a language. So his work has not just touched, but enriched millions of lives. So with that, I'm going to quickly introduce Sriram. So let's have that slide which introduces Sriram as well. But Sriram is Managing Director of Microsoft Research India. He is a ACM fellow, and he's been associated with ACM in a number of roles. And he's, again, as you just heard, that personally knows Al, and he's had the fortune of having had a visit. And I'm sure, Sriram, you have visited him in person multiple times, probably in Redmond and things like that. So without further ado, what I'm going to do is that, having done this introduction, if you don't mind, we will just say hi to you and go into that video where you had a wonderful chat with Professor Eho. And after that, I think we will have about 15 minutes, you decide, a few minutes of Q&A, live Q&A, which Sriram, you will just take over after the video, right?
Good.
Okay.
Yeah, I can happy to do that. Yeah.
Yes. So let's go into the video conversation, what we call the interview and the fireside chat. Yeah, it's coming up. There you go.
Hello, I'm extremely privileged to bring a conversation with Professor Al Eho to our viewers in India through ACM India. And Al is well known to everyone in the computing community. He's the co-winner of last year's Turing Award. Um, and the citation recognizes him for fundamental algorithms and theory underlying programming language implementation, and for synthesizing these results and those of others in their highly influential textbooks, which educated generations of computer scientists, including me. You know, I grew up studying compilers from the Dragon book, Theory of Computation, many such books. So welcome, Al. It's such a pleasure to have you chat with us.
It's so nice to see you, Sriram. It's been many years since we last met, but I'm delighted to be able to have this conversation with you.
Yeah, thank you, Al. I remember I met you a few times. First, when I was in Microsoft Research in Redmond, Tom Ball, my colleague, invited you to Redmond, and we had several wonderful conversations there in Microsoft Research in Redmond. And then I visited Columbia a few years after that, when you and other colleagues hosted me. And yeah, I mean, it's been a long time from my side as well to see you, and I'm delighted that we have the opportunity to catch up today.
Thank you.
Yeah. So tell us, maybe we'll warm up a little bit by, since I've met you a few times, when you told me a little bit about yourself, where you grew up, your childhood, and so on. But our viewers may not have had the same interaction with you. So tell us about, how it was growing up for you. Which high school did you go to? What was the world like then when you were growing up?
Okay, well, I was born in a small town in northern Ontario called Timmins. This is in Canada. And my parents moved to Toronto when I was 2 years old. The story I like to tell is that there was a fortnight where it never got above 20 degrees below zero Fahrenheit in Timmins. So that's why I persuaded my parents to move to Toronto, where it was a little bit warmer. I went to school in Toronto. I attended North Toronto Collegiate Institute for high school, and then after high school, I took engineering physics at the University of Toronto. This program was very mathematically and oriented, and it taught fundamentals, which I thought was a very good beginning for a scientific career. I also played squash. I captained the squash team for the engineering school, and it was nice to have some physical activity of that nature that wasn't too rough. After engineering physics at Toronto, I went to Princeton for my PhD. And the reason I chose Princeton was for my senior thesis at Toronto, I did a paper on minimization of Boolean circuits. And I discovered at that time there was a professor at Princeton University by the name of Ed McCluskey, who was very famous for his work on minimizing Boolean functions. And one of the things I developed in doing my senior thesis was how well you could model logic circuits with Boolean algebra. So I have found this combination of theory and practice to be very intriguing. And Don Knuth has this saying that the best theory is motivated by practice and the best practice by theory. So I've taken that to heart, and I like looking at problems and trying to develop a theoretical model on top of which you can then do problem solving. And there's a field called computational thinking that's become very popular in educational circles these days. And the two pillars of computational thinking are abstractions and algorithms. So in many ways, I'll talk about this a little later if you're interested, how important abstractions and algorithms have been in turning the field of compiler design from an art to a science. And this would be some of the advice I'd also like to give to new students and new faculty, saying that it's always good to look at fundamentals and really try to understand the essence of your field before you start doing research. And then
that'd be wonderful. That'd be wonderful.
And then after getting my PhD at Princeton under Ed McCluskey, because once Ed McCluskey discovered I was interested in minimizing Boolean functions, he started writing personal letters to me and saying, "Oh, you must come to Princeton and study with me to get your PhD." So it seemed like a no-brainer then to go to Princeton for my graduate work. And after Princeton, I joined the Computing Sciences Research Center at Bell Labs and spent 30 years at Bell Labs. And then after Bell Labs, I wanted to spend the last part of my career teaching and working with students. And so I went to Columbia as I initially joined the computer science department at Columbia as the department chair. And this is not necessarily an optimal way to enter academia.
I see. Yeah, indeed. And actually, Al, I would love to talk more about, compilers, abstractions, and so on. But I also want to get our viewers a sense for how computing was when you grew up. What kinds of computers did you play with? What kind of, what did you do? What was your first exposure to computers as a high school student and as a university student?
Well, I entered computer science before there were computer science departments at almost any university in the world. So it's nice to go into a field that's just starting. At the University of Toronto, they had an IBM 7090 computer, and I had to write a program in assembly language on the 7090. I really did not like assembly language programming. When I went to Princeton, the first programming language that I learned, higher level programming language, was IPL5. And the next programming language I learned was Snowball 4. These were somewhat eclectic languages. I had a summer job as I was going to university at Bell Northern Research in Canada. And there I was given the task of working with a professor who had just joined Bell Labs from Waterloo University and a hardware engineer who knew about number 5 crossbar switches and telephony. And we were given the job of design a digital switch. Now, the only background I had at that time was a course in formal language theory, but I had been given the task of designing the order structure of the computer that was to execute the programs in the switch, so I could design my own assembly language. And I thought that was great fun. And then I wrote a Fortran program, which I had to learn for the process of simulating a call through that digital switch. So I learned Fortran this way. So I had a very untraditional introduction to computer science, if you like. And even at Princeton at that time, computer science was an option in the electrical engineering department. So my graduate education at Princeton really consisted of taking 6 courses from the Princeton math department. And I thought that was terrific. Although at the time I was taking the courses, mathematicians think very differently than engineers.
Was this continuous mathematics or discrete mathematics or both?
Oh, well, the courses I had were a course on probability theory from Feller, a course on game theory for Morgenstern, a course on recursive function theory, a course on algebra. So these were graduate level courses being taught to Princeton math students. And at that time, Princeton had, and still does, one of the top math research programs in the world. So meeting the students and the professors was a interesting experience, but they were brilliant. And I discovered later, much later, that what I learned in those courses was very valuable for my computer science career. And I have a saying at this point that you never can learn too much mathematics, because mathematics is just so useful.
Yeah, I completely agree. I know, Al, when I read the books of you and your colleagues, right? I must confess that those books were the ones that attracted me to computing, and the elegance and precision in those books, was artistically appealing as much as scientifically appealing as well, I must say.
Yes, I fully agree with your reactions, because when I was doing my senior thesis, what I discovered was, Boolean algebra is a pretty good model for logic circuits. And what I also discovered was I was trying to minimize the logic circuits using algorithms. And this is why I was interested in what Ed McCluskey was doing, because he was interested in algorithms for minimizing Boolean functions. The Quine-McCluskey method was, or it was a heuristic at that time, was the very popular as a technique for trying to minimize Boolean functions. What I was frustrated by was how difficult it was to minimize or find the truly optimum Boolean circuit. And it's only later in life I discovered that, there are some problems, computing problems, that are very difficult.
Oh, so NP completeness, what hadn't been discovered by then, I guess.
It had not been. This was in 1963 that I did my senior thesis. So Steve Cook wrote his fundamental paper on NP completeness in 1971. And you had asked me at one time, how do you react to failure?
Yes.
So when NP completeness came on the scene, I thought that's an interesting problem, because you could look at NP, the P versus NP problem, as if you can verify a solution for a problem quickly, can you find the solution quickly? That's another way of formulating is P equal to NP. And I took some NP complete problems, like trying to find a Hamiltonian circuit in a graph, and say, this can't be that hard to do. But I couldn't think of a better method than trying all possible circuits to see if you could find a Hamiltonian circuit amongst them. And I think even to this day, nobody knows what the true complexity of NP complete problems are. Either there are a few people who think that P is equal to NP, most people think P is not equal to NP, and actually if you could solve this problem, you could win $1 million prize from the Clay Mathematics Institute. So it's considered to be now one of the most important open questions in computer science. It ranks up there along with the Riemann hypothesis.
Yeah, indeed, Al. Let's take the conversation back to compilers now, right? You are, that's one of the things that you are very well known for. Your work on compilers and also the Dragon book. You mentioned a little bit that you programmed in a few programming languages like Snowball and then Fortran and so on. How was programming experience when you did these things? Were the compilers there? What were they doing? What was lacking? And how did this whole field with abstractions and other, just tell us the story of how compilers evolved.
Oh, so compilers are very interesting devices. They're language translators. They translate a source program written by a programmer into another program which is supposed to be semantically equivalent. And compiler writers face a very onerous task. They have to make sure that their compiler, the language translator that they're writing, preserves the meaning of programs. And even to this day, trying to understand what the meaning of a program is very difficult. So there's a fascination that I find to writing programs. And I like to think of algorithms as recipes for doing some task. In computer science, there's a definition of an algorithm that it's a Turing machine that halts on all inputs. And I don't know whether you've noticed that there are some computer scientists who say that an algorithm doesn't have to halt on all inputs. And I think the distinction is similar to that in recursive function theory. If we look at the total recursive functions, they're like Turing machines that halt on all inputs. If we look at partial recursive functions, they're like Turing machines that don't have to halt on all inputs. And when I was writing the Design and Analysis of Computer Algorithms book with John Hopcroft and Jeff Ullman, we consulted with Don Knuth, who some years later, the New York Times characterized as the Yoda of Silicon Valley. And he said an algorithm must halt on all inputs. So what we called a Turing machine that didn't have to halt on all inputs, a procedure. So the algorithm procedure distinction is like the distinction between total recursive functions and partial recursive functions in recursive function theory. And I think that's a useful distinction to make because the total recursive functions have different properties than the class of partial recursive functions. But this again shows the background that I got by taking math courses as part of my graduate education. In practice, you normally want to write computer programs that halt, that don't go into infinite loops or don't spend too long finding an answer. And it took Alan Turing to show that there's no algorithm to determine whether a computer program is ever going to halt. So one of the intriguing things about computer science is that all of a sudden you're confronted with problems that may or may not have algorithmic solutions. And what's even more frustrating is that you can't tell beforehand whether a problem is decidable or not. So that's why I think the field of programming is intellectually interesting, challenging, and the interest in programming languages is how do you try to capture computations in a way that you can communicate them to other programmers and to a computer easily and simply. So this is the essence of good programming language design. If we look at the world of programming languages today, we see that there are hundreds, maybe even thousands of programming languages, and maybe there are 200 or 300 that are widely used or more commonly used. But it seems that like natural languages, people like diversity. And at one time, I tried to determine whether there were more natural languages in the world than programming languages in the world.
And my
And
guess is that's the case, right? I'm guessing there's more natural languages than programming languages. I'd be surprised if that's
well,
wrong.
Ethnologue catalogs all extant natural languages. And I think there are about 7,000 or so spoken natural languages that are extant in the world today. And I once saw a website at a university that had pointers to 7,000 different programming languages.
That's very equal. That's amazing.
So they're equal, but you know, now it's so easy to create a new programming language and write a compiler for it. I think it's not possible to count all of the programming languages that are out there. But what's also interesting is I try to look at what are the most popular programming languages in the world today. And I track what are the 10 most popular programming languages as time progresses. And what's interesting is that the programming languages that were invented a long time ago are still popular. C is one of the most popular programming languages in the world, and it was invented many decades ago. It's also gone through many different revisions. COBOL programs run the financial world, and I think there are lots of banks, institutions, universities that still use COBOL programs to keep track of students and
They wrap
grades.
it in. They wrap it inside a web service, but inside that it runs COBOL.
Yes. So
Essentially, it's all wrapped using WSDL or something like that. A message goes through the modern HTTP system, but inside it runs still COBOL. You're absolutely right.
yeah, and it's also interesting to look at new programming languages that are becoming popular. Python is becoming a very popular programming language. JavaScript is one of the most used programming languages today. So if you are in computer science or in the computing field, you have to keep up with the times. And that may involve having to learn new languages all the time. Fortunately, we don't have to learn as many natural languages as we do learning programming languages.
So Al, can I interject and ask? I know when I've of course read about awk. That's actually a language that you designed. I'm sure you designed many other languages as well. Tell us about the story behind awk.
Well, this is a very interesting story. I mentioned that after I graduated from Princeton University, I joined the Computing Sciences Research Center at Bell Labs. And I had Brian Kernahan as a colleague in the office next to mine, and Peter Weinberger was very close by as well. And I had been talking with Brian about generalizing the grep program on Unix to do have more interesting patterns and more interesting functionality rather than just printing the line on which it found a regular expression pattern. So Brian and I had developed a specification for a super grep where we could have patterns that had string expressions and arithmetic expressions, and attached to each expression or each pattern, you could attach a program in a C-like programming language, so you could have a lot of flexibility in what kind of output you generate. But the style of programming was still like that of pattern action programming. And pattern action programming is a very natural way of responding to events. If you hear a loud noise, you turn your head in the direction of the loud noise, and so on. So humans are stimulus response creatures. So we, or at least I had this in the back of my mind as a good, simple programming model for doing routine data processing. Brian was also interested in routine data processing, and so was Peter Weinberger. So we created this plan for a routine data processing program, and our thought was that people would be much more willing to write 2 or 3 line awk programs to do the routine data processing tasks that they had in their life, rather than writing a 100 or 200 line C program to do the same thing. And when we unleashed awk in the Unix room, it became instantly popular, one of the most widely used commands on the Unix system. And when it escaped out of the Unix room, and it became one of the most popular applications on Unix in the world for many years, because it was so easy to learn. And you could do useful tasks like keeping track of budgets, keeping track of student grades, routine data processing problems. And there's an awful lot of that in the world.
So I remember, already, even during my graduate school, I had to do a lot of experiments, and for my thesis, get numbers and report them into tables and so on. And I used to write awk scripts for all of them, because the programs used to output numbers and then to format them into tables and so on. Awk was convenient, even one of the most convenient things, even today, I think.
Yes, and also the other aspect that I like about awk is that it's very easy to teach and very easy to learn. You can write a useful awk program and learn how to write a useful awk program in 10 or 15 minutes. And
how did you implement awk? Was it implemented in C? Did you worry about performance? How was it? Now we talked a little bit about the design, right? Tell me a little bit about the implementation of awk as well, and how easy or how difficult it was.
I was very interested in fast regular expression pattern matching programs. I wrote a program to generalize Ken Thompson's grep program initially. Ken Thompson used a simulation of a non-deterministic finite automaton to look for regular expression patterns in input strings. And it was very good for small regular expressions because it ran very fast. But there were some people who had very large regular expressions. My boss at Bell Labs had written a program that would allow different ways of specifying dates and times. And there is enormous diversity in how you can specify a date going across the world and even in times. So he had regular expressions that were very large and many of them. And the first generalized program that I wrote for all regular expressions involved constructing a deterministic finite automaton from the regular expression and then running that deterministic finite automaton. It takes a long time to construct a deterministic finite automaton from a regular expression. It can take time that's exponential in the size of the regular expression. But once you've got the deterministic finite automaton, you can run it very quickly. So the first version of egrep that I wrote, egrep was a generalized extended grep program. You had to wait a while for it to compile the large regular expression specification into a deterministic finite automaton, but then it ran blazingly fast. So it was like if you wanted to across the road, you had to build a Boeing 747, but you spent a lot of time constructing the airplane, but very little time flying it. So what I did was I put in a dynamic, lazy construction of the states of the finite automaton into the second version of eGrep. And then it ran blindingly fast in practice on all inputs. So my boss's date and calendar program all of a sudden ran almost instantly. And he became very impressed with algorithms as a consequence. And I took these fast regular expression pattern matching programs or algorithms that I developed and put them into the AWK. So AWK did a very fast job of doing regular expression pattern matching, and it was much more efficient than some string processing programs that were available at that time. So that, I think, also is a testimonial to saying good algorithms can make or break a program. And good algorithms sometimes require deeper insights than you initially have in thinking about a problem. And there's no better way to get some of these insights other than by having people trying to use your ideas. So we found the feedback that we got from our colleagues as they started to use the first versions of AWK very popular. And I think that also accounts for the popularity of Unix, that Unix was written and rewritten several times in the beginning. Ken Thompson didn't mind throwing away a program that he had written only to replace it by something that he thought was much better and much faster. So this honing of software, I think, is a very nice way of developing software, because you can't think of the best way of doing a problem and seeing all of the cases that you have to consider right at the start. But as you start getting some experience with the class of problems that people are attacking with your software, you get much better insight into how you should have designed it and could have designed it. So again, it's a feedback process that's been, I think, very beneficial in the development of software systems.
Absolutely.
But it does,
yeah.
But it also creates a problem that how do you maintain legacy software systems? You know, we talked about COBOL. We don't teach COBOL to beginning computer science students anymore, but we have, I think I read somewhere that there is something like 2 billion lines of existing COBOL code that need to be maintained. How are those going to be maintained? Or are we going to rewrite them completely in another language? But that becomes prohibitively expensive. So we still have a lot of fascinating problems to solve in computer science.
Absolutely, Al. And one thing I think it struck me as you were describing how, AWK and Unix, it was really developed by trying it out, writing a version, deploying it to users, seeing how it works, and even that even give you insights on which parts to optimize. Whether to optimize ahead of time, like an airplane, and then running it, and so on. So, and I'm very fascinated that a person like you, who has done both theory and practice, is able to lucidly communicate how theory and practice interplay with each other. Can I ask a question along those lines about the world today? I mean, right now, machine learning is very, very popular, and there are many, many applications. We don't understand foundations of it as much. Do you sort of see, during your time, right, when you were studying compilers, algorithms, and so on in the early days of your career, right, those were things that people wanted to use and they didn't completely understand. Do you see a parallel today with how learning and how computing is evolving? And can you venture a guess or give advice to young people on how to navigate the current situation in computing?
That is a very interesting, a very important question. And I think we don't understand how the programs generated by machine learning actually work. I sometimes think of it, how does our brain work? What algorithms does our brain use to come up with ideas, thinking, consciousness? So we could view the brain as one huge neural net, literally a neural net, but we really don't understand what kind of algorithms it uses to process inputs. We see something, how does the brain translate what we see into an image? We hear something, how does it translate the sound waves into speech or whatever, music or whatever we're listening to? And why, if we're listening to music, why does the music stir our soul? What kind of algorithm is there in our body that causes this emotional reaction to music? So maybe that's too tough a problem right now, but my understanding is that you can easily spoof some of these programs generated by machine learning, that if you make, say, an elephant walk across the room, all of a sudden the machine learning program will misclassify the objects it's recognized in the room. So this is a very good and very important research area at the current time of how do we make machine learning more robust and more safe to use in mission critical applications. Will you really trust a pacemaker whose program has been created by machine learning to keep you alive? And we're already seeing that, there's some disastrous aspects of bad software that have been produced even without machine learning. But if we're talking about autonomous vehicles guided by programs that have been produced by machine learning, we may be producing things that aren't as robust as we would like them to be.
Okay, so switching gears, Al, I wanted to talk a little bit about your own career, spending time about close to 30 years in Bell Labs, and then you moved to academia, and you've been a professor for many years, including department chair that you mentioned. So for young people that are listening to this interview, researchers, they might be thinking about, oh, should I go to academia? Should I go to a lab? How should I run my career? What advice do you want to give people about what are the things you enjoyed being in a lab, industrial lab? What things you enjoyed being a faculty member, and what are sort of the attributes of each of those setups?
Well, it's an interesting question for a new person to decide what should he or she accept as his or her first job. And I really didn't know what I wanted to do with my life, so I had a plan. I'll stay in school as long as possible to defer the decision of what I have to do when I grow up. So that's why the idea of getting a PhD was appealing. I could defer the decision. And then after getting the PhD, I really liked doing research. So having the opportunity to join Bell Labs research was wonderful. And at that time, I was creating a life plan for myself. My plan was I'd like to spend the first half of my life working in industry, doing research, and the last half of my career teaching and working with students. And I was very fortunate to be able to accomplish this with my life. So I spent 30 years working at Bell Labs Research. And then after Bell Labs, I went and joined Columbia University. And as I mentioned, I joined the Department of Computer Science as a department chair. And then after that, I was just a professor and I could work with students and teach, which I really enjoyed. So I've been very fortunate to have a career with very good colleagues and very stimulating work. And the other aspect of it was it's much nicer to enter a new field than an existing field, because let's say you want to do research in number theory. You have to spend several years getting to the frontiers of research in number theory before you can start doing significant work. And then if you start doing significant work, maybe there will be 2 or 3 people in the world who will understand the theorem you've just proven because it's so specialized. On the other hand, when you're in a new field, there are a lot of easy results to be had just by plucking the low-hanging fruit, and people can appreciate the fundamental results that undergird a field. So I was very fortunate to enter computer science and the area of programming languages and compilers as they were developing, because there was a lot of fundamental work to be done, new results to be obtained that were broadly applicable. And I also found when I was doing research that teaching and writing and doing research were very synergistic. So that sort of explains why I was interested in writing books as a way of codifying what was known about the field.
Did you teach, Al? Even when you were at Bell Labs, did you give lectures and interact with students even while you were at Bell Labs?
Yes, I was a adjunct professor at Stevens Institute of Technology, and I helped set up the computer science research doctoral program there. So I was teaching graduate courses at Stevens to students, and many of the students were actually students who were working at Bell Labs getting a master's degree. So they were very good students. And I have often said that there's no better way to learn a subject than to teach it.
Yes, yes.
Because
absolutely.
you have to answer all these questions from students. And if the students are good, they really challenge you in a variety of dimensions. And they also help in the exposition that as you're trying to explain the ideas, you understand what ways are there to explain the ideas that make it much easier to learn. So I think one of the intriguing aspects of understanding how the human brain works is maybe we can understand how to teach better if we understand what the algorithms the brain uses to learn. And I think this is individualistic, that you and I may learn things in very different ways in different areas. So there isn't one uniform style of learning that applies to all people.
Yeah. So Al, after you moved to Colombia, have you continued interaction with the industry? I mean, I want to ask the flip question, like when you were at Bell Labs, you were teaching at Stevens
Yes.
Institute of Technology and so on. And how was your experience sitting in academia and interacting with the industry? Tell me a little bit about that.
I think, particularly if you're in academia, you need to keep up to date of what's going on in the real world, what's going on in practice. And there's no better way to keep up with what's going on in practice than to go and talk and work with practitioners. So even when I was at Columbia, I would like to go and spend some sabbaticals working with people in industry. And as you mentioned, we met at Microsoft Research, and I learned a lot from that experience working with Tom Ball and his colleagues at Microsoft Research about what was going on in that part of the world. And I've been a consultant for Bell Labs Research for many years. And so I keep in touch with some of my former colleagues in Bell Labs Research as a way of understanding what's going on in that part of the world. And one of the things that is happening is it's very difficult to remain abreast even of a single area these days because there is so much going on and everything is changing so rapidly. So part of my philosophy of learn a lot of mathematics, but also learn the basics of a field because the basics don't change as quickly as the details of the technology of the nonce. So if you understand the basics, then you might be able to relate some of the newer developments in terms of the basics. But if you just understand the details of COBOL, you're going to have a very difficult time understanding some of the newer areas of like what works and doesn't work with machine learning.
Absolutely, and this is I think a very timely advice to give to students who might be feel intimidated, saying so much is going on. I think the number one thing that they should realize is that maybe so much is going on, but they had to get into foundations and simplicity behind those and learn the mathematics behind them. That will probably hold them good for many many years in their career.
Yes, and the other thing I'd like to mention, and I mention to my students, is you're deciding on what your first job should be. My advice is choose as your first job a job where you can, if you can, work with the best people in the field because you learn so much by working with other people.
Yes.
And once you do that, you'll put yourself in a much better position for your second job because you will have kept up with the field.
Absolutely, right? I mean, colleagues research is not a solitary experience, right? It's social, engaging with others, and colleagues are everything. They determine the quality of what you do and the quality of your experience and what you learn. Absolutely.
Yes. So,
Yeah.
The other part of it is keep talking to the people who are doing the interesting research, interesting developments, because I find talking with individuals is a much better way of keeping up with things rather than just reading their research papers. It's what's between the lines in the research papers that's very interesting. And I might mention that the last field that I had PhD students in at Columbia was in quantum computing. And
Including Krista, whom you sent our way into Microsoft.
yes, she was a wonderful student. And she really got me into quantum computing because she took my programming languages and compilers course. And in it, there's a project that the students perform in teams, and her team developed a little programming language for learning about quantum computing. And she wrote a compiler for this. And after she did this project, she said, would I become her PhD thesis advisor? And I said, absolutely. And so I said, there was a condition. I can teach you about compilers, but you're going to have to teach me about quantum mechanics.
Yeah, this
And
is
I'm
wonderful.
still learning quantum mechanics because it's one of the most intriguing areas I've ever encountered. But there's a lot of hype associated with quantum computing today. But if you understand the basics, you can understand what's hype and what's reality. So if you read accounts by newspaper journalists, the journalists aren't technologists or physicists or computer scientists. So they attempt to sometimes make sweeping assertions where you understand even doing a little bit of that sweeping assertion is not physically feasible at this point with either the technology or with the science.
Yeah. So this is, such wonderful advice, Al. We are running out of time, so we have to close this interview. I really want to thank you on behalf of ACM India for taking this time to talk to all of us. I personally just found just talking with you so inspiring, and I am really glad we are able to have you talk to all our young researchers in India. Thank you so much for this, and good luck with your health and wellness, as the world goes through and recovers from this pandemic.
Well, thank you very much, Sriram. And it was just a delight interacting with you again. And I hope there's some time in the future where we can meet personally and have a cup of coffee or tea or whatever and get caught up. Thank you again.
Absolutely. Thank you again. Bye-bye. So I can read a couple of questions. Al, can you hear me? You can? Okay. So I think we have to unmute yourself.
Yes.
Yeah. So there's a question from Vishnu Ashutosh Dasu, who thanks you for the talk. It says that it's such inspiration for young researchers like him. And he asks, do you still write code today, Al? What's your opinion on modern programming languages like Python?
I usually have to write a program or two each day just to keep my sanity. It's great therapy. Most of my programs that I write today are of the routine data processing kind, so I, not surprisingly, tend to write those in awk. But when I give lectures, I usually try to illustrate algorithms and using a programming language that most of the audience would know. So recently, my programs have been written in Python. And I think I mentioned that it's difficult to keep up with even one area of computer science. I might add that it's also very difficult to keep up with just one programming language because programming languages evolve. And I discovered somewhat rudely that a Python 2 program doesn't compile with the Python 3 compiler anymore. So it's always wise to run your programs before you give a talk that has any real programs in it. Advice for speakers.
Thank you. So the next question is from PJ Narayanan, from AAA Hyderabad. He asks, he says that he knows that you teach a course at Columbia in a very interesting manner, apparently you get students together in small teams to even design a language and a compiler. Maybe you can say how you run that course.
Yes. The course that I enjoyed teaching the most was the programming languages and compilers course. And I thought it would be very beneficial for students to get experience designing their own programming language and writing a compiler for it or a translator of some kind for it. I mentioned this at the beginning of the class that I would like the students to form teams of 5, and each team has to first create and describe a programming language that they would like to write a compiler for. And the programming language has to be designed by the team as a whole. The students look at me when I mention this, saying, this professor is out of his gourd. He not only expects us to design a programming language, but also write a compiler for it. How can this be done? And this is where I think the abstractions and algorithms that we've developed for compiler design have come into play, because this kind of project would not have been possible in the early days of computer science. But because of the abstractions, the algorithms, and the tools that have resulted, tools like lexical analyzer generators and syntax analyzer generators, and also other tools that are involved in creating components of a compiler, they can greatly facilitate how quickly you can create a compiler. What is also interesting about this project is that the students loved the course because they had a chance to exercise their own creativity. I found when I first started teaching compilers courses, I gave them a little language to write a compiler for, and they thought this was the dullest thing imaginable, writing a compiler for a language given to them by their professor. But when I changed this to you create your own language and write a compiler for it, all of a sudden it became their baby and they really became interested in the project. The only bad aspect of it was that some other professors would accuse me of usurping too much time of the students for my course because they enjoyed doing it so much. The other philosophy I had was that by having students work together, they would learn 3 important life skills that would be useful no matter what they did with their careers and their lives. And the 3 skills were project management, teamwork, and communication, both oral and written. So you might ask, why did I choose 5 people for the team? Well, my philosophy was, I thought that you could create a compiler with about 2,000 or 3,000 lines of original code. And I asked, how many students does it take to create 3,000 lines of new source code in 15 weeks? So I applied Barry Beam's COCOA model to this, and it came out with the answer of 4.2. 4.2 people to create 3,000 lines of source code in 15 weeks. This was done a long time ago. And I said, great, I can round that up to 5. And then I could give each person on the team responsibility for one major responsibility for one aspect of the project. So each team had to elect a project manager, and the project manager's responsibility was timely delivery of the deliverables associated with the project. There had to be a language guru, a person who would maintain the intellectual integrity of the language as it was being developed. Because if you have 5 people working on a project, they need to have the same definition, the same specification of the language as the project unfolds. And you rarely get the specification right at the start. So one of the responsibilities of the language guru was to set up a system by which the specification could be updated and delivered to the students on an ongoing basis, so they all had a consistent definition of the language that they were supposed to be implementing. Another person that played a key role was a person who had to define the environment in which the compiler was to be written and what tools could be used or should be used in creating the compiler. And then his responsibility was to teach the other members of the team how to use these tools. Then perhaps the most interesting or important person on the team was the V&V person, validation and verification person. This person had to create a test for every syntactic feature of the program and had to create a test suite which could be invoked by one click. So it was one click, test and build as the compiler was being built. What I also did was I used the model of Appendix A of Kernahan and Ritchie's The C Programming Language book for how a language should be described. So at the very beginning of the course, I said to the students, you have 2 weeks to decide whether you're going to take this course because you're going to serve on a team. And so you have some moral obligation to complete the course because your contributions to the team effort will be essential for the completion of this project. Then after another 2 weeks, I had the students write a white paper patterned after the Java white paper, which was really a value proposition for the language that they were creating. The purpose of this white paper was to get some bonding on the team because the people who are on the team, many of them have never met before. So they had to learn how to work with one another, and what better way to work than to have them contribute their thoughts as to what they thought their dream programming language should be. And then after they wrote the white paper, I would grade the white paper just to make sure that what they're proposing made sense for the course. And then 4 weeks after that, they were to write a grammar and semantic specification for their language, patterned after this Appendix A of Kernahan and Ritchie. And also they had to write a user manual, a teaching manual for this language. So why create a language that you can't teach others to use? And that was also a very educational part of the language design process, because teachability became one of the driving forces in the language design. And then I also asked the students to say, why don't you say what you guarantee, what features of the language you guarantee to implement, and if you have enough time, what additional features you will include as time permits. I discovered the students never implemented any of the additional features because they didn't realize how hard it was just to get the core of their language done. But the students in the course of designing the language learned teamwork, how to work with other people. And they also had to do a lot of talking and writing about their language amongst themselves and to the class. So they learned communication skills, both written and oral. And then at the end of the course, each team had to give a 30-minute presentation to the class of their language. And I must say that the programming languages that the students designed and implemented often far exceeded my expectations. One of the most interesting languages that was created was a language to sonify data, to put sounds to streaming input data. And the team that created this language, they illustrated their language by writing a program that would put music to the ticker tape of the New York Stock Exchange. And when the stock market was going up, the music was bouncy and lively. And when the market was going down, the music was sad and gloomy. And one of the people on the team was a somewhat older student. He had been a venture capitalist right after he graduated from college, and he had been a stockbroker. So he said the last thing a stockbroker wants to do is look at the ticker tape all day. He'd much rather be doing some work and listening to music and having the music determine which way the market was going, rather than having to stare at the ticker tape. So the class was blown away by this demonstration. And that student, Adrian Weller, is now a principal researcher at Oxford University. So that's the other thing I enjoyed about the course, is that I got to meet and learn what students were doing. And many of the students who were taking this course had often had summer jobs at places like Microsoft or Google. So they would describe to me some of the tools and software design practices that were being used by these companies. So it allowed me to keep track of what worked in practice, and also get some insight into what some of the newer problems with the newer technologies were. So all in all, this was a wonderful course for me, and I think the students enjoyed it because they Columbia gave me 2 great teacher awards for teaching this course during the years I was at Columbia. And by the way, I wrote a paper on the how I taught this course for the ACM SIG on computer science education. It describes the process in detail that I used. It took me 30 years of working at Bell Labs to come up with the right weight software engineering process that would make it possible for the students to create and finish producing a working compiler in 15 weeks. And I might say that I've taught this course for 25 years at Columbia, and of the hundreds of teams that I had, never did a team fail to deliver a working compiler by the end of the project. And there's no magic to this, because one of the responsibilities of the project manager was timely delivery of all the artifacts associated with it. And they got graded for how well they performed these tasks as part of the team grade. So the project manager made this always happen.
This is wonderful. And I mean, I guess actually you're experienced in the industry, managing teams, getting things done, writing books is so wonderful. I mean, there's more questions, right? But we are out of time. So what I request is actually the people, I think there's more questions. Maybe you can just email Al. Al usually responds, at least when I write email, he responds usually. So, and then maybe he can respond to your questions via email. So with that, I'll thank you again, Al. It's so delightful to hear from you again. And I'll give it back to Hemant.
And thank you, Sriram. As usual, it's great interacting with you.
Thank you very much, Professor Eho. I speak for everybody when I say that we really appreciate you taking the time to talk to us live and taking the time to record the conversation, and also special thanks to Sriram for agreeing to interview. I must say we learned so much. It's a wealth of information that we gathered. Thank you very much. And I think with this, we will take a few minutes break before we go into the next session, which is again another highly anticipated one, which is the award ceremony. Thank you, everybody.
Thank you. Bye-bye.
And thank you, everyone.
Thank you, Al. Okay.
Thank you,
Control
Professor.
back to the organizers.
Yeah. Thank you, professors. It's a very exciting and informative discussion. Thank you. And now we have a short break, and we'll be joined back after 5 minutes. And it's as Sir said, no, it's going to be a wonderful session, the award ceremony. Thank you, sir. Thank you.
Thank you.
And Hemant, Vicky has just joined us. So let's welcome her to our annual event. Thanks very much, Vicky, for being with us today.
Hi, happy to be here.
Okay.
Good to see you. Hi.
Again, we had hoped to have you
Good
in
evening
person.
to all of you.
Right.
That's right. Yeah, we hope to have you in person soon, if not next week.
We shall see. Yeah, things are getting better here. So
here too. Yes.
Yeah, good. Yeah, you said you're coming out of it. Yeah, right.
We're just hoping there isn't a fourth wave or a fifth wave, that it ends at 3, right?
Yeah, that's the concern, right?
Right, yeah.
So Hemangi, shall we come back in a few minutes? I'll turn my video off for some time.
Sure. Should I just put that slide for award, or the organizers are doing that? And just so that people know what's next.
That's correct. Yeah. So. Yeah,
yeah, you don't want the awardees to get worried that the ceremony is not there, right? Yeah.
Right. It's 7:30, by the way, but no problem. The display says 7:45.
Right. And a couple of minutes.
7:30 to 8:45 p.m.
Yeah.
Yeah, we have some buffer built in already, so that we can take care of that. Okay.
Wonderful response time. It's been corrected.
So Hemant, should we begin? It's at 7:30.
Absolutely.
Ma'am, shall we start?
Yeah. So should I directly share screen, or you have something to say?
We'll start formally, ma'am.
Okay, please.
So good evening, one and all again. It's now the time to announce and to embrace the award winners of the ACM India. So now we have the ACM India Award ceremony, and I request Professor Hemangi Kapoor to host this event. Over to you, ma'am.
Yeah, thank you, local organizers. I will share my screen and we'll begin the proceedings. Yeah, is the slide visible?
Yes, ma'am.
Yeah.
Yeah, so good evening and welcome to yet another virtual, thanks to COVID, gathering of our awards. Normally, we were looking forward this year at least to visit Coimbatore. So welcome to the ACM India Annual Event 2022 Award Ceremony. We have definitely no words of appreciation and really thank PSG College of Engineering Coimbatore for once again virtually hosting us and diligently managing the backend. How much all of us wish to visit Coimbatore, so let's hope that we can visit you in future. To begin this event, let me first welcome our guests who are located in various parts of the country as well as in the world because of the different time zones. A warm welcome to Gabrielle Kotsis, ACM President. She is a computer science professor at Johannes Kepler University, Austria. She is a distinguished member of the ACM and currently elected president of the ACM. Welcome, Gabrielle. Welcome to Vicky Hansen, Executive Director and CEO of the ACM. She is a Fellow of the ACM, Fellow of Royal Society of Edinburgh, Fellow of the British Computer Society. She is known for her research in human-computer interaction and accessibility. A warm welcome to all our council members, sponsors, winners, and participants. Let us begin the evening with a song presented by our student. The song is Maitrim Bhajata. It is a benediction composed in Sanskrit by Jagadguru Sri Chandrasekharendra Saraswati, renowned as the Paramacharya of Kanchi. The song was set in Rag Malika by composer Sri Vasant Desai. The song advises one and all to cultivate friendship and humanity, look upon others as similar to ourselves, renounce war and forsake competition. It tells us that Mother Earth yields all that we require. Please enjoy the song.
Maitrim Bhajada Akhila Hrijetri Maitrim Bhajada Akhila Hrijetri Atmavadeva Paranapi Pashyata Atmavadeva Paranapi Pashyata Yuddham Tyajata Spardham Tyajata Yuddham Tyajata Spardham Tyajata Tyajata Pareshu Kramamakramanam Tyajata Pareshva Kramamakramanam Maitrim Bhajada Akhila Hrijetri Maitrim Bhajada Akhila Hrijetri.
Thank you, Ashwati, for a very nice song. You really set the stage for the evening. Thank you so much. Okay. So continuing with the award ceremony. We begin this evening by congratulating our member elevations. I would request ACM CEO Vicky to talk about the ACM Fellow and the ACM Distinguished Member Program and congratulate the elevations from India. Requesting Vicky to please discuss.
Okay, hello. There, okay, I'm on, good. Thank you very much for inviting me. I'm very pleased to be here to congratulate the ACM members from India who've achieved the distinction of ACM Fellow or Distinguished Member for 2021. These honors recognize outstanding accomplishments in computing, as well as outstanding service to the larger computing community. All who are elected for these honors are people who we look to serve as mentors and role models and to help guide others in their careers. It's important to realize that both fellows and distinguished members are ACM member grades, which means that ACM membership is required in order to attain this status. For both, a person has to have been a professional member of ACM for at least 5 of the last 10 years. But membership alone just isn't enough to receive one of these honors. Distinguished members represent the top 10% of ACM's global membership, as demonstrated by their leadership in engineering, research, education, or management. ACM's most prestigious member grade is Fellows, which recognizes only the top 1% of ACM members. Fellows are selected for having achieved lasting impact on their field and for their technical and leadership contributions. So I want to congratulate those who you can see on the slide here were selected as fellows or distinguished members for this year. I'm thrilled to recognize you for your outstanding contributions, and I look forward to seeing a lot more ACM fellows and distinguished members from ACM next year. So congratulations to all of you.
Thank you, Vicky. Yes, so congratulations from our side as well to ACM fellows, Professor M. Balakrishnan, Sunita Saravagi. Then we have in the distinguished members list, Ranjita Bhagwan, R. Govind Ranjan, Yogesh Simhan. Then we have Ujjwal Maulik, Supratik Chakravarti, P. Kumaraguru, and B. Ravindran. Congratulations to all of you. Definitely these elevations are worth noting, and we had a committee of fellows who have efficiently mentored and shepherded all the nominations throughout the year. So it has helped to get a quantum leap in a successful set of nominations from India. So we thank the ACM India Committee of Fellows, which consists of Ganesh Ramalingam, Hemant, Jayant, Madhav, Manish Gupta, Venkat Rangan, Rajiv Alur, Rajiv Rastogi, Sandhya Dwarkadash, Sriram Rajamani, Venkat Padmanabhan. And thank you, Vicky, for being an advisor to this committee. We are grateful to this committee and we look forward to your continued support in the coming years. Thank you so much. We will quickly take a group photograph of all the elevated members, the distinguished members, the fellows with Vicky and ACM President and related dignitaries. So I would request these people to turn on their cameras and help the organizers take a group photograph. Should I stop screen sharing?
Yeah, maybe just for the photograph. Yeah.
Yeah, we could request only you, Vicky, and the award winners to turn on their videos and others to turn them off so that we can get everybody in one frame. Great. Okay, thank you very much. Got a picture.
Okay. So starting with the various ACM Media Awards. So from last year, we have constituted several awards at the ACM India level. Some of them are, all of them are listed here. The first is the Early Career Researcher Award, given to individuals in their early careers within 12 years of their contributions. Then Outstanding Contributions to Women in Computing Award, Outstanding Contributions to Computing in Education, our ongoing Doctoral Dissertation Awards, and a new set of Student Chapter Awards. All these awards at the ACM level are handled by the steering committee, which approves and oversees the selection of these awards. Every award has got a jury chaired by a jury chair, and the jury shortlists the candidates, follows a rigorous review process, and then decides the winner. The winner is communicated to the steering committee. So this is the process of selection of the awards. The award steering committee at ACM India level is consisting of these dignitaries: Supratik, Anand Deshpande, Jayant, Pankaj Jalote, Hemant Pandey, Sriram Rajamani, and Chandrasekhar Sahasrabudhe. So they have been working throughout the year in coordination with all the jury to decide these award-winning people. Starting with the OCCE award. Dr. Sarvapalli Radhakrishnan said, and I quote, "The teacher refines and reconciles the different currents of thought. She adopts the method not of denial, but of presentation, and shows how these different lines of thought converge towards the same end." End quote. Yes, teachers do play a very important role in our life. ACM India extends its recognition for contributions to teaching by our professional community. This includes recognition of individuals who are dedicated in creating future generation teachers and technical leaders. So this year's jury consisted of Professor M. Balakrishnan, Manish Gupta, Deepak Phatak, who has been the chair of the jury, Susan Roger, Anil Sahasrabudhe, and Sardar Sani. So thank you so much to the jury for working very hard and reviewing all the nominations. This year we received 8 nominations and 1 was chosen as the winner. I request the jury chair, Professor Deepak Phatak, to announce the winner and discuss about the contribution. Professor Phatak.
Thank you. Delighted to announce Professor Sri V. Jawahar as the winner of this award. His fundamental selfless service in teaching of computing and nurturing a generation of students who now serve the larger society have led to an impact in multiple dimensions of computing education, and the jury committee is delighted to select him for this award.
Thank you, Professor Phatak. I would request Professor Jawahar to say a few words, please.
So, yeah, thank you. So I would like to thank, first of all the students with whom I closely worked in the past, and look forward to work with many more students in the future. They made this possible. I learned a lot from them, and I look forward for an exciting journey as a teacher, instructor, supervisor, advisor, friend, colleague in the future. I also would like to thank ACM and Microsoft, especially for this. And as a teacher, this is something very, very special to me. Thank you.
Thank you, Professor Jawahar. ACM India thanks support from Microsoft Research India for this award. We have with us Dr. Satish Sangameshwaran from MSRI. Thank you, Satish, for joining us, and I would like you to say something.
Thank you, Hemangi. On behalf of Microsoft Research, we are extremely honored and proud to be associated with this very prestigious award. And we couldn't be more happier for someone like Professor Jawahar to be declared as a winner this year. We all know the outstanding contribution that he's made, to the computer science community over, many, many decades. And we congratulate Professor Jawahar. We also applaud all the other nominees and all the winners in the other categories, which are going to be announced today. Thank you again, and congratulations again, Professor Jawahar. Pleasure to be here.
Thank you. Requesting the organizers to take a group picture with the sponsor, winner, and the jury chair. Kindly turn on your cameras, please.
Thank you.
Okay, thank you. A strong woman knows that she has strength enough for the journey, but women of strength know that it is the journey that will make them strong. Yes, we have such women of strength among us who keep inspiring the young generation. Even at ACM India, we support and celebrate engagement of women in all aspects of computing. We are happy to recognize their contributions in our next award, the Outstanding Contributions to Computing by Women. The jury for this award was chaired by Neelam Dhawan, and the other jury members were Sandhya Dwarkadas, Niloy Ganguly, Geeta Kannan, Shwetak Patel, B. Ravindran, Barbara Ryder, and Gaurav Sharma. This year, we received 11 nominations, and one was declared as the winner. We thank the jury members for their efforts in choosing the winner. Requesting Hemant Pandey, Executive Director of ACM, to announce the winner and tell about the contribution.
Thank you, Hemangi. Actually, Neelam could not join the session today because she's the rightful person to talk about this. But I was fortunate enough to be an observer on the jury on behalf of the steering committee. So I'll take this opportunity. It's my pleasure to say that Gargi Dasgupta was the winner. As Hemangi said, there were very, very strong contenders for this, but it was Gargi's overall contribution, which is as an individual researcher, as a leader of a reputed research organization. So taking the team with her, as well as being an inspiration through example, through her work to women and her active help in developing their career, in promoting their career for women in STEM. I think that's the major contribution which was recognized by the committee. Hemangi, Gargi, I suppose, is on a flight right now. So
yes, she has sent a video for us. So I'll just play that video.
Thank you, ACM, for this great honor and recognition. It not only motivates me to continue on what is my passion, but it also encourages me to do more. As a researcher, it's always been my dream to see the transformation of the worlds of IT and business with AI. And that's what I will continue to focus on in the coming years. But at the same time, it's also been my passion to set up collaborations across the three pillars that I talk about: the industry, the academia, and the government. And we've made great inroads with our programs on AI, quantum, and hybrid cloud with the top institutes. So thank you for this. And one closing comment that I would make is that often we think that research is serendipitous. However, behind that serendipity, I want to thank the tireless efforts of a dedicated few individuals who work hard to bring together communities that are technically vital, highly skilled, and highly connected. And thank you, ACM, for playing that role in our country.
Gargi continues on her journey, contributing to the society, and she just couldn't make to this award, but she was kind enough to send a short video at such a short notice. So thank you to Gargi. ACM India thanks support from Google Research India for this award. We have Dr. Manish Gupta from Google Research requesting Manish to say a few words.
Thanks, Hemangi. It's a privilege for us to support this award from Google Research India. And again, it was a real pleasure to see Gargi Dasgupta win it. As a former colleague of Gargi, I can attest to the kind of impact that she's had both technically as well as the inspiration that she has provided to so many women leaders and her very active involvement in community building. In fact, she's a member of the ACM India Council. So it's just so wonderful to see, again, a former colleague and friend somebody I really respect, Gargi, win this award. Thank you.
Thank you, Manish. Because we don't have Gargi with us right now, group photo with the winner is not possible. We can take some pictures at the end. So continuing with the ceremony. The next award is the ECR award. So I would like to read out something. Take up one idea, make that one idea your life. Think of it, dream of it, live on that idea. Let the brain, muscles, nerves, every part of your body be full of that idea and just leave every other idea alone. This is the way to success, said Swami Vivekananda. What a real key to success, and our young professionals are truly following such advices and succeeding in their career very early on. ACM India is happy to recognize them through the Early Career Researcher Award. The jury for this award consisted of Vipin Kumar Mosam, Venkat Padmanabhan, Jai Kumar Radhakrishnan, Sunita Saravagi, Moshe Vardi, Gerhard Vaikun, and S. Sudarshan, chaired by Sudarshan. This year, we received 8 nominations and 1 was chosen as the winner. Thank you, jury, for your efforts in selecting the winner. Requesting the jury chair, Sudarshan, to announce the winner and tell about the contribution.
So, like last year, this year too, our young researchers in India have done their best to make the job of the jury hard by performing brilliantly. And, I'm very impressed with how many good researchers we have at the early stage of their career, and this is surely very good for India. But this year, one person stood above the rest and made the choice easy for us, and that was Pratik Ji, who is now with Google Research India. Pratik has had a fantastic career. The number of papers, the citations, the impact he has had are that of a person who has spent twice or thrice of his time in research. So it is a fabulous amount of work he has done in a short time. So this award, is in recognition of his fundamental research contributions to the area of rigorous machine learning, including non-convex optimization, stochastic methods, and robust learning. And the rigorous part includes the theory as well as there is also a lot of practical impact of his work. So I'm very happy that he is receiving the award this year. Congratulations. Thank you, Sudarshan. ACM India thanks the support of sponsorship from Persistent Foundation for the ECR award. We have Madam Sonali and Dr. Anand Deshpande from Persistent. Thank you for joining and taking your time to attend this event. I would request Sonali to say a few words.
Hi, so on behalf of the Persistent Foundation, I would like to congratulate Dr. Pratik Jain for being the award winner this year. We would also like to applaud and appreciate the efforts of all the nominees who were selected for this award. I would also like to thank the ACM, the steering committee, and the jury for working hard to make this possible. And congratulations to all the winners, and thank you, ACM, again. Thank you so much.
Thank you, Sonali. We'll take a group picture with the sponsors, the winner, the jury chair.
Hey, Mangi, how about asking Pratik to say a few words?
Yeah, I don't think he got a chance.
Oh, yeah. Sorry, Pratik. I missed it. Pratik, over to you, please.
Oh, thanks so much. I would love to thank ACM India and Persistent Systems for this wonderful honor. It's really, really a huge honor, and I hope it will be a big motivator in my next phase of the career. And I will also take this chance to thank my colleagues and collaborators and mentors and students throughout this journey, both at Microsoft Research India as well as Google India, including Shriram Rajamani, Manish Gupta, Manik Verma, Venkat Padmanabhan, Ravi Kannan, and many others. Thank you so much.
Thank you. For the group picture, please turn on your cameras.
Done.
Thank you.
Thank you.
Okay, so there are several PhD jokes on the internet. One of them I read goes like this. Long time ago, people who sacrificed their sleep, family, food, laughter, and other joys of life were called saints. Now they are called PhD students. Well, this was on a humorous note, but we do have sincere, hardworking students amongst us and who produce best quality work and award-winning thesis. Most of us have attended the talks yesterday in the Arts Symposium. ACM India recognizes their achievements through the Doctoral Dissertation Award. The jury for this current year's jury was chaired by Professor Somesh Jha, and the other members were Shipra Agarwal, Raman Arora, Pranjal Avasthi, Suman Banerjee, Abhishek Chandra, Kamalika Chaudhary, Mohit Gupta, Dakshita Khurana, Madhusudan Parthasathy, and Nirupam Roy. We received 18 nominations, and because of the tough competition, we have selected 3 top, out of which 1 is the winner and 2 honorable mentions. I request Professor Somesh Jha, chair of the jury, to discuss about the nominations and announce the winner. I will start with the honorable mentions first. Over to you, Somesh.
Hemangi, I think Somesh has not been able to join so far.
Okay, so
I can do the announcement.
Yeah,
That's okay.
Yes, please.
Yeah, so it's a great pleasure to announce the Doctoral Dissertation Awards instituted by ACM India for the best doctoral dissertations, very high quality work coming out from the PhD programs in India. So the first honorable mention for the Best Doctoral Dissertation Award this year goes to Dr. Suprabhat Khoshal, who did his PhD from Indian Institute of Science, Bangalore. And he's being awarded the honorable mention for new algorithmic and hardness results in learning, error correcting codes, and constraint satisfaction problems. So congratulations, Suprabhat, and also to Suprabhat's advisors, Professor Arnab Bhattacharya and Siddharth Barman.
Requesting Suprabhat to say a few words. Suprabhat.
Thank you, ACM, for this recognition. Yeah, this was really an honor, and I'd like to thank the various people who have supported me throughout this journey, my advisors and my family members, old and new. Also, I'd like to thank all my collaborators who have made the various parts of this thesis possible. Yes, this will be a huge inspiration for me going forward and produce work that inspires development and improvement in the overall world of computation. Thanks again.
Thank you, Suprabhat. We'll take a group picture at the end. We'll finish the other 2 awards and then take a DDA level group picture. The next award, I'm putting up the slides, requesting Supratik to announce that, please.
Yeah, it's again a great pleasure to announce the second honorable mention for the Best Doctoral Dissertation Award. This goes to Dr. Vrunda Dave from Indian Institute of Technology, Bombay. And she's being recognized for her thesis, which makes fundamental contributions to the problem of word transducers and to applications of word transducers. So congratulations, Vrunda, and also congratulations to our advisor, Professor Shankara Narayanan Krishna.
Thank you, Vrunda. Would you want to say something?
Thank you, ACM, for recognizing our work and the thesis for this prestigious award. I would like to take this opportunity to thank my advisor, Professor Krishna, for her constant support and guidance. Thank you, ma'am, and thanks to all of my wonderful collaborators. Thank you.
Thank you, Vrunda. Yes, Supratik.
And finally, the Best Doctoral Dissertation Award from ACM India 2021-22 goes to Dr. Suhail Sharif, who completed his PhD dissertation from the Tata Institute of Fundamental Research, Mumbai. And his dissertation makes breakthrough contributions in communication complexity and quantum optimization lower bounds via query complexity. So congratulations, Suhail, and also to his advisor, Professor Arkadev Chakrabarty.
Suhail, over to you.
Thank you. I should really thank the computing community in large for being such a nice environment to work in. I really enjoyed my PhD years, and I owe a lot to them in this dissertation. Thank you, ACM, for giving me this award. And that's it.
Yeah, nice. Thanks, Shoaib. ACM thanks support from TCS for sponsoring this award. It has always been a source of motivation for the young PhD students, and most of them continue to strive so that eventually at the end of the PhD, they are eligible to get this. So thank you, TCS. Requesting Gautam Shroff from TCS to say a few words.
Congratulations to all the award winners. It's been a pleasure for TCS to support this award for a long time. We've supported many PhD scholars, and we, as Al Aho said in the last session, we encourage all the award winners and everyone else, whether they're doing theory or systems or AI, even if you're teaching and doing academic research, do spend time in industry. As Al said, it helps you. We're open to have anyone spend some time with us and just exchange ideas. All the best, everyone.
Thank you, Gautam, and thank you for your encouragement to the students to explore the industry option as well. We'll take a group picture with all the winners, 3 winners, sponsor, jury chair, Suprathi. Please turn on your cameras, please.
Thank you.
Thank you. The next deadline for most of these awards would be around 31st August of this month. So please mark your calendars and think of applying. Okay, next comes our youngest and most enthusiastic group of members. Yes, the student chapters. These chapters have been working throughout the year, making life interesting for themselves and keeping all of us busy with many events that they are organizing. The student chapters have been organizing many activities, and these are the places where we get our next generation leaders and professionals created. To recognize their hard work and community spirit, ACM India has constituted, or rather it has updated with a new set of awards. So because this is the first year for such awards, I request Professor Ranga Rajgopal to describe the new set of awards and the selection procedure. Over to Professor Ranga Rajgopal.
Pleasant evening to everybody. Hemangi, am I audible?
Yes, please.
Yeah, okay. So thanks to ACM India Council for giving me this opportunity. While I'm probably doing the honor lap now, I mean, there's a whole lot of people who supported me in this process and a whole lot of people who worked towards this. It was actually towards the early part of last year, 2021, that the ACM India Internal Engagement Committee in our meetings got together to look at other awards that could be included, because in 2020, we had only one award, which was the Best Chapter Award, Best Student Chapter Award. So a new set of awards were instituted after a lot of deliberations. The idea was to actually look at the ACM Global Awards, student awards that were being given, and from there these various awards were picked up. So we had new awards which were instituted in terms of the Best Chapter Website, Best Student Activities, Best Community Related Activities, and the Best Recruitment Award. But subsequently, what happened was we felt that ACM India was getting a lot of new student chapters also coming in. So we came up with something called the Emerging Student Chapter Award. That's how the new awards were created. These were typically awards that were to be looked at from a point of view of technology events that were conducted, non-technical events, community-related events, and so on. And each of them is recognized with a cash award and certification and so on. So we had a jury which was constituted, which comprised Mr. Satish Babu from the industry. He is the CEO of INAP. We had Dr. Mini Ulanath from Kochi University, and we had Professor Suresh Satpathy, Dean of Research from KIIT, Kalinga Institute, Bhubaneswar, and I was the jury chair. So it was a very long process that we followed, because early this year, like I said, with the support of the student chapter from Chitkara University, ably supported by Dr. Rajneesh, We had a portal that was created, which was announced and communicated to all the student chapters, where they could put up their various activities. And this was a continuous process. And to motivate these student chapters, every month a best chapter was kind of selected and showcased on the ACM student website, by which they would feel good and they will keep working towards better activities and so on. So at the end of the process, sometime towards end of December, we had requested them to select the best 4 activities. Close to about 70 plus nominations, 70 plus chapters had put up these four best activities for the year. So overall, about more than 650 plus events were reported. The jury, the first level that was done was we had to select the best 15 from for each of these awards, and then from the best 15, each of the jury members had to choose the top 3, and then these top 3 were put together, and from there we had to look at. In some cases, it was a clear winner, but in some cases there was a tie. So where there was a tie, we had to seek inputs from ACM headquarters. I mean, just to get into 1 or 2 of the awards, how it was done. For example, in the case for the best website, we had to look at what are the kind of technologies that they have used, how SEO friendly the site was, what is the kind of the way in which they have the UI UX and so on. And in the case of the best recruitment, we had to write back to the shortlisted student chapters to find out what are the kind of recruitment strategies that they had used, what is the kind of membership growth that was there during the year, and so on. So there was a very stringent process that was followed, and there were 3 areas, 3 awards for which there were ties. And for these 3 awards, we had again go back to one each to each of the jury members to request them to relook at the whole thing with the set of inputs that were received from ACM headquarters. And at the end of that, we had a whole list of chapters that were shortlisted for the various awards. From this, the ones that had qualified at least for 3 or more of these categories were again looked at for looking at the overall best chapter award. So this is how the whole process was. So it is my pleasure, because I see that there are a whole lot of student chapters and members who are very excited and who are here today to share this moment with us. So it's my pleasure to announce the awardees and the people who have received this for this year with a whole lot of hard work. So we have for the best chapter website award, if I can look at that. Okay, for this, I think we have the best chapter activities award. We had the ACM VIT Women ACMW student chapter that was conferred this. They had used very innovative methodologies for actually reaching out to their student members in terms of podcasts and so on. And it was very consistently done over the year. For the emerging chapter, we had the GMRIT ACMW from Rajam, Andhra Pradesh, which was the emerging chapter award. VIT, as you know, is in Tamil Nadu. For the outstanding recruitment program, we had the I2IT ACM student chapter from Pune, which was shortlisted. Apart from this, we had the best website award, which was backed by PICT Pune, and the Manipal University MUJ ACM student chapter in Jaipur had done a whole lot of activities. In fact, I would, when time permits, probably you could look at their website and look at the kind of activities that they had done. A whole lot of activities, more than 100 activities for the year, which are very meaningful, and they were awarded the best outstanding chapter award for the year. So overall, it was a great learning for the jury to look at various kinds of awards and how they had conducted various events. And I would like to say is congrats to all the winners. Excellence is a journey, not a destination, as they always say. So I hope that the winners are inspired to do better in the coming year, and the other chapters who have done very well, the differences in certain areas was very thin. It was very difficult for the jury to decide. So I hope that they would be motivated to put in better efforts in the coming year and make it to the list in the coming year. All the best to all of you. Thank you, ACM.
Thank you, Professor. So I'm just going through the complete list. The Outstanding Chapter Award is MUJ ACM Student Chapter. Outstanding Website, PICT ACM Student Chapter. Outstanding Activities, VIT Chapter. Outstanding Community Service, UPES ACMW Student Chapter, and Emerging Chapter Award to JMRIT ACMW Chapter. Congratulations to all of you. For all these chapters, we have collected short videos. So I would request the local organizers to play the videos for them. I'll stop screen share. Local organizers, can we have the videos, please?
If the videos are taking time, perhaps we can invite.
Sir, Ranga sir, please turn on your camera, sir.
आवाज कुणाचा DICT-चा आवाज कुणाचा DICT-चा
If the videos are not playing, then I guess we can go to SET, our sponsor.
All right, so we can continue playing the videos once they are ready, maybe after another couple of minutes. Okay, so thank you to ICETIS for sponsoring all the student chapters. We have Mr. Seth Nesbitt from ICETIS. So I would request Seth to say a few words.
Thanks so much, Shimanji. On behalf of the entire iCertis organization, we're extremely honored to sponsor the Student Chapter Awards and by our association with ACM. Huge congratulations to all the winners, and we celebrate the promise and dedication you've shown. It's an incredible amount of work. I'll just wrap up by saying I echo my colleague at TCF, and if you're so inclined, we encourage you to explore industry opportunities at iCertis. We'd love to hear from you. And again, a big congratulations to everyone.
Thank you. We will take a photograph with the sponsor, Professor Ranga Rajgopal, and any student chapter representative. If they are here, they can turn on their cameras.
Let's get those cameras on. Yeah. Congratulations, everyone. Great job. Great job.
Thank you, everybody. Local organizers, can we have the videos? It's taking some more time. You're muted.
Yes, ma'am. Yes, ma'am.
Okay, so are you going to play them right now?
Yeah, yes, ma'am.
Okay, so I'll be in wait.
Is it visible, ma'am?
Yes, yes.
Yes, ma'am. Okay.
Hello and welcome to Manipal University Jaipur ACM Student Chapter. I am Dr. Akhilesh Kumar Sharma, Faculty Coordinator.
And I am Aditya Giri, the Chairperson for this year.
We have been awarded the Outstanding Chapter Award for 2021-22 session.
This is the fruitful results of our various initiatives such as ACM Mentorship Program, ACM Experience Projects Team, Intern with ACM and many more. We believe in tech for good and have conducted various chapter activities to support people with our technical expertise. We connect tech with people, passion, and possibilities. Thank you.
Thank you.
outset, I'd like to congratulate the ACM chapter student members of GMR Research Technology, and they have done a great job.
Congratulations to the ACM Women chapter of GMRIT. Thanks to the jury committee of ACM India. I ensure that our ACM Women chapter will be giving their best for the upcoming years.
We feel so happy for receiving this Outstanding Emerging Chapter Award for the year 2021.
It's a great joy that we are awarded with Outstanding Emerging Student Chapter Award. I would like to congratulate all of my team for their great efforts, and I would also like to congratulate the other student chapters who won the awards. We are looking for great contributions to ACM in the days to come. Thank you so much.
Thank you. And really, it has boosted our spirits also. The evening has become so lively after looking at these videos. Thank you for the videos, all the student chapters, and thank you, Professor Rangaraj Gopal, for.
I would just like to add one thing, Hemangi, here. Out of the 6 awards, we have 3 which have been taken by ACM W chapters.
Yeah.
That's a huge, so that's a very encouraging thing for the ACM W chapter. That's all. Thank you.
Great motivator. Thank you. All right. Okay, so all things big and small have to come to an end to have new beginnings for the new year. I would request Venkatesh Raman, Secretary, ACM India Council, to present the vote of thanks. He will be sharing the screen and giving the vote of thanks. Over to you, Venkatesh.
Thank you, Hemangi. Can you see the screen?
Yes.
Okay, so to repeat the oft-repeated cliche, all good things come to an end. So with the announcement of the chapter awards, that brings the curtain to the award ceremony, annual event, the associated 4-day event starting from ACM Women's Workshop, ARCs, and annual event. It's also a culmination of nearly about a year of preparation, and I have the simplest and the most pleasing task of thanking all those who made this possible. So I'll start with thanking the distinguished speakers of the annual event, because after all, the speakers bring in the quality of the event. Alfred Ahu, Margaret Martinozzi, Shrikant Srinivasan, Manik Verma, and the interviewer, Sriram Rajamani. As you know, it's been a pretty difficult year, and so many of the speakers and the interviewer had to adjust their schedule under difficult circumstances to make this happen, and it was a great set of talks, and thanks to all the speakers and Sriram for that. We thank our distinguished guests from ACM headquarters, President of ACM, Gabriela Kotsis, and Vicky Hansen, for participating at some, and making time in their schedule. Speakers and session chairs of ACM Women, ARCs, and annual event. Our sponsors, including of various awards, platinum, gold, and silver sponsors, as well as sponsors of various awards. The steering committee and program committee of ACM Workshop and Arts, and these are the team of people who actually have been working nearly for the last year, and particularly more intensely in the last 3-4 months. ACM India Council members, Hemant Pandey for coordinating with all the award winners, along with Hemangi, the award winners and jury members. Hemangi Kapoor, Vice President, for anchoring the entire awards ceremony. You can see that it was quite a non-trivial task, coordinating with nearly about 30-40 people and various videos and coming up with all these beautiful slides. I know the whole thing worked like a clockwork, and it's amazing. So it's tremendous work from Hemangi in the last several weeks, trying to coordinate with all those people. And last but not the least, the technical team of Sonia Gacha, Neil Dara Mishra, Shekhar Chakrabade, and Rutvi Shah. When we were all listening to the talks, these were the people who were behind, coordinating with the speakers to make sure the slides work okay, moving people from participants to panelists, putting the spotlights on right people and taking all these pictures. So, while physical organization has its own challenges, the virtual organization has a different set of challenges. And it is this team of people who made all this work like a clockwork. And last but not the least, the organizing team from PSG College of Technology, Coimbatore, they tried very hard twice to get us all there. In fact, I personally have very close association with PSG College. And then I was all looking forward to visiting them. I had my plans starting from December until this, the new wave hit us. And I'm sure I will visit them again anyway. I'll find any excuse to go and visit PSG College, and we hope that they can all have you there very soon. So we particularly thank the principal, the head of the Department of Applied Math and Computing, Narajan, Ranga Rajagopal, Suresh, and several other volunteers, students, and teachers for working behind the scene to coordinate everything. Great job on the cultural programs. It was an extremely pleasant surprise to optimally use the break times. And last but not the least, all the participants for showing up for all the events. And we hope to see you all in Bhopal next year for the annual event. Thank you. And over to you, Himangi. Himangi, or to the organizing team, or Jayant, you want to say something?
No, I thought Himangi was on mute and probably not realized it. Yeah.
I had muted myself. So I would like to thank Venkatesh, who has given such sweet words of appreciation, and all our efforts come to fruit when we hear such nice things. So thank you, Venkatesh, for your kind words. So we come to end of today's session. Sorry. So see you all next year in Bhopal, and very good night, and thank you to all of you. So we close our award ceremony here, and I will request all the dignitaries we'll just take quick group photographs. I'll stop screen share. In a minute, we'll take some pictures in the grid view and close the session. Thank you, everybody, and let's continue our good work for the coming year. Thanks, and bye-bye.
Yeah, I would just like to add, great job, everybody. It was a wonderful team effort, and it's obvious that a lot of effort has gone into making this a grand success. Thank you all very much.
Absolutely. I think let's all, those who can turn on their videos, those who have the panelist privilege, everybody turn on their videos so that we can take as many pictures as possible. I see one screen here. Okay, I see another screen. Okay. So both screens have been captured. Somebody else has just appeared. Another picture. Wonderful. Meenakshi. Okay. Another picture. As in when people come, I think we have no dearth of picture opportunities. Anybody else taking pictures, please go ahead, because I might miss some. Thank you, everybody. It's been a wonderful occasion here. And I echo Himangi, Venkatesh, Jayant's words. Thank you to everybody, to the organizers.
And a reminder to the council members to come back at 9:15 for the meeting with the headquarters team.
Correct. The council members' work is not over. There is a council meeting to happen yet. So let's get a quick grab a bite of dinner and come back at 9:50 India.
Yeah, thanks on behalf of the organizing committee. Thanks, Jayan. Thanks, Dr. Meenakshi. Thanks, everybody, for giving us the opportunity for the second year. And we we have been able to live up to the expectations. And we hope that in the coming years, we will be able to host another grand event of ACM physically. Thank you very much.
Thank you.
Thank you.
Bye-bye. Good night.
Thanks, everyone.
Bye. Bye, everybody.
Bye.
Good night. Good night.
Night. Bye.
Bye.